Your your mic might be off. Let me just check.
It's on? Okay. I hope everybody can hear me now. Yeah, I can. All right, great. So this is the AMWG meeting. Welcome. Let's go ahead and get started. This is our code of conduct for everybody for the meeting. You saw this yesterday. And before we get started on the update itself, I want to go through some sort of AMWG news. Today is my last day as co-chair, and I will be happily accepting Peter Lauritsen's. So welcome, Peter, and Peter's in the back. I hope some of the events that happened during my 6 years don't happen during yours. All right. So, okay, so I'll just go ahead and kind of try to summarize where we are today. I think we are, everybody who's been at these meetings has seen a slide like this multiple times. So we have new vertical structure. I think that's kind of a big development over the last 6 years. We have higher vertical resolution and a higher model top. We've unified many of the functions of what was WACM and CAM, so they're now sort of a unified model. We have two configurations: the CMIP class workhorse, which has a top at around 80 kilometers, and a sort of hopefully more economical 42 kilometer top model with 58 levels for development of and testing of things that you don't really expect to be of much relevance in the middle atmosphere. So since January, we've done some kind of, I'd call them final cleanup updates on the model. We have a new sort of, we've always been running our testing so far with the specified chemistry comp set from WACM. We've updated this to a new comp set that we're calling prognostic greenhouse gas. It uses advected and radiatively active greenhouse gases, including CO2. It's used for both the L58 and the L93. There are no differences between the two configurations except for a specified upper boundary condition on water for the L58. For the L93, we just have zero flux boundary conditions for all things at the top of the model. So these are the all right. No? Oh, there it is. Finally, it takes a while. So these are the FLT and everybody's favorite BLT comp sets. And for the mid-top, or the 80 kilometer, we have FMT and BMT. We've updated the organic aerosols and aqueous chemistry. Prognostic momentum flux and club is now the default. And we've unified, at least in terms of the structure, the gravity wave parameterizations in both the mid-top and the high top, or sorry, the low top and the mid-top. So, chemistry changes resulted in brighter clouds. We went from about 45, which is close to the new series EBAF. When the chemistry updates came in a few months ago, our clouds brightened by almost 5 watts per meter squared, and that's a problem. Ben Stevens did some, I think, really nice retuning using parameters that we don't normally use, including things like the the radius of uh, ice clouds converting to snow, things like that. But he managed to come up with some retuning that brought us back about 2 watts and really didn't affect things in the stratus regions, which I think, you know, on second thought, they're probably a bit strong, but we wanted to try to retune the model in a way that didn't affect stratus decks too severely, and with these retunings that he came up with, did succeed in reducing by about 2.5 watts. We're still cold. We're at 47 now instead of 45, and initial couple testing with this configuration of the model, which started about 2 weeks ago to a month. Unfortunately, we are freezing the lab C. This is a persistent problem with our model, so I think we are going to have to resort to more adjustments. We're going to we are going to go ahead and attack the stratus decks to try to get the clouds thinner and our rest DOM a little higher for the coupled simulations. All right, so that's sort of where we are with tuning of the atmosphere clouds. We've also, as I mentioned earlier, we've unified the structure of the gravity wave parameterizations in the model. This is what we've been using up to now. So in the low top model, we have no non-orographic gravity waves. So the only source of gravity wave drag, parameterized drag anyway, in the low top model is orographic waves. That was the state before. The mid top model uses the Wacom configuration with non-orographic waves turned on. So fronts and convection can produce gravity waves. Another parameter is the treatment of this flux at the top of the model. We had been using sort of a transparent boundary condition for gravity wave, for parameterized gravity waves. We'd been using a transparent condition at the top, in the low top model. So the waves just move through the model. If they haven't broken for, let's call them dynamical reasons, below the model top, they just propagate through. In the mid-top model, as was the case in Wacom, everything's absorbed at the top. So we have now changed. I'll show you in a second. We get better, I'd say, very good agreement between the low top and the mid-top configuration using the same settings for the gravity waves now. So that's illustrated here. This shows annual mean, it only works this way. Annual mean zonal winds, it's in log P format, and temperatures. This is a comparison of the low top configuration and the mid top configuration. And what you see is that, below maybe 20 millibars, the simulations agree very well. So we're getting, I think, a good agreement between the low top and the mid top configurations, which is not essential, but it's certainly desirable if we're trying to use the low top for development. So I'm just going to quickly go over the climate of the mid-top model now. This is our 80-kilometer model, which will eventually be the CMIP workhorse model. So the top at 80 kilometers, 93 levels, and it shows behavior that's not uncommon in models of the middle atmosphere. That is, you can tune the gravity wave drag to give you good answers in the in the northern hemisphere over here during winter. So here we have a very good simulation of the polar night jet in the stratosphere in this model. Unfortunately, we're really unable to shake away from this strong bias in winds in the southern hemisphere. That might not be such a problem on its own, but this is, it's associated, thermal wind, it's associated with a very strong cold bias in the southern hemisphere, and that's going to be a problem for our chemistry. So in the next few months, we'll continue to experiment with orographic drag. I think we shouldn't expect the orographic drag to solve all these problems. I mean, just look at a map and see how much orography there is in the southern hemisphere. It's really 3 or 4 spots. So I think we probably will have to, address this problem using other sources of parameterized gravity waves. But I hope I'm pretty confident we'll get this soon. The QBO in this model is looking pretty good. As all of us who were involved in this design know, that was a target for the model. So the QBO is looking okay in the current version of the model. And again, this is, something we have to keep looking at and perhaps retuning if things in the convection scheme change, for example. So other things we want to keep in mind as we, try to find, how much time do I have? None. Okay. So Isla Simpson has started looking in more detail at the climate of this model, and we see some undesirable changes in the simulation of our 200 millibar winds. One example, it's not the only thing, but it's what I think it's something we can focus on, is the reduction of this Pacific jet at 200 millibars. It's really kind of weakened in the current version of the model. It was better in CAM 6. So this is something we need to address. It's not clear yet how, but I believe that this has something to do with our increased boundary layer resolution, not the free tropospheric resolution. But hopefully, again, more about this will come in the next few months. So where we are on the development timeline, this was the CMIP timeline. I know that there have been updates in the last 24 hours. I don't know. I don't know whether these new updates have an impact on our timeline, but we're expecting to start simulations in mid to late 2024 with CSM 3. So this is where we are now. We're here. This is kind of a schematic of our development process. We do tuning and development of individual components for a while. We get together and start coupled simulations. Of course, during these simulations, tuning and other development doesn't stop, but it's aimed at coupled simulation behavior. So now we're here. We're starting a new round of coupled evaluation, and we'll see how this goes in the next few months. Finally, this is a slide from Adam. Another element of our planning is transitioning to the new CAM-SEMA infrastructure, and Adam has illustrated here how our physics will go from our CAM repository into an CCPP. This is a common community physics package. It will be a new framework for our physics, and we expect this transition to happen over the next few years. And I don't know if, Adam, you have anything to add. Sorry to put you on the spot. All right. Okay, so I think that's it for this update. Thank you very much. Any questions?
Great. Thanks, Julio. So I think we have time for one or two quick questions if there are some. But okay, if not, we'll move on to our next speaker, which is Mary Barth here? Remote? Oh, we are remote. Okay.
Okay. We have a remote presentation next.
I don't see that presenter
Yeah.
online. Yep.
Uh-oh.
Next presenter, if you're under a different name, just raise your digital
okay.
hand.
She wrote that she's there. She wrote in the chat. So you might have to give her privileges to.
Okay, Mary, you should be able to unmute and share your screen.
Okay, so you can hear me?
Yes, we can. And then if you want to share your screen.
Okay.
As you're doing that, I'll just mention, so our next speaker is Mary Barth, who's going to talk about an update on the System for Integrated Modeling of the Atmosphere, SEMA. Yeah, so we can see your screen if you just want to go to full screen mode.
Yeah. So I have to move a bunch of screens out of the way.
Yeah, once you share the screen, then all the buttons go to different
Okay.
location. Perfect.
Actually, not. There's a,
That works on our side.
I have a little screen that lists, I guess, maybe participants. I'm not sure if I can close it.
Yeah, you should be able to if you go to up to one of the options at the top.
Okay, got it.
Perfect.
Okay. Yeah, so thank you. So today I'm going to give an update on the System for Integrated Modeling of the Atmosphere, or SEMA. And I want to begin by thanking the leadership of the SEMA project listed here. You will see that this is a group of NCAR scientists and software engineers from across NCAR representing the CGD, ACOM, MCube, HAO, and computational science laboratories at NCAR. We also have a software engineering project manager, Jordan Powers, who helps coordinate the software engineering development. I want to mention that CESM interests are well represented here, and as well as on the SEMA steering committee, which includes the CGD director and the CISL lab director. So so I want to talk about 4 things in this presentation listed here. Just remind you of the goals, give you a taste of some of our recent accomplishments, and then talk about some ongoing activities, and then introduce you to this cross-disciplinary science application project. The aim of the SEMA project is to unify NCAR atmospheric modeling system from multiple models, which you see over here on the left side, going from global scale with CAM and WACM and the MPAS model to regional scale like the WRF model, and down to local scales like large eddy simulations, and move these to a single atmospheric modeling system, which is what we hope to achieve in the coming years. We think that with the single modeling atmospheric system, that we will be able to enhance our frontier science studies and in climate, weather, chemistry, geospace, but also in cross-disciplinary research using this one system. And that's kind of described here in this graphic with the Venn diagram, where we think these frontier science simulations are in these overlapping regions that you see in the Venn diagram. Back in 2020, we had a workshop, and here are a few examples of some of these science applications, looking at atmospheric chemistry and mineralogy, going from urban centers to global scales, biomass burning, to global scales, deep convection to global scales, looking at space weather and geospatial atmospheric coupling, looking at the predictability of tropical cyclone formation in an Earth system model, which I think will be really transformative. And then, but also looking at other topics like extreme weather events in a changing climate and predictability of the Arctic. And hopefully you can keep thinking of one after another type of topic that the single atmospheric modeling system can address. As we were visioning this new system, we realized that there are additional benefits. And to me, one of the important ones is that we're bringing in this broader range of atmospheric and geospace scientists using the same tool. And this increases the interdisciplinary interaction. It fosters collaborations, brings in diverse perspectives, and exchanges knowledge and tools. I think that's a real good benefit. But another important benefit is creating a centralized and efficient model development, maintenance, and support system. We also realized that by doing this change, that we had the opportunity to modernize our underlying software, including doing some code refactoring for GPUs and other computing architectures. Okay, so we can go back several years and say, we started here, and that start is with the CAM model with CAM physics and chemistry and aerosols, includes thermosphere and ionosphere, and coupling it to dynamics with the FV dynamical core and the spectral element dynamical core. During the past 5 years, there's been a coordinated effort of implementing the non-hydrostatic MPAS dynamical core into CAM. And so we are now at this point, you've seen some presentations that include that, and it's very promising. But our work's not done. We have more work to do to bring in the CCPP framework that Julio just mentioned, and then create the physics, the chemistry, and the dynamics code to be CCPP compliant. So that gives you a baseline of our where we're trying to go and the next steps of what we're going to do. I just wanted to highlight some recent accomplishments, and as you saw from Adam's talk and previous presentations by Han Lee, that one of the things that CESM has helped support are simulations providing insights on the effects of grid size for both the Arctic region and for geospace, for doing these Gamera Wacom coupling simulations. And both of these, I think, the bottom line is that this, higher grid resolution helps to represent processes a little more, with a little more fidelity, which is nice. But I also wanted to talk about these core CEMA development efforts over the past few months. One is looking at these recent tests that have shown improved convective storms, and then showing that running with chemistry with CAM MPAS is viable. So let me spend a few minutes showing you a couple of examples. So yesterday you saw slides similar to this in Jim Hurl's talk, talking about the recent tests that the MG3 with the MG3 cloud physics scheme. So this is a convective squall line that was observed in spring of 2017. And so the group is aiming to see how well CAM with MPAS dynamical core can represent the squall line. The observations shown in the left panel shows the radar reflectivity for that storm. In the next panel is an MPAS standalone simulation using the WRF physics suite. And you can see that there's a lot of similarities with the leading line of convection, very typical of squall lines, and a trailing stratiform region. When the group created or took the same case and ran CAM MPAS with CAM6 physics, and the G3 default settings, they got a very different picture of this convective storm. It's not very well representative of the observations yet. But over the past few months, they've been doing a lot of tuning to both the cloud physics scheme and also by removing this cloud fraction estimation from club affecting the cloud physics in this region. And you can see in the last panel that there's a much better representation of the squall line in the radar reflectivity. This improvement is really shown with the cold pool. These are vertical cross sections of the potential temperature. And you can see in these three panels on the left is the MPAS standalone model. Looking in the circled regions, you can see where this transition going from the potential temperature ahead of the squall line, which is warm, into a kind of deep cold pool, which is very typical of squall lines. This is not seen at all in the out of the box CAM and MPAS simulation, but with the tuning that this group did, you can see a much more proper cold pool being represented in the storm. So this is showing some really good progress in developing CAM MPAS for representing convective weather systems. And I'm looking forward to maybe some further improvements over the next couple of months. With the success of CAM MPAS, we've over on the atmospheric chemistry side of the group, we're curious to see if we could run CAM MPAS with full chemistry. And so we're doing that with this grid. It's a grid with regional refinement over the Asian summer monsoon region. And we're testing it on a 5-day period in August of 2019. The early results are promising, and I'll just show you a couple of plots from that. So what I'm showing here are carbon monoxide maps at 14 kilometers altitude. In the upper left are the results from the CAM MPAS with full chemistry run. Upper right is WACM for about the same altitude. And then in the lower right is Musica version 0, which is using the spectral element core with regional refinement down to 25 kilometers. And you can see from these maps that the transport patterns are the same and that the magnitude of the carbon monoxide concentrations are pretty similar among simulations. So this has given us good confidence that some things are going okay in this new model run. But you have to keep in mind that this is carbon monoxide. It's really a transport tracer. And so I wanted to show you what other chemical species, and that's sulfur dioxide, which has a much shorter lifetime chemically, and also is prone to wet scavenging. And so it should be affected, maybe in a little bit different way. And so at 14 kilometers altitude, the SO2 in the CAM MPAS with chemistry run, again, shows quite similar patterns to the WACM simulation and has similar magnitudes, but there definitely are more differences here compared to the other two global model runs. So again, there's a lot more to evaluate with these simulations, but we do definitely feel like it's promising that we can run atmospheric chemistry at these convective and urban scales over parts of the globe. All right, so those are some recent updates, and I want to just talk a little bit now about our ongoing development activities and introduce this cross-disciplinary science application project.
So Mary, I just want to chime in and let you know you have about 2 minutes left.
Yeah, and I'm almost there. So listed here are the core CEMA development efforts. I really want to highlight number 2. This is alluding to what Julio just showed in his last slide, where our main focus of from this year and the coming years is to develop what's called CAM CEMA, and that includes finishing the CCPP framework, refactoring the CAM physics to be compliant with CCPP, getting the chemistry module to be CCPP compliant, and testing WRF MPAS CCPP compliant physics in CAN-SEMA. But we're also doing other activities, like working with the ionospheric module, implementing abstract interfaces for aerosol physics interfaces, further developing MICM and deep atmospheric dynamical core with MPAS, et cetera. So these, you can see, are a little more disciplinary. And there's also, because of the benefit opportunities of SEMA, we wanted to include a cross-disciplinary project as well. So in the last couple months, a project was identified to proceed, and this is a project that's on subseasonal to seasonal sun to surface prediction system. The PI of the project is Nick Davis, and you can see from the team listed there that it is a cross NCAR project going from M-Cube to CGD and HEO, as well as the ACOM laboratories. Their goals are to evaluate the role of small-scale processes on extreme weather events and quantify the value of the refined resolution to the events. The project will address 2 extreme weather events, a cold air outbreak that hit Texas in February 2021, and the Pacific Northwest heat wave that happened later that year in June of 2021. And so besides some of these things that are listed here, I think one of the real benefits that we hope to get out of this project is to establish a workflow for ensemble simulations using refined grids. Okay, so I'm just going to end my talk here, listing some of the updates as to what SEMA has been doing over this last several months, highlighting the number 3 and number 4, where we're making good progress on some development with SEMA, and reminding you about our ongoing and near-term efforts to focus on creating CAN-SEMA. So with that, I want to thank you, and I am looking forward to seeing you all in person tomorrow. So thanks a lot.
Thanks, Mary. I think to keep on schedule, we're going to move to the next talk, which is the next speaker is João Teixeira, who's going to talk about some of the updated EDMF results.
Hello. Thank you for the opportunity. Good morning. Adam and I are going to give you a brief summary of the EDMF CPT.
He's working on it.
All right, thank you. So Adam and I will give you a brief summary of the EDMF CPT. I move up and down like this. No. Yeah, this one.
Yeah, perfect.
Right, and the pointer is.
Then you have to hold it towards the screen.
Huh? All right, perfect. All right, okay, so sorry for the slight delay. Catch up. This is sort of a more programmatic slide on what the EDMF CPT is. The goal is to reduce key biases related to PBL clouds and deep convection in both the NCAR and GFDL model, although today we'll focus on the NCAR model. It's the CESM workshop after all. The overall philosophy is to implement and validate a sort of unified or different versions of unified PBL and convection parameterizations based on concepts from eddy diffusivity mass flux. We're focused on the PBL, but also the PBL and transition to deep convection, both over the ocean, sort of more of a spatial transition, and the diurnal cycle over land as well. I'm the lead PI. The PIs are Julio Bachmeister, Leo Donner, Rong Fu, Georgios Mateo, and Michael Weedy. One of those two, but I'm clicking both.
That's bad. All right, try the middle big
one. Okay, sorry, I just need to be stronger. All right, so this is a motivation slide. We all know why we're here. We're trying to improve the understanding of the climate system, of the atmosphere in terms of climate and weather. But the practical motivation of a lot of our work is the fact that although in the end, all of these different processes you see in this schematic are different manifestations of a turbulent atmosphere interacting with phase transitions and long wave and short wave radiation, in practice, for practical reasons, engineering ways in which we build our models, our current parameterizations are often very modular, and you'll have models that for example, will have a routine for the stable boundary layer, another one for the dry convective boundary layer, sometimes another one for stratocumulus and so on. So over the last couple of decades, a few different groups around the world have been trying to come up with ideas in which we can to sort of unify as much as possible the representation of grid scale mixing, right? So turbulence and convection. And what we're going to show you is one way to do that implemented in the NCAR model. Point it somewhere? Is this, oh, it's the point. Anyway, so, okay. So, okay, there'll be like a 10-second between each slide, sorry. Behind a lot, if not everything we do, are these tools called large eddy simulation. I'm not going to summarize what LES is because I'm pretty sure all of you know what LES is and how powerful it is. But I want to summarize a paper that I think is really important and hopefully will be very influential. This was done by our colleagues at the University of Connecticut as part of the CPT, Umaima and Georgius. And what they did was to try to test the sensitivity of the representation of shallow convection, precipitating shallow convection to the domain size, which is something that hasn't been done very much for a variety of good reasons. Now what they did, and you can see it here, they have simulations in which they have a domain size of about 40 by 40 kilometers, another one 80 by 80, another one 160 by 160. They actually have a new one of 320 by 320, but it's not too different from the 160. And what is immediately apparent to you is that if you run the model with sort of domain sizes of about 40 kilometers or 80 kilometers or less, and most, if not all of the LES that we have used for shallow convection have domain sizes that are smaller than this. They constrain the size of what actually the atmosphere wants to do, right? And you can see it on the 160 that there are these very large structures, much bigger than 40 and 80 kilometer domains that develop naturally if you give it the space to do it, right? And so that's the first conclusion of the paper and the studies, that convection organization does depend on the LES domain size. However, they also found that horizontal organization does not fundamentally modify the local convection. And you can see that in that context, you can see it in sort of the mean thermodynamic profiles. They don't change very much. The vertical velocity variance, the scale of fluxes, none of them is particularly sensitive to domain size. And so what this shows is it sort of partly explains why previous LES simulations and parameterizations based on the LES simulations that use very small domains actually have been somewhat successful. Is that in the end, some of the things that we're actually looking for, like the vertical fluxes and the mean profiles, don't change very much. However, this is not the end of the story, and this is a story to be continued, and one way to see that it is to be continued is that the TKE, for example, depends on domain size. Now let me get into the parameterization side of the story. So what we have done in terms of CAM was to merge a high order closure, club, with multiple plumes, a mass flux scheme based on multiple plumes. And so intuitively, you can think of it as club representing sort of the double Gaussian subgrid scale mixing that happens in the atmosphere, while the plumes are sort of discrete, additional discrete skewness. And you'll see that better in a slide, in the next slide or two. In practical terms, the multiple plumes do things to say. We sample from surface layer thermodynamic PDFs, and also we use an approach that based on studies by Romps and Kwang and others that we followed. And it's basically a stochastic lateral entrainment with some modifications, in particular one that we did recently, which is that part of our lateral entrainment is based on turbulent kinetic energy that is produced by the club scheme. Now, the way we actually implement this in practice is actually to get to the guts of the scheme. We go to the 5-diagonal solver of club, where we solve turbulent fluxes and mean field simultaneously and bring the mass flux terms to the right-hand side of those equations. So let me show you a couple of quick results of things that we've done over the last year or so. One is based on the paper written by Michael Weedy and many of us, and it's focused on shallow convection. This is a particular case that's very well known, the Bomex case. It's a non-precipitating shallow convection case. And you see profiles of both mean liquid water, and cloud cover. And there's 3 lines I want you to look at. So one is the black line, which is LES. The blue line is club. And the sort of orangey pink salmon, I'm not really sure what the color is club MF. Then there's 2 additional lines that sort of decompose club MF into the MF part and the club part. But if you focus on the first 3, you can see that although far from perfect, the club MF really does represent reality as sort of produced by the LES better than club alone. And that happens because these mass flux plumes, these discrete plumes, actually provide additional vertical mixing. You can see that on the next slide, which I think illustrates this relatively nicely. So what we did here was, you get the LES simulation, you take a cut. This is about 250 meters above cloud base, and you get all the points, you get all of the values that you, for total water and liquid water potential temperature, and you plot histograms or a joint PDF from the LES of the perturbations around the mean for both the water and the temperature variable, and you get this plot over here, you get these lines over here, so you get this nice gray joint PDF. It's a histogram, really. Then over here, you get what the club joint PDF is at the same time, at that time step and all that. And in addition, you get this discrete plume. So these dots over there represent the values of thermodynamics at that level for each one of the plumes for that particular time step. And what's quite noticeable here is that in this particular case, and sort of in general for shallow convection, the club PDF does not seem to be, or apparently is not able to sort of be, large enough, wide enough to capture what happens in the skewed part of the distribution. It's really here that most of the action takes place. This is where the convection is taking place, right? And so the plumes, these discrete plumes, add this other dimension, right? They go out there to the place where there's, where there's action, and they represent that convection mixing that club is unable to do. Now, so what we've done over the last, I say, 18 months is to test a variety of these configurations of club NF in the full-blown model. And this is actually a particular version that we like, and we work a lot in sort of our control version, is version 76. And what we've done is that for all of the simulations right now that we do with Club MF, we don't run with explicit deep convection. So Club MF does all of the vertical mixing from the stable boundary layer to the dry convection, shallow convection, and deep convection. And in the end, is able to produce what we consider a realistic climatology of many of the fundamental properties of the Earth's atmosphere, clouds, precipitation, top of the atmosphere, radiation. And these are just 2 examples. So on the right, you have low cloud cover. On the left, you have precipitation. Top, you have the observations. Then you have control level 32, control 58, and Club MF. And if you look at it relatively carefully, you see that the differences between Club MF and the other models compared to the observations are not significant. And in some cases, if something, the new model seems to produce better results. Now, before we summarize, I'll ask Adam to talk quickly about some of very recent experiments that we've done.
I'll just wait while it does
Okay,
that.
go.
Okay. Thanks, Joao. We have to do deep convection. If we have any chance of dethroning ZM, we have to do deep convection. We are not using a convective quasi-equilibrium closure. We are integrating our mass flux plumes upward, taking the buoyancy at each level to inform the next level. And so we are the exception rather than the rule when it comes to deep convection schemes. And so then we really want to target a dynamic entrainment rate that adjusts as convection deepens. And so a very basic concept that's used is you can take the properties of your plume ensemble over prior time steps, and you can use that to inform the entrainment rate at the current time step. And that can allow some sort of natural progression from shallow to deep. And so here's an example where I'm just taking the depth of convection at the prior time steps and using that to inform the entrainment length scale. And there's an 11-member ensemble shown there where is the top of the plumes compared to LES. And you can see we're starting to get that nice progression. And this is the LBA case over the South America. But obviously we're nowhere near as deep as LES indicates we should be, nor are our precipitation rates high enough. And so we are been using this cold pool parameterization based on Kajsa-Sulj et al. 2019, which really describes the basic fundamentals of our mass flux scheme that we're using. And so the way that we want to parameterize cold pools is they facilitate new convection and they can organize convection, and you can graft that behavior onto a bulk entrainment rate. You can imagine your entrainment rate would go down with organized convection and also a larger convective radius. And so what we've used is actually we compute the magnitude of the downdrafts. So we have downdrafts in our scheme at the prior time steps, and that sort of informs, yet again, our entrainment rate at the current time step. So once we start precipitating and we start developing downdrafts, that ends up feeding back on the entrainment rate. And so you can see an 11-member ensemble using this approach. We can start to get deep convection, piercing 9 kilometers up to 15 kilometers in the LBA case. The middle panel just shows what this downdraft magnitudes look like instantaneously. And the bottom plot shows the precipitation rates are now a bit higher than they are in LES, but we have now enveloped our target, and so this is an approach that we want to utilize going forward. And so then I think at this point we should end on the summary, and I'm going to give this back to Joao.
Thank you.
Go ahead and do that.
So just very quickly, so we have a new fully unified sort of PBL shallow and deep convection parameterization. We've combined club with multiple plume mass flux approach. We've tested in single column model, in 3D model. Right now we run it without explicit deep convection, and we are able to produce realistic climatology of clouds, precipitation, and top of the atmosphere radiation. And this is actually particularly significant because as far as we know, we are the first group to actually be able to implement a fully unified PBL shallow deep convection parameterization successfully in a global atmospheric model, weather or climate prediction. Adam highlighted a couple of main development tracks, mostly focus on entrainment formulation. There's also plume initialization work that we're doing. And we also wanted to make sure that we mentioned that there are parallel efforts of colleagues at NCAR working on convective momentum transport and land surface heterogeneity and the connection to plumes that are important to mention as well. So thank you for your time.
To move on to the next speaker to stay on time. And I believe the next speaker is actually online. So do you want to share your screen?
The next speaker, if you can raise your hand so that I can make you a co-host,
Yeah,
and you'll
the
be
last
able to
name
share your
is
screen.
Wong. So our next speaker can you raise your, so they can make you host? The only person that's on video right now. Yep, so they just thumbs up. Okay, perfect. Okay, so you should have access to share your screen in 1 minute or in a second, but as
You should have access now. Please go ahead and share.
Yes. So can you hear me?
Yes, we can.
Do you change?
Yes. Okay, so I'm going to share my screen. So can you hear me?
Yes, we can hear you, and we
Can you see the screen?
Yep, and we can see your screen. So take it away. I'll chime in at 12 minutes just to let you know where you're at.
Okay, so thank you for giving me the opportunity to talk remotely. So my talk is also about club. So we are taking a different approach. So we are talking about improve the club PDF closure in the model. And I would like to thank all the courses for their contribution to this work. And in fact, most of our work was done by our PhD student, Te Li. I think we probably don't have too good details about these slides, and we all know no clouds are regarded as the most significant source of uncertainties in cloud feedback and climate sensitivity. This probably mainly because local simulations depends on a lot of small scale turbulent processes and the interaction with radiation. So I think the previous speaker already said the issue with the low clouds. So we jump to the club. The club is assume the PDF high order closure scheme. And so what this really means? So it's assume the PDF and high order closure. So basically, so the club predict a bunch of high order moments in the model. And because but then in these high order moment equations, so you have a lot of the unclosed high order terms. So in order to close those high order terms, and then the cloud uses and assume the PDF approach. So basically, you assume a functional form of the PDF, and then the exact form of those PDF will be determined by your prognostic equations. So in this way, you close the equation, which is assuming the PDF, and then the assuming the PDF can produce cloud fraction, can be used to diagnose liquid water from PDF, and then can be further used to advance the model into a next time step. So in this way, it provides a unified treatment for boundary layer turbulence, shallow convection, and cloud mechaphysics. But then the one key part of this scheme is that the assuming PDF part is quite a significant part of the club scheme. So basically, the basic form is like this. So it has two functional forms. So it's a PDF1 and then PDF2, and then it's combined through this weighting function. And then for each PDF, you have like the mean of the PDF, and then you have the thickness of the PDF, and then you can combine them together. So, but in the current, I think the default club in Chem6, it used called the ADG1, the analytic double Gaussian 1 PDF form. So what they did is the two Gaussian of this PDF using equal weights. So basically, they assume the weights of the vertical velocity PDF to be equal, same one. But because I mean, in the reality, the PDF should the two PDF should change. The weights of the two PDF should change, right? But then in this formula, it assume is equal of the two PDF. So I think we can expect it's provide serious limitation of the functional form of the PDF. So I think in fact, so that limits the PDF variability. And I think and then a study by Fitch in JS 2019, they use RES simulations to check the ADG1, the PDF closure, the PDF form. And what they found is in the ADG1, the one used in the default chem, it produces two double peak, so basically one peak and then the peak two. This mainly is caused because you assume the equal weights of these two individual Gaussian PDF. So then, in fact, the Fitch provide a way to get away from that equal weights assumptions. And in the paper, they developed this scheme based on RES results. And what they got, this kind of the proposed form. So they have sigma, the weights for the problem 1, and then the weights for the problem 2. And for both weights now are not equal. So then like a separate form, and all this functional form is also based on RES results. And then they introduced a codus into this form, and the codus, because the model didn't, the codus is dependent on the fourth order moment, but because this one, the W prime 4 is not predicted by the model, then they further use the RES results to get the payload to connect the codus from the skewness. Then you can have a completed form for this weights of the vertical velocity, unequal weights of vertical velocity. And to further, so we implement this scheme into the chem model, the chem6 model, and in order to further improve it, So we further updated the width of the total water and the width of the liquid potential temperature, these other two variables. And what we did is kind of a simple scaling. We scale these forms of the Plume 2 with the scrutinies. And I think the exact, we have kind of the tunable parameter here, and here we use 1.2 of the scrutinies. And the exact reason for why we choose this is because from the single column simulations, we found the 1.2 is a better choice for the results. To which that, then we first we test the new PDF, the new closure scheme into the model. And one here is LES, the large eddy simulation results, and this is one ADG1, the default one, and this is a new one. And what here we show is W and the QT joint distribution, and this is a joint distribution, and this is the projected distribution in the vertical velocity coordinate. And here is projected distribution on the QT coordinate. So I think one thing you can clearly see is in the ADG2, as we mentioned before, it produces like a double peak. But then with the updated scheme, so this double peak kind of disappeared. And then again, another thing is we check the joint distribution of the theta L and the QT. And so this line shows the saturation line. So it's above this is the saturated region. So from LES in this particular case, and then you can see the saturated area is about 76%. But then in the ADG1, it's very small. But then in the new scheme, the updated scheme, so it's 16.6%. So you can clearly see the new one agrees better with the large eddy simulation results. And then next we run the global simulations. So it's a AMAP type of simulations. So ADG1 is a default scheme. The new one is a updated scheme. And we run the present day results with the climatology SST. And also we in the end we try to see how this the cloud feedback might be different in this new scheme. So we run of 4K warming idealized simulations. So here we show the improvement in the low cloud simulations globally. So this is from Calypso, and this is from the ADG1, the default scheme, and this is from new scheme. So you can clearly see in those stratocumulus regions, we see a significant improvement in low clouds. And so here like it's a bias for the default scheme ADG1, and here is a bias compared to Calypso from the new scheme. So you can clearly see this the strong underestimated region has been improved a lot, and this shows the difference between the two schemes, new plus ADG1. You can also see the improvement is over these regions. Like we further check the Taylor program, the Taylor diagram over the 5 SC to stratocumulus to cumulus, shallow cumulus transition region, and we show the ADG1 is blue dot, and then the new one is red one. And then if you just look at the low cloud fraction and shallow low cloud fraction and shallow cloud forcing, the 1 and 2, you can clearly see this one, the improvement from the blue to red, a significant improvement from the blue to red. So you can see, we see the significant improvement in the stratocumulus to cumulus transition region, and the cloud fraction increase can reach by 20 to 30%. So next we check some cross section from like this traditional or classical the transition region from stratocumulus to cumulus, and then the deep convection regions, and we choose two locations. So one close to the coast region, the stratocumulus region, and the other one is a little far away from the coast. It's a shallow cumulus region. So in both regions, we can see that the cloud blue, the red one, agrees better with the observations. This purple line, the red one agrees better with the purple line, and like in the shallow cumulus region, the red one shows significantly more cloud fraction. And then we also check the total moment of the vertical velocity, basically the close to scrutiny, and you can clearly see the total moment of the vertical velocity is significantly smaller in the stratocumulus region, even though it's close to here. But then we check the total water variance, the QT variance, and in both locations, the total water variance is smaller. I think that so here we try to explain why. I think one reason in the straight cumulus regions we produce a smaller W prime 3. So that means we produce a more stable, more symmetrical turbulence in the straight cumulus region. In the shorter cumulus region, I didn't show here, but we did see a larger W prime 2, the variance of the vertical velocity. I think that produced a more stronger convection in the shallow cumulus regions. And then for both locations, we show a smaller QT. The smaller QT, the QT variance, the total water variance, that can further lead to the smaller variance in cloud water. So that, in fact, reduce like some physical processes. I didn't show here because of the time of the limit. But I think what we found, so here this paper was published in JAMS this year, and I have a reference later. And then further, we did this kind of ongoing work. We examined the cloud feedback, which then this new scheme. So we use the 4K experiments minus the climatology one, and the one without the 4K. So I think the basic information we got here is the new scheme. So this is a new one. If you see, so new scheme produced smaller weak positive low cloud feedback. So basically, cloud fraction decreases. But with the new scheme, even though it produced a larger low cloud in the present day climate, but it produced weaker positive low cloud feedback. And then we examined the change in scrutiny of the vertical velocity, and what we found is the change. So in the warming climate, the scrutiny in fact increases. So that means the shallow convection increase in the warm climate. But then the increase, when we check the two cases, the increase is relatively smaller with the new scheme. I think with that, I come to the conclusion of my talks. So we implement a new unequal with the PDF closure to the club, and this significantly improve the stratocumulus to cumulus cloud regions cloud fraction by 20 to 30%. And so we produce a more symmetrical turbulence in stratocumulus regions and stronger turbulent transfer in shallow convection cumulus. And then it is the interaction which macrophysical scheme also play a role there. And we produce a weaker positive low cloud feedbacks, despite assuming the stronger low cloud fraction in the present day as we assuming less increase in scrutiny in the plus 4K experiments. I think that's all I have. Thank you.
Okay, so we actually have time for a question if there is one. Yeah. Yeah, if you can go to the mic.
That was very interesting. I have two quick questions. Easy. First one's easy. What additional costs does this new PDF cost? And two, the transition from the stratocumulus off the coast of California to shallow convection as you progress towards Hawaii. In CAM, that transition happens because the ZM scheme starts developing cumulus clouds and interfering with the stratocumulus. So I'd be curious to see how ZM scheme is changing in that shallow convection region with your new PDF closure. That is, yeah, the impact of this new closure on ZM.
Okay, thank you for your questions. I think for first one, the cost is really, I would say, it's negligible because basically we just added a bunch of the formulas to replace the original formulas in the default scheme for the readers of the PDF. So the cost is negligible for the first question. And the second one, I think in the region we are choosing is basically here. Most of these are still controlled by the cloud scheme. So basically, in our paper, in fact we show the vertical profile from the coastal region to the deeper ocean, deeper tropical region. But I think the two profiles we show here are mainly from the cloud scheme, and not. I think it didn't. Those regions. The rule of the ZM scheme is still small, I believe, and Right, in the manuscript, we show the vertical, the zonal distribution, and it also clearly show at least as these regions have not been affected by the ZM yet. But I think what you raised is a really good question. Yes. So how you are interested to see how with the new scheme how this might interact with the ZM scheme. We have not come to that one yet. Thank you for your questions.
Yeah, especially as you go further down that transect, the ZM schemes can be more important.
Exactly.
Yeah,
Yeah, exactly.
I take your point that that might be too close to the stratocumulus region that ZM's not very active.
Right,
Yes.
so I think we need to move on to the next speaker. So Kyle, if you could come up. So our next speaker is Kyle Nardi, who's going to speak a little bit more about continuing the discussion on club.
Awesome. Sounds good. Thanks. All right, so thanks very much for having me. So I'm going to give a summary of some of my ongoing PhD work that's funded by the Momentum Flux CPT. And the main goal of my work is to identify a handful of tunable input parameters in club that we could potentially target to improve some regional and global biases in CAM6. So I have there club X. And what I mean by X is that I'm running club with prognostic momentum flux and also a regime-specific formulation for the dissipation of turbulent eddies. So this is a summary of the prognostic momentum flux formulation within club. So there are several terms here. I'll go through it quickly. So there are some advection terms. We have turbulent production terms, buoyant production terms, and also this return to isotropy adjustment term, which we'll talk about in a little bit. And what I really want to point out here is that there are several tunable parameters within this equation that we could potentially address to maybe change some aspects of the turbulence profile, and that could then have effects on some aspects of the global climate. And I'll also mention here that tau itself, so tau is the eddy turnover time scale. It's proportional to the turbulent length scale. And that in itself is tunable with this regime-specific formulation for eddy dissipation. I won't go into details about that, but if you have more questions about that, I'd be happy to talk about that offline. So experimental version of CAM6 with ClubX was run over a 10-year simulation, free-running simulation with baseline parameter settings. And there are several biases that were found. So first is the surface stress bias. So the reds over the Southern Ocean imply that there's a high bias in surface wind stress for the simulation with the baseline parameter settings in ClubX. And there's also a bias in shortwave cloud forcing, notably off the coast of South America. These blues imply that we have too low of a shortwave cloud forcing, so too high magnitude of negative shortwave cloud forcing. So that's a result of having too much low cloud fraction in this region. And for the purposes of this talk, I'm going to focus on the surface stress bias, but I also have results for the shortwave cloud forcing bias. And if you're interested in those results, I could chat about that afterwards. So the question is, how do we identify certain club input parameters that could be influential for addressing some of these biases? And the issue is that club has many tunable parameters that could be adjusted. So I showed a few in the previous slide, but there are certainly others that we could target. So then we're trying to find a way that we can efficiently screen a large number of these input parameters and find a handful of these input parameters that do merit additional analysis. So to do this, we run a sensitivity analysis called the Morris one-at-a-time method. And the way it works is we start with a set of tunable input parameters in ClubX, and then we run the model multiple times, each time with the unique combination of input parameter values. And from one run to the next, we're changing the value of only one input parameter, and we're keeping everything else constant. And what that allows us to do is to analyze the difference in model output between consecutive model runs, knowing that the only difference between those model runs is the value of that one particular input parameter. And we can actually do this multiple times, each time with a new baseline set of input parameter values. And what that allows us to do is to get a sense of the variability in the input parameters influence on the output based on the values of the other input parameters in the background. So we do this for 17 input parameters. Most of them are in club. We also do have a few that are in the microphysics scheme. But with the 10 different initial combinations, this results in 180 unique configurations per Morris sensitivity analysis. So we do this with short-term initialized hindcasts run at 1 degree horizontal resolution with 58 vertical levels, and we're running for 72 hours. And PBL turbulence is parameterized using Club X. And we're initializing atmosphere with ERA 5, ocean and sea ice with NOAA data, and then also we're using ERA 5 to initialize and spin up the land. And this is using BetaCast, which is created by my advisor, Colin Zarzicki, and there's a GitHub link here if you're interested in using it. And so we have 180 configurations with this sensitivity analysis per initialization. We actually initialize with 4 different sets of initial conditions. So we essentially have 4 runs of each of the 180 configurations. That's 720 configurations in total. And then for each of the 180 configurations, we average the output from that configuration over the 4 different initializations. And we can average it over a region or over the globe and then run sensitivity analysis on those averaged metrics. And we're calculating sensitivities at 72 hours. This is a very short-term simulation, but this is similar to the methodology used in Sean et al. 2018. And what they found was a lot of the sensitivities they found at 72 hours translated to the sensitivities that they found for longer-term simulations. So this allows us to run for a shorter period of time and allows us to run more simulations at less computational cost. So these are some of the sensitivity results. So here what I'm showing is mu star. So mu star is the average magnitude of the response of the output. I have several outputs shown on the horizontal axis, and each of the input parameters is shown on the vertical axis. And this is averaged over the Southern Ocean. So the column here for tau surface, which is surface wind stress in this case, so this shows all of the parameters ranked by their influence. So the darker colors imply that that input parameter had a higher average effect on the surface wind stress. So I highlight 2 input parameters here. The first is C inverse tau shear. So C inverse tau shear is a coefficient within this regime-specific formulation for turbulent eddy dissipation. So this is going to affect tau, the eddy turnover time scale. So this is going to have an influence on the magnitude of the return to isotropy term in the momentum flux budget. And then also CU shear is shown here. This is in the essentially a check on the turbulent production of momentum flux. So when we increase this input parameter, we're going to get a reduction in the turbulent production of momentum flux from updrafts and downdrafts. So what this is showing here is the sign of the response. We want to find input parameters that have a consistent directional response. So this is the probability that increasing the input parameter is going to increase the output. So blues here imply that when we increase C inverse tau shear, we are frequently getting a decrease in surface wind stress. So over the 10 different initialized background states, 9 of those 10 produce a decrease in surface wind stress. And then CU shear, we have a similar story where we increase CU shear, we're getting a consistent decrease in surface wind stress. And I'll go into a little bit of the physical mechanisms that could be at play here. So with the 4 sets of initializations for the 180 configurations, there are actually 40 different instances where we are increasing C inverse tau shear and keeping all else constant. So I look at all 40 configurations before we increase C inverse tau shear and after we increase C inverse tau shear. So the red profile here is the median profile before we increase C inverse tau shear, and the green is the median profile after we increase C inverse tau shear. And then the shading here represents the 25th to 75th percentile of the output at that particular level. So this first plot here is tau ZM, so this is the eddy turnover time scale, so again, it's proportional to the turbulent length scale. So when we increase C inverse tau shear, we're actually getting an increase in the dissipation of turbulent eddies. So we're breaking up the larger turbulent eddies into smaller turbulent eddies in the presence of high vertical wind shear, which is what we'd expect in the southern storm track over the Southern Ocean. So these greens here, we see that we get a decrease in the eddy turnover time scale. So that translates then to an increase in the inverse of the eddy turnover time scale, which is shown here in the profile of pressure term 1, which is this return to isotropy term. So because tau is decreasing, when we increase C inverse tau shear, we're getting an increase in inverse tau. We're getting an increase in this pressure term 1. So we're actually getting more of a damping of the time tendency of momentum flux, which is what we see here. So especially above about 100, 200 meters, we are getting a subtle decrease in the magnitude of vertical momentum flux. And that has an influence then on the profile of wind speed. So what we're seeing here is actually with a decrease in vertical momentum flux, we're getting an increase in the vertical wind shear. We're getting stronger winds aloft, weaker winds close to the surface. And what we're thinking is happening here is with less vertical momentum flux, we're getting less efficient mixing of stronger winds aloft down towards the surface. That's having an influence on the surface, or near surface wind speeds. So when we look at a global perspective, so this is U-bot. So U-bot here is calculated as the surface wind speed at the lowest model level. And this is at all grid cells. So the blues here imply that when we increase the inverse tau shear, we're getting a decrease in surface wind speed, or near surface wind speed, at that particular location. So from a globally average perspective, we do get a decrease in U-bot in this case. And we look at a zonally average perspective, we can see that at every latitude, we're getting a decrease in the wind speed at the lowest model level, and that's especially pronounced over the southern storm track. So now we see that this has an influence then on surface wind stress. So tau here is surface wind stress, and that's related to the low-level wind speed. So if we're getting a decrease in U-bot, we would expect to get a decrease in surface wind stress as well, which is what we see. So from a globally average perspective, we do get a decrease in the surface wind stress, and it's especially pronounced over the southern storm track. Now I'll note here, we're only using 4 different initializations, so we're only sampling 4 different synoptic states. So you can kind of get a sense of, we're probably seeing some individual extratropical cyclones in this case. But overall, we are getting a pretty consistent decrease in surface wind stress, which was predicted by the sensitivity analysis. So with the last couple of seconds I have here, I also just wanted to give a sample of something else we're looking at. So I've been showing just single outputs and the sensitivities for single outputs. But we also want to ask the question, can we potentially look at multiple outputs at one time? So I have a similar plot here where I'm actually looking at linear combinations of multiple globally average output metrics. For example, surface wind stress and shortwave cloud forcing. And we can see if we can sort of synthesize all of this information and find input parameters that influence a broad set of output metrics. And then this is sort of a Gleckler type plot that I've started to work with to get a sense of sort of the joint directional response. So if you're changing an input parameter, you're looking at 2 different output metrics, you could have 4 different outcomes for the sign of the change. So both could increase, one could decrease, both could decrease, and so on and so forth. So these sort of show some probabilities for the different outcomes. And what we're looking for here is a combination on the left of the darker colors, so the higher sensitivities, but also these black triangles would imply that there's a consistent joint directional response. So this is also just something that we're starting to look at. If anyone has any comments, I'd be happy to hear them. I'll also put my main takeaways here. And again, this was funded by the Momentum Flux CPT. I have some previous work doing this analysis of tropical cyclones. If you're interested in checking that out, you can look at this citation. And yeah, I don't know if there's any time for questions, but if there are, I'd be happy to take them.
So we do have time if there's one question. Yep.
Nice work. I just, you may have said it, and I apologize if I missed it, but how did you decide what range you vary the parameters over, and and what defines a tunable parameter?
Yes, that's a good question. So to be quite frank, a lot of this was done in consultation with Vince Larson, who developed Club. So he provided a lot of great guidance. So we had some sense of, so the one challenge with some of these tunable parameters is we actually don't know what the physical bounds should be. So that's added a little bit of a challenge. So some of it is practical. So we found that if we sort of have too much of a bound, or too much of a range, we actually do get some instability issues. So that's required us to sort of narrow the range for some of these terms. But a lot of it is just gut sense of what we think would work. But that's the one challenge, is we don't really have a good sense of what the upper and lower bounds should be for a lot of these club terms, especially some of these experimental terms. So some of it is some trial and error for sure.
All right, so thanks, Kyle. I think we'll move on to our last speaker, which is Yang Tian, who is going to talk a little bit about vertical shear.
Sounds good. Good morning, everyone. My name is Yang Tian. So how to go back? I am a scientist at AMP CGD. And as you can see from the title of my talk, This is going to be a slightly different talk from most other talks in this session because I'm not going to talk a lot about the club EDMF or things related, but instead I am using a much finer resolution model that is cloud resolving model to understand a certain process in the atmosphere with the hope that we can use this improved understanding to better represent this process in a convective parameterization scheme such as club EDMF or other schemes. We know that wind shear wind shear plays an important role in organizing convection, as in mesoscale convective system, and MCS systems, they are important features in transporting heat, moisture, momentum, and also strongly influencing the precipitation distribution across the globe. Because of their importance, we want to include some impacts of the MCS systems in the climate model in some way. And there have been some past efforts in incorporating mesoscale parameterization in global climate models. One of the most recent work is by our own colleague, Mitch Moncrief, in 2017, in which they proposed a multi-scale coherent structure parameterization. Essentially what this scheme does is to treat this MCS as a slantwise layer, overturning structure. Overturning structure. And what's special about this structure is that it has a very distinct convective heating pattern with a stratiform warming in the upper troposphere and cooling in the lower troposphere, which essentially resembles a second baroclinic mode of convective heating. What this scheme really does is that on the top of a traditional convective heating profile from the ZM deep convection scheme, it adds an additional convective heating from this MCS system. In order to kick off this additional convective heating, it depends on a few different factors. One of the factors is a wind shear threshold. Once the wind shear exceeds a certain threshold, then this convective heating, additional convective heating will kick off. Okay, but in the current treatment, it uses a pretty arbitrary wind shear threshold, and also we don't know the underlying mechanisms or processes regarding the relationship between wind shear and the convective organization. Therefore, the purpose of our work is really to get an ensemble convective responses in a less storm-like and more realistic environment, because most existing literatures regarding this relationship are mostly focused on a single scoreline case or idealized warm bubble experiments. In order to implement that into a convection scheme or global model, we want it to be more realistic. And we hope to inform a physically based relationship to be used in climate models. All right. So I am using a cloud resolving model, SAM, to simulate the cumulus cloud field. And we first run this model to a radiative convective equilibrium state. After it reaches the equilibrium state, we will create 20 ensemble members with different wind profiles. And each ensemble member will be run for 3 hours to sample sufficient convective responses to the imposed wind shear profile. I'm using a horizontal resolution of 500 meter and temporal resolution of 10 seconds to do the simulation. Okay, because there are a lot of different wind profiles. We experimented with many of them. So here is just a few. We have experimented with so this control run is no shear, and we've experimented with second baroclinic mode, a single mode, where half the magnitude, double the magnitude, were impose a linear wind shear profile. So the figure to the right just shows the surface precipitation response to those listed wind profiles. And this blue curve here shows the result from the control run with no shear at all. there are two interesting findings from here. One finding is that regardless of the shape or magnitude of wind we impose, we always see a reduction of surface precipitation in about half an hour to 1 hour of the simulation. The second observation is that after about an hour, there will be a gradual pickup of surface precipitation in response to the wind shear. And the strongest response that we can see is actually from this linear wind shear case. Okay. To give you a much better sense of what the wind shear does to the cumulus ensemble field, I just created some animations, but I hope it works. Okay, so this is a control run simulation, and what you can see, the bottom and the top and the bottom, they are actually the same figure, but it's just with different, is there a way to stop this? Okay, so what you can see is actually, okay, and word. Oh, okay, I know that there is gonna be some issues, but anyway, so this is the cumulus ensemble field from the linear wind shear, similar to the control field, but you can actually see like the shear is going to shearing off the top of the clouds, and then it forms more like an MCS type convection. And we can also see from the surface variable latent heat flux that it is more aligned along an arc or just like a straight line instead of a more circular shape when compared to the control run simulation. And also for the linear shear scenario, we found that 15 out of 20 ensemble members display a sort of convective organization compared to 10 out of 20 in the control simulation. Okay. As we noticed earlier that we found a very strong convective response to the linear wind shear profile. Therefore, we decided to look a little bit more in details into this particular shape of wind profile. In total, we actually look into 12 profiles, including a control wind profile with no shear at all, and another control run, but with surface wind speed at -5 meters per second. And I've also used 10 different linear shears with various magnitudes, but we decided to start at above 2 kilometers because most existing literatures, it claimed that the bottom low-level shear is important because of the interaction between shear and the cold pool. Therefore, we're curious to see what happens if we actually elevated this wind shear and see if we can actually see some convective responses to this wind shear. Okay, and the figure to the right shows the surface precipitation responses to those 12 different profiles again. What we see is that there is still like a reduction in the surface precipitation in about half an hour into the simulation. And then after about an hour, there will be a gradual pickup of surface precipitation. There are a lot of curves, I'm sorry, but I just want to draw your attention to a particular line that is this black curve, which corresponds to linear shear profile 6. So this linear wind shear is neither the maximum nor the minimum wind shear among all of those different shear cases, but you can actually see a minimum surface precipitation response in this linear shear profile. If we look at the surface sensible heat flux and latent heat flux responses, and if we observe like the linear 6 case, this also exhibits like a minimum surface sensible heat flux as well as the latent heat flux responses. Okay, if this is still not obvious enough, I will show you some other convective responses. So what I show here are the convective heating, apparent moisture sink, and surface enthalpy fluxes. So again, if we focus on this linear 6 case, we can see that first, there is actually a big jump from linear 6 to linear 7 in the cumulus heating profile. And then there is also a shift in the convective heating from a slightly more top-heavy to bottom-heavy for this case. Similarly, if we go from the moisture sink, there is a jump here, as well as a slight jump from linear 6 to linear 7 in this enthalpy flux case. Okay, and this will be more obvious, I hope. Here I plotted the mean precipitation, the minimum and the maximum precipitation to the different wind shear profiles. And we can see that like this case is actually linear 6. It has a shear at the magnitude of 1.5 times 10 to the third per second. So we can see actually a non-monotonic behavior with the imposed linear wind shear profiles. Below this value, the mean precipitation decreases as the shear magnitude increases. But above this value, the mean precipitation actually increases as the wind shear increases. So this non-monotonic behavior is really interesting, and we do have some scientific questions because of those explorations. The first is trying to understand why is surface precipitation suppression in the first hour of simulation. And the second or the third, they're related to this non-monotonic behavior and what determines the critical wind shear value. For the sake of time, I will only very briefly, okay, yeah, so this is not actually the most updated slides. Sorry. How do I go back? Okay.
Which slide would you like to go to? Okay, you can go backwards and forwards now.
Okay, yeah, that's fine. So we have some hypotheses regarding the first suppression of precipitation in the hour that is related to like a pressure drag. When we perturb the surface, when we were the lower atmosphere, there is going to be like a pressure drag formation, and then it's going to decrease the vertical momentum flux transport and reduce the vertical development of convective cells. Therefore, there will be more formation of shallow cloud population and reduction in the deep population, which actually is shown here. So you can actually see like an increase in the shallow cloud population once we impose any surface or above the surface wind shear. And we're so regarding this non-monotonic behavior, we look into the momentum budget. So when we compare the case of control 5 and linear 6, we can see that the linear 6, the forces in the momentum budget of linear 6 case, they strike a very good balance of those different terms. So I have the perturbation pressure terms, buoyancy-induced perturbation pressure, mechanical pressure and buoyancy, and total acceleration. So comparing those two figures, you can see that for the linear 6 case, the forces in the vertical momentum budget actually strikes a very good balance. Therefore, you don't have that much acceleration going on for the convection to go deeper and produce like large precipitation. Okay, so this is like the take-home message. Sorry, the slides are like the slides are not the most updated slides. So yeah, I hope you get a sense of what I try to convey today. Thank you so much.
Okay, we do have time if there is one question. Yeah, Julio.
That is a very good question. I think the reason why we don't think it is rain evaporation is because of the very short response time. Because we can see that like from the very beginning, so after about like a few minutes or 10 minutes, the surface precipitation starts to decrease. And we don't think like the rain actually, it takes a little bit time for the rain and the rain evaporation to take effect on this reduced surface precipitation. And we think maybe pressure drag is more relevant because the response of pressure is immediate compared to like a gradual development of thermal or convection or rain evaporation. Yeah.
Okay. Does that answer? You have follow-up? Okay.
Okay. Yeah. Thank you so much.
Right. Thanks, Yang. So we'll have a break now, and then we'll come back here at 10:30. So everybody will be coffeeed up, so we'll be ready to go.
a talk on marine cloud brightening from Haruki Hirasawa, and I think we should just go ahead and get started.
Haruki. I'm a postdoc at the University of Victoria in Victoria, Canada. So I'll be talking today about some marine cloud brightening simulations that we've done in CSM2 and E3SM in collaboration with some colleagues at the Pacific Northwest National Laboratory and University of Washington, and in particular, Ming-Shuang Wu, who led a lot of the E3SM work, and Phil Resch, who's sort of the brains of the operation. So this work was done with the support of Silver Lining, as well as using computational resources from Amazon Web Services. Okay, so marine cloud brightening. So MCB is a proposed solar radiation management or solar geoengineering technique wherein sea salt aerosol would be injected into low clouds with the goal of increasing the cloud droplet number concentration within the clouds, and thereby increasing their albedo and lifetime, and then thus causing local surface cooling with the aim of causing enough cooling to reduce the impacts of greenhouse gas warming or mask it to some degree. So there are obviously many different uncertainties associated with MCB, many outstanding scientific questions, in large part because we're dealing with aerosol cloud interactions and in the troposphere. And so there's a lot of different modeling efforts that go into trying to understand MCB, ranging from small scale aerosol work to, of course, there's quite a lot of LES work in MCB. In our case here, we're using GCMs, and so obviously, these are coarse resolution simulations, and they rely a lot on the parameterizations of the aerosols and the cloud processes. But we can still learn quite a lot from them. So we can use these GCMs to assess large-scale cloud responses to aerosol injections, as well as the radiative and carbon cycle feedbacks. And so, MCB, the forcing itself will likely differ quite a bit from greenhouse gas forcing, and we know that the pattern of temperature response to a forcing plays a pretty substantial role in the radiative feedback, for example. And then, of course, we can use the GCMs to get an idea for how the local as well as remote climate, regional climates might change as a result of MCB interventions. So when we test MCB in GCMs, there's sort of two main methods. So the first is a relatively idealized method where we would prescribe or increase the cloud droplet number concentration within low clouds directly. And so we would simply just intervene in the parameterizations and increase or set or prescribe CDNC values in the clouds. The second is still, I guess, pretty idealized, but a little bit less so, where we simply add sea salt emissions to at the surface into the boundary layer. And in particular, we would focus on adding accumulation mode aerosols, which are thought to have the largest brightening effect on clouds. So we've conducted simulations in, again, CSM2 and E3SM version 1. And so we started off running some fixed SST simulations to estimate the effective radiative forcing of applying MCB in 3 regions, which I've highlighted on the right. We're calling it the Northeast Pacific, Southeast Pacific, and Southeast Atlantic. And so these are regions that have been identified as having extensive stratocumulus cloud decks that are thought to be sensitive to aerosol perturbations. And so we vary the magnitude of our MCB perturbations in order to identify a certain perturbation value that gives us a target forcing of negative 1.8 watts per meter squared. And so I'm showing here in a table the different testing ranges for CDNC and sea salt emissions. And yes, I know that some of these values are quite extreme, especially for the CDNC. Okay, so once we've identified the CDNC and sea salt emission perturbations that give us the target forcing, we then apply these perturbations within a set of coupled simulations with a background of SSP2/5, which is standard now in the geoengineering literature. And we simply start the forcing in 2015 and continue it for 50 years. And this is what's called a G4-like simulation. And so we test the effect of forcing in all three regions together and then separately to see the role of the difference in the forcing pattern on the climate impact. So you can get a little bit of a sense for this here on the right, where I'm showing the global mean surface temperature anomalies due to the different simulations. And so in solid blue is the effective forcing in all three regions together in CSM2. And then you can see that for the slightly lighter, the dashed dotted lines, most of this cooling is because of forcing in the Southeast Pacific and less of it, and with lesser contributions from the other two regions. Okay, so there have been several different other looks at MCB in GCMs in the past. And so our protocol differs first in the sense that we're trying to do a multi-model comparison of climate impacts in specific regions that are thought to have higher cloud sensitivity to MCB. So this differs from the GeoMIP simulations where the forcing is more global. And then we also specify the strength of the MCB based on the resulting effective radiative forcing rather than any specific cloud droplet number or sea salt emission level. And so the idea here is that we want to be able to separate the forcing uncertainty from the uncertainty in the teleconnections, the large scale circulation response. And of course, this is one of the newer assessments in the CMIP6 models. Okay, so these are some results from our fixed SST simulations. So I'm showing the top of atmosphere shortwave and longwave anomalies for different sea salt emission and CDNC perturbation values. And this is averaged in the Southeast Pacific region. And on the x-axis, I'm showing the vertically integrated cloud droplet number concentration that we get from the simulations. And so the first thing to note is that the aerosol cloud interaction is more sensitive in CSM2 than E3SM. This is, tracks with other analyses of the sulfate aerosol forcing, for example. And another thing we notice here is that for a given level of CDNC, the sea salt emission simulations are giving us more forcing than the CDNC simulations. And so this is in large part because, when we're actually using sea salt aerosols, we're including a direct aerosol forcing. And so here I've added a couple lines in the X's in both panels. I'm showing the cloud radiative anomalies, and then in the triangles I'm showing the clear sky radiative anomalies. And so we can see a couple things here. One interesting thing is that as we go to extremely high sea salt emission rates, so over 100 teragrams per year globally, we actually start seeing that the aerosol cloud interaction is becoming less effective and in fact inverting its sign. And so as we add more sea salt aerosols, we're actually causing a positive forcing in the ACI. But because as we increase sea salt aerosol forcing, we're also increasing the direct aerosol forcing. This direct aerosol forcing actually, to a large extent, compensates for this reduction in the effectiveness of ACI. And so this sort of, corresponds with similar work in GeoMIP, for example. So again, so we identified a we took a look at the radiative forcing from those fixed SST simulations, and we chose a forcing level that achieved the 1.8 watt per meter squared cooling negative ERF effect. And when we impose that in the coupled models, what we find is we get a La Nina-like cooling pattern in both models. But we do see that even though the global mean surface temperature effect is around 1 Kelvin in both models, the pattern of the response to MCB is, pretty different. And so to the point where in some regions, we're getting opposite signed responses, despite the fact that we're getting we're applying similar forcings, for example, over the continental US, where CSM2 is saying that we'll get a warming due to MCB in these three regions, while E3SM is saying we'll get a cooling. And so a lot of this is because of uncertainties in the responses to the different regions. And so I'm just going to highlight here the effect of forcing in the Southeast Atlantic, where we get an Atlantic Nina-like response. But in the CSM2, we're getting warming in the Northern Hemisphere, while E3SM is giving more cooling. Okay, so just to conclude, CSM2 is, again, more sensitive in both sea salt emissions and CDMC than E3SM. And as we go to excessive sea salt emission rates, we're reducing the aerosol cloud interaction efficacy. And that means that there's a substantial role for the direct aerosol forcing at these high emission rates. And we do see some differences in the large scale responses between the two models, even though, of course, they are relatively similar in a lot of ways. So yeah, thank you.
We actually have a lot of time for questions, so
Talking to this one?
I think so.
Haruki, can you hear me?
Yes, I can.
This is Nikki Lewandowski. Thank you for sharing your output for from these simulations for marine biogeochemistry. I appreciate it.
No worries.
Why do you think CSM2 is so much more sensitive, and what does that mean for understanding of, for example, how volcanic eruptions might influence the sensitivity of the climate to, or how sensitive the climate simulations are to volcanic eruptions?
Yeah, well, I guess there's probably some people in the room who could answer this better than me, but I guess one thing to note is that if we take a look at some of the where the aerosol cloud interaction in CSM2 and E3SM are coming from, we're seeing a much stronger second indirect effect. So this means that aerosols are increasing the cloud liquid water path and the cloud amounts much more than in E3SM. And so this comes down to some choices in the parameterizations. And so, right, so yeah, this does have an effect, I think for, of course, tropospheric volcanic eruptions, these sulfate aerosols, I know there's some papers that look at the effect, using these volcanic eruptions as sort of observational constraints on aerosol forcing, and so yeah, obviously these differences in the parameterizations plays a big role in the resulting air forcing that you get from the volcanoes.
Are there other questions? Okay, well, I think if there are no other questions, thank you very much for the talk. And our next presenter is Margaret Duffy. Well,
all right, cool. Okay, hi. So I'm Margaret Duffy. I'm a postdoc in AMP at NCAR, and I'm going to be telling you about the sensitivity of cloud feedbacks to parameters in CAM6. And this is work that I've done with Brian Medeiros, Andrew Gettleman, and Truda Eidhammer. So the motivation for studying cloud feedbacks is their relationship to the climate sensitivity, which is a measure of the amount of warming per doubling of CO2 in the atmosphere. And so what I have on the slide here, does this work? Oh yeah, okay. The x-axis is the time that the science was done, and the y-axis shows the range of climate sensitivity estimates. And then we can see that from 1979 to present, the climate sensitivity has been very stubborn and hard to constrain. We've made some recent progress by combining multiple lines of evidence for the AR6 assessment, but still the likely range of 2.5 to 4 degrees is obviously like a pretty impactful difference, right? 2.5 degrees of warming is pretty different from 4 degrees of warming per doubling, so further constraining this is a priority. The relationship now between this ECS and the cloud feedbacks that I mentioned can be visualized using this kind of forcing feedback framework, which I'm sure is familiar to many of you. But we can see that there's just an inverse relationship between the climate sensitivity or our temperature response and the feedback lambda. And those feedbacks include both cloud and non-cloud components. Okay, so focusing in on that lambda term that I mentioned, the total lambda is over here on the right. Yes, far right, and then second from right is the cloud contribution to that total feedback. And focusing on the error bars, we can see that across the various lines of assessment, the different colors are the different lines of assessment, cloud feedbacks are consistently contributing the most uncertainty to the total feedback. So that is why we're so interested in the cloud feedback. Now moving into model world, we can take a look on the far now left here of what's been going on in the CMIP model. So while the AR6 assessment was narrowing our range of climate sensitivity, the CMIP models was actually widening the range of climate sensitivity. So the previous generation in blue is CMIP 5 to the most recent generation in orange is CMIP 6, and we can see that there's a much larger spread, especially on the high end, with an increase in the mean climate sensitivity. And so obviously our community is very concerned, what if these climate sensitivity values that are very large are real? And I've added stars to this very familiar figure showing where the NCAR model sits. And so we can see that going from CCSM 4, 2 generations ago, to CESM 1, the previous generation, to CESM 2, the current generation, the climate sensitivity has gone up quite a bit in the NCAR specific model. And then we can also see, looking at this decomposition, that the cloud feedback is playing a very, very, very large role in that increase in ECS, specifically in the NCAR model. Okay, so what am I doing to address this? Well, I'm looking at the role of those cloud feedbacks in the NCAR model to parameters. This is a schematic just showing basically the processes that we're interested in. These are processes that relate to clouds, and we are perturbing parameters related to cloud processes in the NCAR model and looking at their impact on climate sensitivity. This is done using a perturbed parameter ensemble, which we introduced in a session yesterday. And so we're varying 45 atmospheric parameters across convection, turbulence, microphysics, and aerosol schemes. Here's a little bit more information about this perturbed parameter ensemble that we're using to evaluate the sensitivity of cloud feedbacks to parameters. It's a 262 member ensemble, and the difference between each member is in the 45 atmospheric parameters that I mentioned, each of which relates to cloud processes. These are 3-year-long simulations with fixed SST, and for each of these 262 simulations, we have 2 experiments, a present day and then a uniform 4K warming, and we're looking at the feedback in the difference between the 4K warming and the present day. I think we had a question in the previous session about ranges of parameters, and so I wanted to address that here. The range of the 45 parameters is set by expert assessment, and it's intended to be realistic. But because all the parameters are varying in conjunction with one another, and because there's some subjectivity that goes into that, you can imagine that some of our 206 ensemble members have an unrealistic looking climate. And so to deal with that, we have eliminated about 50 or so simulations based on the top of atmosphere radiative imbalance. That's these lines. So the ones that are very far out of balance are eliminated to make sure that we're looking at realistic looking climates for our analysis. Okay, that's been a lot of methods. Let's get into some results. The PBE simulations are shown in blue. Each dot is one of our 206 simulations. For the total feedback on the top and the total cloud feedback on the top and the total feedback on the bottom. And I've compared this just to the CMIP 6 models in yellow, and we can see that we're getting a very comparable spread. I'm going to focus mostly on the cloud feedback. We're seeing that we're getting a very comparable spread just by changing the parameters alone in one model, that's in blue, to the full CMIP 6 ensemble in yellow. Okay, so some questions that I have about this. I won't talk about all of these today. I'll just talk about 1 and 2. Why is the cloud feedback so much lower in the PPE default simulation? That's this black circle. Than in CESM2, that's this black square. This was sort of one of these unexpected turns that our research took. We weren't necessarily expecting a lower cloud feedback in the PPE default simulation than in CESM, the contribution to CMIP. So that was a surprise, and I'll talk about that. And then we also wanted to know whether it was a coincidence that these things had the same spread, or whether there's kind of similar underlying mechanisms. And then I have 2 more questions, 3 and 4, that I won't address today, but that I have thought about and that you are welcome to ask me about if you're interested. Okay. Okay, so first, why was our PPE default simulation so much lower than the CMIP6 simulation? That's the black star. What's up with this difference? This is a pretty impactful difference. This is a lower cloud feedback, which would correspond to a much lower climate sensitivity. And so we were really curious about what was going on. Why does our PPE default simulation suddenly not really have a high climate sensitivity? And so there, we did a little deep dive into this, and our answer is twofold, 2-part answer. We went through all of the difference between the CESM to contribution to CMIP and the CAM6 PPE default simulation, and looked at what was causing the decrease in the cloud feedback. And one of them was coupling. So if I have the AMIP models on here, and the CESM contribution to AMIP in the black square, and we can see that roughly half the difference, half of this decrease, is due to the role of coupling. That didn't entirely surprise us, right? In our atmosphere-only simulations, that are the PPE are atmosphere-only simulations, and so those can't fully represent the pattern effect and state-dependent cloud feedbacks. And we know that CESM has a large pattern effect. So that one didn't surprise us, but what did surprise us is that there's an additional decrease just with the different generation of CAM that was used for the PPE as compared to CMIP6. So CMIP6, CESM2 uses CAM 6.0. That's here for the atmosphere only, the triangle. And then for the PPE, we ended up using CAM 6.3, that's the circle, and there's a pretty big decrease just through these kind of run-of-the-mill changes that happened going from CAM 6.0 to CAM 6.3. And we haven't further investigated what happened. Maybe some of you in this room might have some hypotheses as to why there's a lower cloud feedback in CAM 6.3 than CAM 6.0. And then, okay, I'll kind of tease you with that and move on to the second question, which was like about that spread that we saw that was comparable, very comparable between the parameters and the CMIP6 ensemble. And so in order to kind of figure out what was going on there, is it a coincidence, is it not? I took a look at the processes setting the cloud feedback. So cloud feedbacks can be decomposed into shortwave and longwave contributions. I did that. And they can also be decomposed into these 6 assessed components from the Sherwood et al. Or WCRP assessment here. So I will start with just the shortwave and the longwave. Here's this figure now with shortwave and longwave contribution. So here's our total cloud feedback in CMIP6 in yellow and in the PPE in blue. And we can see that the partitioning of the total cloud feedback into its shortwave and longwave contributions have very similar spreads across the PPE and CMIP6 models. So we cannot call this a coincidence yet. This sort of similar spread is holding up across this decomposition. What about this more elaborate decomposition? And what I'm showing here is the total feedback on the bottom, and then, this isn't very precise, this pointer. And then the 6 components on the top. So yellow is again the CMIP models, blue is again the PPE. I've also included the Sherwood or WCRP assessed values in these little orange bars for reference, and the AMIT models are on there too. So what you can do is take a look at this figure and compare the spread in the blue and the yellow. And if those spreads are about the same, then that's telling us that the processes underlying those similar spreads across the CMIP6 and across the PPE are set by the same processes. And my interpretation of this is that yes, they are. The high latitude, low cloud optical depth feedback is a little bit different, but other than that, the spreads are pretty robust across these different contributions. And so it's interesting because this is kind of telling us like we can just hit one model and change parameters, or we can look at the whole structural uncertainty and we get very similar spreads both ways, which we weren't necessarily expecting. Okay, I'm skipping over this. I just wanted to let you know that I have thought about those questions and that you can chat with me about them. But here is my summary. So the two main questions that I addressed today is that we were surprised to see a lower cloud feedback in the PPE default simulation than in CESM2. And the reason for that was basically two-part. One was coupling, and then one was changes in the generation of CAM6, lowering the cloud feedback, and thus all else equal the ECS. And then we saw that we could basically recreate the spread in CMIP6 model cloud feedbacks in just CAM6 by tweaking parameters alone. And we wanted to know whether those kind of comparable spreads were coincidence or not, and we found that the mechanisms controlling the spreads across both ensembles were the same, and so we can't say that it's a coincidence at this point. I have these two other questions which I won't address, but you can read them, and if you want to come chat with me about the other questions, that would be great. So again, my name is Margaret Duffy. My email is on the slide, and thanks for listening. All right.
Thanks, Margaret. We have time for questions. Hey, Colin.
Yeah, very, very nice talk. I think my questions pertain to the second bullet point here. So the first kind of simple question would be that you actually you kind of set these ranges with expert judgment. Conceivably, they're physically plausible. Now, obviously, you could have a situation where you're on the high end of multiple ranges, and then the climate you get is not reasonable. But do any of those results, that spread, change if you include the simulations that you threw out? Does that spread kind of fan out? And then sort of tied to that question, do you know of any other, modeling initiatives like that confidence, I assume, could be improved if there were other centers doing similar PPE type experiments and seeing similar behaviors? Are you aware of anyone that's been doing that?
I think it would be really interesting to look at this in other PPE, but I don't know that that's been done specifically. I will point out, I think this issue about how to pick your parameter range is a really important one. And I won't exactly address your question directly, but I will say that something that gave me confidence that we were on the right track with what we did is that these are the three most highly correlated parameters with the cloud feedback. And we can see that even amongst the highly correlated parameters, they're not super highly correlated, which is, I think, actually a good thing. I think that that's telling us that there's not sort of one parameter that we're just tweaking way more than the others to artificially give us a super high correlation. And so the fact that there's like a pretty good scatter, I mean, you would expect that if you were tweaking 45 parameters kind of equivalently from one another. So this is something that gave me confidence that we were on the right track there. I think the ranges here do widen a little bit if you include the other 50-something simulations, but to be honest, it wasn't crazy sensitive to that, if I recall correctly.
Thank you.
Sure, thanks.
I have actually, I have a question about this slide.
Yeah.
Are we to interpret from this slide that the decrease in sensitivity that we see in CSM when you go from coupled to atmosphere only, is that not the case in other models?
That's the case in other models, but not to the same extent. So we have a relatively large pattern effect as compared to other models, and that's, I think, a big part of what's going on in this spread. If I'm understanding the decrease from CMIP to AMIP correctly. I mean, you can look at what's going on just by comparing the yellow dots to the green dots, and you can see that the AMIP models and the CMIP models are by and large in the same ballpark. But then for CESM2, it decreases quite a bit. And it's known that we have a kind of larger pattern effect. And then I think like Jenny Bjordal had the state-dependent cloud feedback, which is captured differently in CMIP than in AMIP. So that jump didn't actually surprise me based on what we already know about our model. It was the jump from generation that surprised me most.
I think we definitely have to look into that.
Yeah. Okay,
All right.
Thanks.
Thank you very much. So our next speaker
Okay, so this is a talk very similar to what Haruki just gave. And this is on MCB, and this is simulation done using CSM2. And very quickly, for solar climate interventions, the two most commonly researched strategies are either injecting sulfate aerosols into the stratosphere, SAI, or MCB. That's the focus of this talk. And MCB induces a cooling effect through mostly two indirect effects. First is the tuning effect. When you deploy cloud seeding, you reduce the cloud drop size, and the clouds become more reflective of solar radiation. The second one is the Albright effect. Due to the smaller cloud drops, clouds become more persistent because you reduce precipitation. And this is work I did with Phil Rash back in 08, 09. Back then, we used CESM3, which didn't really simulate cloud aerosol interaction because there's a one moment microphysics scheme. So we had to force the model to do what we wanted to do, and we call that a constrained approach. That's, you basically prescribe the cloud drop number concentration in the boundary layer in the designated cloud seeding regions. And the approach we took here is a bit different from Haruki alluded to. And we first seek out regions most susceptible to cloud seeding, and the strategy we took was to do two simulations. One, just plain baseline simulation. The other, you prescribe the cloud drop number concentration in the boundary layer cloud over the ocean everywhere to either 375 or 1,000 per cc. And then you compare the two simulations and pick out, you rank all the grid points based on the shorewave cloud forcing between the two simulations, and then you do a ranking, and the bottom panels are, how do I do this? So, wait. So here's the results back in 09. So assuming you're allowed to see over 20%, 30%, 40%, 70% of the ocean surface, and the color here is showing how many months you deploy seeding. 12 meaning you deploy seeding all year round. 0 meaning you never apply seeding. And the scenario built at the time is a doubling CO2 scenario. And the question posed is how much seeding you need to restore these four metrics. Surface temperature, for example, in order to restore surface temperature, global average surface temperature, you need to apply seeding over 50% of the ocean surface. That's gigantic. And for precipitation, you only need to see over 25% of the ocean surface. And we also look at sea ice in the northern hemisphere and southern hemisphere. The take-home message from this study is we couldn't find a seeding strategy to simultaneously restore all four metrics at once. So that's the message from this study. And this is a more recent study that I call an unconstrained approach. You just inject sea salt particles and see what happens. And so in this study, first of all, if you inject sea salt particles in the Aiken mode, meaning very, very small particles, this study actually found you induce a warming effect instead of cooling. And you only induce cooling if you inject sea salt particles in the accumulation mode. Second, while they increase the amount of injection of sea salt in mass, you can bump the cloud drop number concentration up to 450, and then you can't go any higher. So based on this study, also with personal communication with an expert in cloud microphysicists, Andrew Gettleman, the assumption we made back then in 08 or 09, 1,000 is probably not achievable, it's not totally unrealistic. So we have to avoid that in this round of the study. So instead, I go with 375 in the current study. This is a seeding mask built using CESM2 and based on SSP 245. And this is a 20-year average between 2015 to 2034. And I lay down the seeding mask based on month. And So there are like 4 levels, 2.5% of ocean surface, 5% being the blue, the green is 7.5% of the ocean surface, and then 12.5, the yellow. So you can see in the border winter, for example, in January, December, the regions most susceptible to seeding is mostly in the southern hemisphere. During the boreal summer, June, July, August, you see the regions shift to the northern hemisphere off the west coast of the United States. So the two factors regulating the most susceptible to seeding is, first is the solar inclination. Second is the low cloud distribution. If you see over regions where there's no cloud, you're not going to induce any cooling. So here's a comparison of the seeding mask. I pick out 20% seeding mask back then using CESM3 versus CESM2 results. As you can see now, the map look much smoother. I think it's because if my memory serves me correctly, back then I only did a 1-year simulation. That's why it's much noisier. Second, right now the seeding mass is more concentrated over the stratus-cumulus region. And here's just a calculation of how much cooling you would induce based on the same amount of cloud seeding. This is radiative forcing based on just plain simulation seeding everywhere over the ocean. Say if you are allowed to see over the top 20% of the grid points, now with CESM2, you're going to induce a net cooling of 7.5 watts per meter square. But back then, using CESM3, you were only producing 2.5 watts per meter square. We're looking at a threefold difference. The reason is on the panel on the right. This is taken from a study by Jen Kay. For low cloud biases in CAM4, you can see there's intense low cloud biases in the negative, we have a lot less low clouds compared with observations, and especially over stratus-cumulus regions. That's where we intend to apply seeding. And the panel on the right is CAM5. As you can see, the low cloud biases are highly corrected with all the updates in CAM5. And that explains why you're looking at a threefold difference in cooling between the two models. And now we need to build a scenario in order to mimic what ARISE SI has done. We try to build the same kind of scenario. So we assume solar climate intervention will be deployed starting in 2035, and it will run out to 2069. The target we set is the global average surface temperature during the last 20 years. There's a simulation that will be 2050 to 2069 would be restored back to the 2020 and 2039 level. So the first round, we try to see what this new model will do. So we try 4 different seeding schemes. The blue is seeding over 2.5 of the ocean surface, the red 5%, blue 7.5%, and the magenta 12.5. The black is the ensemble mean of the CESM2 simulations based on SSP 245. And the dashed lines are the average during the last 20 years. And the black dashed line is the average of the target. As you can see from this plot, seeding over 5% of the ocean surface is right on target. Then next, we proceed with the 10 ensemble simulations using the same seeding strategy. And I'll show you the global response in terms of surface temperature. And I'll just focus on the top panels. The panel on the left is the temperature difference between the MCB ensemble during the last 20 years, 2050 to 2069, and the basis is from the baseline simulation during the first 20 years, 2020 to 2039. The most intense cooling takes place where we apply seeding, so there's no surprise, but the cooling also extends to the tropical West Pacific. And this is a nonlinear-like kind of response. And the panel on the top panel on the right is basically the same thing, except the basis is from the baseline model between 2050 and 2069. Next, I'll show you the the precipitation response. As you can see, due to the temperature response, the cooling extends to the tropical west, and there's a strong reduction of precipitation over the warm pole. And you also see an increase of precipitation over maritime continent and over Australia. And it's no different. Either you use the basis from the baseline model between 2020 and 2039, or using the last 20-year average. And if you break that down with either convective precip in the metal panels or the stratiform precip, you will see actually convective precip is the more dominant factor in the total precip. So quickly, I'll summarize. In this study, we find seeding over 5% of the ocean surface is enough to restore the global surface temperature between 2050 to 2069 to the 2020 to 2039 level. And MCB induced the largest precipitation, also the temperature response, mostly in the tropics. And precipitation is reduced over the ocean, but it's increased over land, actually, mainly over Australia. And our next step is to move into building a controller like a RISE SAI, meaning you don't have a fixed seeding strategy throughout the simulation. So that will mimic a RISE SAI. The second is we're going to move into the unconstrained approach, meaning we need to go into inject CESL particles in the model. This will add a degree of uncertainty. It highly depends on how the model simulates aerosol-cloud interaction. And that's all I have today for you. I'm glad to take questions.
Thanks, Jack. Could you clarify for the ocean biogeochemist how your findings are different from Haruki's? If they are, they look very similar to me.
Yes. I think, yeah, I actually saw his results in our previous silver lining kind of meetings. I think it's good to know the induced response is so similar. And I should add, in this, I call optimal seeding strategy, meaning you look for regions most susceptible to cloud seeding. The advantage is that you can induce maximum cooling with the minimum effort of cloud seeding. The disadvantage is that you don't know what's causing what, because like I said, when you want to look at the regional response, you don't know what's causing what. So another thing we plan to do is try to repeat what he has done. And then for building this controller, I probably should put a spoiler what we try to do. From this plot, I come up with a very simple-minded kind of controller. As you can see, during maybe the first 5 years, I can deploy 2.5% cloud seeding, and then I start to ramp up seeding over the years. I will be able to maintain at that 2020 to 2039 level, right? This is I think this is not a very elegant way to build a controller. The second approach is to dissect the cloud seeding regions like Haruki showed. So study what seeding in each region would do, and then you build a controller based on that approach. So there's an advantage in his approach, meaning the fixed location kind of approach. And this gives us a kind of a different perspective. But it's good to know we actually ended up very similar response, because I see over where he's seated too. That's probably why we are looking at very similar results.
Question, maybe not a fair question for you, but this, that you're showing a La Nina-like response
Yeah.
from cloud seeding, and
Yeah.
La Nina-like, La Nina is associated with for example, with increased tropical cyclones in the Atlantic. Is there any consideration to, looking into those things?
Of oceanographers approached me, and then they took my simulation for analysis and say, Jack, your simulation shows ANSO is disrupted. Are you sure you're going to do that? So they're working on the paper now, and we're going to have regular meetings. So one thing we might want to do is move away our seeding from the Pacific Ocean. See if we can see over South Atlantic, for example, to get away from there, because without doing that, we didn't know. And I'm not an expert on ANSO. Unfortunately, we have people interested in this and then take a look and say, ANSO is pretty much gone in this simulation. So that's kind of an interesting finding, in my opinion.
Yeah, thank you.
Yeah.
We have, real quick, Roy. Oh.
For the excellent talk.
Yeah, well, we'll have to make it quick.
Yeah.
But
do you have plans to look into land use patterns relating to the changes in precipitation and how that will impact different communities across different continents?
Yeah, I think we are all, I'm pretty sure with very different models, we see this pattern. Like in the UK Met Office, they use a totally different seeding strategy. They also see the same thing. But we're just seeing at this point, we're just comparing our results. We haven't actually looked into what's the impact. I think I'm not really in that area. And that, we can bring in people who are experts in that to tell us what's the implication of this kind of precipitation difference. But what I'm showing here is actually confirmed by several different models. So we have pretty high confidence about these results.
thank you, Jack.
Thank you.
I think we're going to have to move on. It was an interesting discussion, but we're running late now. Our next talk is from Jonah Shaw, and I'm actually not sure. Oh, okay, great.
Okay, great. Hi, I'm Jonah. I'm a graduate student at CU, and I work with Professor Jen Kay. And today I'll be talking about a tool that I'm building for CSM2 and COSP for simulating spectral radiances for more kind of apples-to-apples model satellite comparisons. And this really wouldn't be possible without some tremendous guidance that I've gotten from Dustin Swales at NOAA. So when we think about model observation comparisons, I think we often think in one direction, which is that observations are used to constrain our models. But what I really want to focus on today is the fact that we can run our comparisons in the opposite direction and take climate model simulations and use them to really inform our observations and enhance what we can do with those observations. And to be more specific, I think it's useful to look at the most kind of recent US National Climate Assessment. And what we're seeing here is that in order to do attribution and detection of climate change, you need climate model simulations. And I think what we can see is that on the left, we're looking at surface temperature records and CMIT-5 simulations that have been run with both natural and kind of external forcings. And so our surface temperature records throughout this time period are consistent with the observations. But if we compare those same observations with these CMIT-5 simulations that are now kind of leaving out our carbon dioxide increases, our aerosol changes, they become inconsistent. And so this point around 1980 is when our surface temperature changes are attributable to climate change. And so really what the models are providing here is this broader context of forced change and internal variability that we're placing the observations in. And why do you think, attribution and detection is important? It's all about kind of action. So being able to make a statement where you say that this change is attributable to the human influence makes action much easier. Or even being able to kind of forecast in the future and say this change will become attributable. And so that's why doing these studies is important. But let's say, I'm interested in the Arctic, where surface temperature observations are really sparse, or let's say I'm interested in changes happening in the atmosphere or to clouds. In that case, I'll want to apply these methods to satellite observations. And that's actually what some of my previous work kind of did. So we're looking at broadband top of atmosphere changes in the Arctic, and what we found is that the time to emergence, we're no longer kind of using the observational record, but we're looking into the future and asking when did these changes kind of exit that envelope of variability, become attributable. There's this really strong seasonal cycle. And what this is really related to is that our forced change is overlapping with low internal variability in these fall months, and so we're able to detect changes much quicker, whereas in the spring, we have less change and more variability. And so satellite observations are really a powerful tool for attribution and detection, and there's a few important reasons for that. And one of them is that a lot of these records are now into their third decade. And so we have 20 plus years of continuous observations. And whereas surface temperature observations or just kind of surface observations are limited, they're point observations, our satellites are sampling kind of continuously in a spatial and temporal sense. And we have this advantage from satellites. Another big advantage is that the surface temperature observations are exactly that. They're at the surface. But again, if we want to see changes in clouds or changes in the atmosphere, we're going to be better suited for satellite observations. And so when we take observations from satellites, specifically spectral observations, this is where our retrievals come from. And so we can do attribution of changes in the atmosphere, which are also really important. However, there are some kind of important limitations as well. The reason that we're doing this study with kind of series observations of broadband radiation and not other observations is that we have this really nice scenario where the broadband output is exactly something that our model outputs as well. And so unless we have variables that are comparable, we can't do this attribution and detection work. So we can't take these observations and put them again in this context of change and variability. And so this big limitation is that climate models are not outputting things that can be directly compared with most satellite observations, right? Most satellites are observing over restricted spectral range, they have a field of view, and so they're observing a radiance that's not something that our climate models output. And that's exactly the tool that I'm kind of developing and kind of advertising here today. So to just kind of briefly summarize, climate change detection and attribution is really useful for policy and adaptation. Satellite records are this really powerful tool for that kind of work, but we need this kind of last link in the chain to take our models and create analogous output so we can draw these comparisons. And so what does this actually look like? Well, I'm going to start with COSPS, something that hopefully many of you are familiar with. It's a satellite simulator package developed largely in Boulder and by the CFMIP community. And this is for making comparisons between models and between models and observations where we're creating consistent definitions of clouds. So what are clouds defined by in CAM, or how does the ISKIP record define clouds? We're going to create consistent definitions so we're not running into definition issues when we're making our comparisons. And this tool is already kind of broadly used in the model development community. And what I'm taking and coupling into this is this fast rate of transfer tool called RTTOV. This has been developed by the UK Met Office and is used for data assimilation. And what it does is simulates the output from our satellites, again, these specific spectral and kind of field of view radiances, and it does it in a computationally efficient manner. And so we're going to, again, feed the same fields from our model into this rate of transfer code so we can create this comparable output. And And how is it going? Well, hopefully pretty well. The first step, which is integrating this rate of transfer code into COSP, is done and running. And what I'm working on right now is taking that COSP code and putting it into CSM2. And so that's underway, and hopefully it will be done by the end of the summer. And then our goal is to have both atmosphere only and some initial fully coupled simulations done by the end of the year. And so if you are thinking about how you could use this tool or have ideas on potential pitfalls, now is a great time. I would love to hear from you because I'm kind of working on the code. And once we move into the science realm of doing the simulations, it'll be harder to go back. So if there's functionality that you think would be really useful for some of your science, I would really love to talk with you. A really important question that you might have right now is this computationally efficient? And so I have this very boring screen capture of my screen where I just ran this tool for 150 model grid cells and for 3 instruments, for all MODIS channels, for all channels for an upcoming mission called TICFLYER in the far infrared, and for about 2,300 channels for the NASA AIRS instrument. And you can see that it only took a few seconds, and most of that was wind up. And so just like COSP, this is, hopefully you're not making the decision of whether to use this because of time, and you're thinking about the science that you're doing and whether it's going to serve your science. So this should be a tool for the community that is computationally efficient. And so I think that I talked a lot about attribution and detection, but I think there's some also compelling reasons to use this for climate model evaluation that Brian Medeiros, some kind of recent work that I've done with him, has laid bare. And so what we're looking at here is several versions of CAM. So we have CAM 4, CAM 5, and CAM 6. And we have our model bias and our cloud radiative effect. And so this is, again, our broadband property that is often used to tune the model. And then we're, again, using COSP to make these kind of definition-aware comparisons and looking at the actual cloud fields in the model. And what we're seeing is that over these sequential generations of CAM, there's improvement in our broadband cloud radiative effect. And so we have this kind of monotonic decrease in our error. But if we're looking now between CAM 5 and CAM 6 in the actual cloud fields, the improvement is more ambiguous. And in some cases, it looks like there's not an improvement, that the clouds may have slightly regressed. And so I think what this kind of tells us is that these broadband cloud radiative effect fields can hide compensating biases spectrally. And so you can improve this broadband effect by kind of making these compensating biases that are going to be apparent in the spectral domain. And so now to kind of look at some initial output from this tool, again, this is that 3rd instrument, the NASA AIRS sounder, and so we have all this spectral information, but what I want to focus on is that we have our clear sky in blue and all sky in red cloud radiative effects, and so the difference kind of between them, these are just clear sky and all sky outgoing radiance, and the difference between them is effectively a cloud radiative effect. And so we can see that in both scenarios, we have clouds, we have a big reduction in our outgoing radiation when we kind of move from clear sky to all sky, but that the spectral features are very different. And so if we're only looking at a broadband field, we're effectively integrating over our channel dimension, which is our spectral dimension. And so the area under the curve might be very similar and make it seem as if our cloud radiative effect is similar, when in fact the features of the clouds are present and can be evaluated with these spectral comparisons. And so I think that would be a really interesting application. And I'm not telling you to look at a spectrum every time you tune your model, because I think that's kind of ridiculous. But what we could do is just think about looking at error in the spectral domain alongside these broadband cloud radiative effect. To understand if, again, that broadband improvement is coming at the expense of worsening compensating biases. So to just briefly summarize, I'm building this computationally efficient and instrument-specific tool for simulating radiances in COSP and CSM2, and we're planning to also do this in the GIS Model E later in the year. And I'm primarily going to be using this for attribution and detection, but again, this should be a tool for the community, and so I want to make it useful for a lot of different applications, and if you have ideas, I would love to hear it. And we should have some initial simulations in CSM2 hopefully by the end of the year. That's all, and yeah, would love to talk further if you have any thoughts. Thanks.
just.
Yeah, it's a really good question because we can have the definition consistent, but if the scale isn't consistent, that's its own issue. Um, in terms of sub kind of grid sampling, this radiative transfer tool already does it with clouds. I don't think it does it with temperature and humidity. And so there are some kind of fundamental limitations of the scale there. And yeah, if you have ideas on how to kind of work through that, I'd be interested in talking. Thank you.
Ron, our next talk is from Garrett Lyman on limitations of machine learning. You got it?
Yeah.
All right.
Hi. Yeah. So I'm Garrett Limon from the University of Michigan. I work with Christiana Jablonowski, and I'm going to talk a little bit about some of our recent work on some machine learning stuff in CAM. Maybe a little change of pace from what we've been doing all morning. So some overarching questions that we look at is, first of all, can machine learning methods do some reproduction of simplified, or in our case, simplified physical parameterization schemes in CAM6? Over the last 5 years, this has been proven pretty true, I think, just in the machine learning community and climate modeling. And we're not going to oppose that here. The second question is whether or not the machine learning performance depends on the complexity of your parameterization scheme. And in particular, for simpler machine learning models, can we find some limits, or can we start to think there's a little bit of a limitation to their applicability in this realm? And then something that came up through this work is this question of domain knowledge and whether or not we can improve these predictions because of things that we know as atmospheric scientists, even in the context of modeling and things that are pretty well defined within the model, right? And then I'll just use this chance to shamelessly plug the paper we just published on this here, and if you want more details, it'll all be there. So how we're setting this up is, I think, pretty similar to how you would set up anything you would do with a new climate model or adding to a climate model. Is you don't just start with the most complex thing you have. You start from first principles, and we're going to be working in a 3D dynamical core with some simplified physics, and we're going to use two case studies of this simple physics test. One that's already built into CAM6, the Thatcher-Jablonowski or the Moist-Held-Suarez test. And we took that test and coupled a Betz-Miller convection scheme to it to add just a slight additional nonlinearity to the physics scheme. The math, this is the only slide with math. Basically, we're trying to predict the temperature, moisture, and precip rate, the tendencies, excuse me, from the Moist-Held-Suarez scheme. If you're familiar, it has this temperature equilibrium profile is kind of what can't find this thing. What depends, or what defines the Held-Suarez scheme, and for the moist case, it is slightly adjusted from what the dry case would do. And then we have this Betz-Miller convection, which adds a convective precipitation rate calculation, which I don't show here because it's a little bit overcomplicated for the purposes here. And then it does adjust that Thatcher-Jablonowski. You basically are adding this term here for each of these. So it's pretty simple additional complexity, but it does have consequences with the machine learning techniques that we use. So yeah, just to highlight, these are basically the Betz-Miller scheme is just the Thatcher-Jablonowski scheme plus these extra terms. So machine learning, pretty high level here. A lot of people view it as a kind of black box. You put in something and you get something out. And for a lot of users, I think that's pretty accurate. But what it really is doing is defining or determining a functional relationship between data. And in our case, we're really focused on random forests because I think they have abilities that I think are being overlooked, especially today versus maybe when we started all this machine learning excitement maybe 5 years ago. And so we wanted to really kind of probe that while we're in this simple regime in the climate model, we should be in a simple regime with the machine learning as well. We also do include a baseline neural network just for comparison because that's kind of the standard today. And we use Python packages, pretty common ones, scikit-learn and Keras to develop all this, and a hyperparameter tuning software called Sherpa for the random forest tuning. The neural networks, we don't actually tune them. We just took some inspiration from the literature and maybe a tweak or two, and they worked pretty well for us. And then I'll also take this chance to kind of convey that each case and each tendency that we're trying to predict or precipitate is uniquely tuned and trained for their own random forests. And this is our attempt, since we're working offline, to really find this kind of best case random forest for all of our things. So even though there's an additional complexity, that random forest is not just the same one we used for the moist case versus the coupled case. Just since this is the audience for it, the CESM configuration we used is very coarse. It's 2 degree CAM6 with the finite volume, 30 model levels. We used a 60-year model run, and we used the first 50 years of that after spin up to train our model, and the last 6 years to kind of test it. So all the results are coming from the data from the last 6 years. Wow. We also do some reshaping just to make it more applicable to the random forest and the way that this is built in Python. And the neural networks, you probably, if you have heard anything about machine learning, you always have to normalize things. And nowadays, you can just do that in Keras with a normalization layer, so that's pretty convenient. So onto some results. On the top right, these four panels are the temperature tendency anomalies, zonal mean, time mean, temperature tendency anomalies. So the machine learning minus the CAM output after doing the mean, or actually it's before doing the mean, should be the same. And we can see that these anomalies are pretty, I mean, they look busy, but the order of magnitude on these plots are pretty small. They're effectively reproducing what we want to see in CAM. The orientation here on the top is the moist case. On the bottom is the coupled to the convection scheme case. And then left is the random forest, and right is the neural network anomaly. And I think the main point for this top right side here is that as we go from that moist case to just adding that convection scheme in that one term, we do see in both the random forest and the neural networks this increase in the regions associated with the significant anomaly. Right? In the precip case on the bottom here, we have the moist, the large-scale precips, the only thing that's being predicted or being generated in the Thatcher-Jablonowski scheme. And then in the coupled case, we have both the large-scale precip and the convective precip. And these are almost indistinguishable. If I zoomed in here on the convective precip right at the equator, you would see a little bit of a discrepancy, but for this case, this is essentially indistinguishable. We also looked at some R-squared investigations, so I'm not going to show you all of them, but I'll point out the moisture tendencies here. Unfortunately, this is oriented basically the opposite of the last one. So the moist case is vertical here on the left side, and the convection is vertical on the right. And then the random forest is the top row, and the neural networks are the bottom row. That's just because I pulled these straight from the paper and cropped them, and I probably should have reproduced them. What the R-squared is the correlation coefficient. It's a ratio, or it's a measure of the ratio of the error in our simulation or our predictions to the variance of the data. And the easy way to interpret it is the closer to 1, the better you're getting. So the The more red areas, the better. Or better your learning, sorry. And I think oops, I clicked the wrong button. Wait, did I click the wrong button? What I want to point out in the R-squared for the moisture tendencies is this significant drop when you go into the convection scheme, which is kind of associated right where the precipitation rate peaks here. Where's it? Right where the precip peaks here in the convection precip scheme. Not sure why that happens, but it is very significant here in the R-squared statistical measure here versus the means that we saw before. On the bottom here, we have all of the precipitation runs for the R-squares, and I want to point out the order of magnitude here on the left-hand side, and all of these are very skilled, so everything here would correspond to like, this color and higher if it was in the color bar. But we do see that when the convective scheme is a little bit less skilled than the large-scale scheme, which essentially overlaps for each case because it's the same calculation internally in the model. So you would expect to be able to do it no matter which case you're studying. Also, I will highlight the kind of this domain knowledge idea that we had and Christiana suggested about a year ago, where these tendencies in their functional form in the model don't explicitly rely on the relative humidity, but we know that relative humidity is interacting with all of these processes under, in the physics of the system. And so when we tried to just include that in the input features, we got significantly better results. This is early results. We basically, this went from where we were still working on getting these things to run where we thought we could and to where we felt like we could kind of publish some of this work. So it was pretty exciting, but I think I like to refer to it as maybe an unexpected result if you were a data scientist trying to do this, but maybe an unsurprising result as an atmospheric scientist. And I think that interaction and that intersection is pretty interesting where I tend to spend my time. And then I did try last week just to have something that wasn't in the paper for us here today, and it's working, to generate some new 2-hourly data with the same CSM configuration and apply the random forest to it. So this is the large-scale precipitation rate from the coupled case, the convection case. And so this can be considered a very simple example of what we would say transfer learning and applying something to new data, even though it's the same case, it's different resolution data. And the red flag that we got right away, and I still wanted to show it, was that we seem to be missing in the predictions the lowest range of the precip. So I'm not sure why that's happening. I have a few ideas. There's a paper that's probably going to come out soon from Ashesh, who talks a lot about constraining machine learning for smaller scale features so that it's more stable when you couple some of these crazy things they're doing at NVIDIA back into the model. Maybe something like that is happening. Definitely, if I left this without further investigation, I expect it would impact the results we'd get in the model when we couple it. So I'll have to look. I'm hoping it's just a bug, though. But we'll see. And then just some ongoing and future work. I'm in the process of coupling some of this. We've hit, as Peter mentioned yesterday, a few known unknowns in that process. I liked that word, so I wanted to throw it in particular with these were best case scenarios, so these random forests are pretty big when you save them to file. So balancing that is going to be a little bit tricky if we want to actually couple some of these. In particular, this parameter here, which is both very important for the skill of the model, but also the size of the model. It's basically how long our branches of our trees can be. I want to go further into some of this transfer learning stuff once we have some of these coupling tests done. And then something I would like to do one day, but maybe is not time appropriate as I try to finish my thesis, is kind of creating more steps, but also a repeatable kind of workflow in Python for some of this work so that I can kind of distribute it or something like that. I think that'd be really interesting. And then I think at this point we're we're on the topic of maybe moving on from the random forests in general, as the rest of the community seems to have done, and just focusing more on some of the neural network stuff and the capabilities they have. And for that, I'll end and take a question or two if we have time. Colin?
Yeah, this is really cool stuff. So it was interesting to me that the relative humidity inclusion as a predictor seemed to improve things quite a bit, because relative humidity at the end of the day is kind of T, Q, and P. Like,
yeah.
You know, and you have T and Q in there. You know, it wasn't 100% clear whether you had pressure as a predictor. But my question, which kind of falls off of that, but then also aligns nicely with your last bullet point, was so one of the benefits of random forests is they provide this nice like feature importance metric that you can actually use for interpretability. I was curious if you had looked at that and if you had any insights into kind of what was leading to skill improvements or dropouts in some of your runs.
So in the paper, we do have a little bit of a conversation, but to the extent of this work, it was really that relative humidity inclusion. It was the most important feature improvement that we got. We used to use some stuff like the latitude, because that's an important in the calculation. It didn't really make a huge difference taking it out or leaving it in. And that's something that we definitely talked about, maybe checking if we even need to use the full model pressure or just the surface pressure or things like that, but we never really got around to it. But it's a good point. And as you said, there are a lot of benefits to random forests, but I think their capabilities and their size and their memory to be able to do some of this stuff, especially when we're talking about such simple things here, and what we would, you know, preferably in 5-10 years want to be doing, it's hard to see that really holding up any longer, and probably why the review process really wanted those neural networks in there for our paper.
But I do love the interpretability side.
Yeah,
of
the interpretability, and there's other things like it won't extrapolate outside of the range you want it to be, and so without having to hard code in physical constraints, it can be really useful like that too. Yeah. Mm-hmm. Yeah. Thank you.
Yeah, this is a little bit of a wild ride through the biases in E3SM. E3SM is a climate model by DOE. And this will be quick. Let me get started. I also want to mention this is work together with my student Lisa Nguyen. And also Doug Kinnison provided me with WACAM data last week, so I thought I'd sneak in some WACAM information because this is kind of the audience, not just for E3SM, but for WACAM as well. So let's get going. I'm talking about temperature, so three things: temperature, specific humidity, and zonal wind, and kind of focus on the biases in the stratosphere, mostly in the tropics, but you also see global climatologies. What you are seeing here are CMIP6 data from the released versions that you find also online, like E3SM version 1, E3SM version 2, which is the newest one, and that only has been released last year. It's not in the literature, and therefore I want to really show it. And then we also have WACAM data. These are AMIP type simulations from something called WACAM CCMI, which Doug Kinnison provided. We also have some comparison to ERA5 data, and also SWOOSH, which is a satellite product for ozone and vapor, and some TRIM, which is precipitation. All right, let me get going here with the temperature, and this gives you kind of a general overview of the, the climatology. These are really long-term means. And as you kind of see already, this is E3SM version 2, this is ERA5. This is the difference between the two. We are talking about biases in the upper atmosphere of 40 Kelvin plus. This is really substantial. This is a warm bias in E3SM, so maybe even telling us we shouldn't use the model in these regions. Let's compare this, quick look here at WACAM, which is kind of now here on that side. WACAM does not have that bias, luckily, but we see even in the older versions, E3SM version 1 here in the middle, it's almost identical to E3SM version 2, the new version. So this bias has been around, but maybe not noticed by E3SM people. okay, let's ask questions, what's causing this bias? And this is kind of, kind of a wild ride through potential causes. One potential variable you can look at is called DT-cont. This is heating from moist processes. And this is now a stratospheric view of DT-cont climatology here in E3SM version 2. And that's even very problematic because you see this stovepipe behavior, constant heating with no structure. So this is definitely something, I talked to Adam Harrington here at NCAR, this seems to be a bug in CLUB actually, and not a feature we should be seeing. And this was, interestingly enough, it was not actually even present in the old version of E3SM. And it's also not present in WACM, but WACM has something at 1 hectopascal. I'm not certain what that is, some heating tendency for moist processes. So maybe WACM people can tell me. So maybe that should be there, maybe not, I can't tell. All right, then you can ask, okay, this constant heating, yes, that contributes to, a warm bias, but you can also speculate it could be radiation. And in radiation, you can look at solar radiation, heating from solar radiation, or cooling from long wave radiation. So let's take a look at the two. So the upper row is heating from solar radiation, E3SM version 2, version 1, and WACM. And now you clearly see a difference. WACM is actually doing the right thing. We see really huge biases in the solar radiation in E3SM. But when you look down, the long wave cooling has also this huge bias. And interesting enough, when you add the two, and this is kind of where the cancellation typically comes from, when you add the solar heating and the long wave cooling, it's gone, it's almost gone. So there are these huge biases in radiation. In the sum, they are, when you kind of compare it now, WACM, this is the sum of the two in WACM. Here's the sum of the two in E3SM. There is sponge layer, you see some, sponge layer effects here still in E3SM version 2. But it's probably not radiation because there's cancellation of errors. Of course, radiation errors are probably caused in this region by ozone. So let's take a look, and then we go to specific humidity. Yeah, ozone isn't looking too bad, actually. And this is now a comparison between, E3SM version 2. This is climatology of ozone. This is swoosh, this is satellite product, and then we have WACM, and they kind of look alike. You find some differences, but that's probably not the player in this big temperature discrepancy. All right, okay. Next wide right, specific humidity. So this is really not good. We have E3SM, E3SM super dry, almost no moisture here in the upper atmosphere. This is ERA, and here we have the difference. So basically there's absolutely no moisture, and we can again compare this rather quickly to to WACM and swoosh. Okay, now it's a little bit different display here. This is kind of the logarithm. No, this is in ppmv. So we have almost no moisture in E3SM, swoosh and WACM kind of look alike. So that's good news, of course, for WACM. And when we, again, ask questions, what in the world could cause this? You can look at this is now the drying tendency from moist processes, DCQ, it's a kind of a model variable. And yeah, you clearly see in E3SM that, there's a lot in green. There's a lot of permanent drying here in both versions of E3SM. That's not true in WACM. That's actually slightly positive even. But this is a logarithmic scale down here. So yes, there's something going on. It could be related to CLUB. We can't tell at this point. But what really I want to focus on, not so much on this climatology here. I thought the tape recorder might be of interest. Tape recorder is this water vapor signal that propagates from the tropical, tropopause up into the atmosphere. Here you kind of see it a little bit. Basically what you are looking at are timelines. Down here we have in years, and then we have the pressure aligned E3SM version 1, 2, 1, ERA as kind of an observational product, and swoosh as a real observation. You actually see ERA and swoosh are almost perfectly aligned. And we see the big, of course, drying bias here in the E3SM data. So yeah, that's really distracting. So let's take out the, just look at the anomaly. Let's take out the background bias, the dry bias, and then we really just have the anomaly propagating upward as a tape recorder signal. This is a water vapor signal. Again, we have like the timeline, the pressure, swoosh down here, and ERA as observations. And now we see it a little clearer in E3SM. Actually, there is a signal there. Let's take a closer look, just 15 years, do a composite of January's, February's, and so on to get really a clearer view. And when you do that, then you have a real more, kind of clearer view. Now we have just a composite of all the month versus height. And here's swoosh, and you see the negative and positive anomalies. And this is an eyeball norm line that I was drawing to kind of get information about, the speeds. And here I'm just, this is eyeball estimate, yeah, but we are clearly seeing a swoosh kind of, this is the upward speed in millimeters per second, error 5, overestimating it, and E3SM kind of in the middle when you kind of look at these. Before we then, maybe only have a minute left here. Before we move into zonal wind, one more thing. Wacom is doing actually a good job, and this is from the literature. It's by Gettleman. When you look at the tape recorder signal from Gettleman, and I really just want to highlight this coupled simulation that is giving a decent tape recorder. It's a little bit too quick in Wacom. My estimate is maybe 0.29 millimeters per second, which is unfortunately not consistent what they had assessed in their paper as the speed of this tape recorder. But that is kind of just my estimate here when I just look at contours. All right. Okay, I want to finish, let me see whether I get through him, by some thoughts about zonal wind, my last item. Zonal wind, of course, now climatology even, again, very much biased in E3SM. Let's take a look here. So we have actually large biases here in the polar jets. Also, it's both in hemispheres. This is ERA 5, and this is a difference. ERA 5 actually has also an overestimation. This blob here is actually the semi-annual oscillation here in the mesosphere. This is actually an overestimation, so maybe let's not concentrate on that blob. That Mara and others don't have the strength of that. But kind of let's just take a look at zonal wind. Here, again, Wacom doing a decent job, maybe not so much in the SAO, but Wacom is decent in comparison to ERA 5. Okay, last thing, QBO, and this is, again, the U wind signal in the tropical atmosphere, in the stratosphere, E3SM version 2, 1, and ERA as kind of the reference here. You clearly see, various kind of characteristics of the QBO. So let's that's also in here, the SAO here in DOSE's version is actually propagating way too deeply into the atmosphere. So this is another bias, but let's not focus on that. Let's just focus on like a 20 hectopascal cross-section. And then we see the period actually really clearly. So in color-coded, we have, E3SM version 1, E3SM version 2, and ERA as an observation. And yes, all are biased. E3SM are biased. You see ERA is about 28 months here in orange. Version 1 has about a 16-month period and 21 months for ERA version 2. But you also see actually the amplitude variations, and now you pick your battle because neither version 1 nor version 2 are perfect. Some overshoot in the westerlies, some overshoot in the easterlies, so you pick your battle here. Okay. I want to wrap up with possible reasons for these QBO differences. Cloud could be a trigger for waves, and that was really a shocking thing for me to see that when I plotted some of the cloud features, this is cloud fraction, again in E3SM version 2 versus 1 Wacom, we actually lose a lot of cloud in DOE, E3SM, and we really use convective clouds. There's almost no convective clouds, and you think convective clouds could be one of the triggers for tropical waves. What I then got surprised at, that, you lose all the clouds, but you don't lose the precipitation. So that's curious. So with fewer clouds, you still get almost identical when you kind of look here at, this is total precipitation, large-scale convective precipitation. That's not so much of a difference, especially in the total. You see basically E3SM version 1 and 2, very much the same as even with Wacom, but in the cloud amount, very, very different. So maybe it has a hint here, which is a hypothesis that, you have fewer clouds, but if you have them, they rain really hard. So you get these blasts of rain. So that's a hypothesis which needs to be tested. Okay, I wrap up. I'm over, okay, let me skip. We have some, you can look at it later. You can look at some tropical waves, and let me, wrap up with, some observations. My main message is, E3SM is pretty biased in the stratosphere, needs to be looked at. I don't think they, DOE focused on that, but it looks really, WACM in comparison looks really, really good against it. Let me close here. Thank you.
Yep. It is WACM 6, so it's
yes, it's
okay,
WACM 6. Yeah. Mm-hmm.
So in terms of the vertical grid in the stratosphere, what's the kind of summary of the difference between E3SM? Because I believe that's 72 layers.
72 levels, 70 levels.
Okay.
Model top at 150.
And that are they comparable?
70 levels.
Okay.
Model top at 150.
And that are they comparable then in the stratosphere?
Oh, the resolution should actually be denser in E3SM. We have more grid points in E3SM.
I thought E3SM had, given the 72 levels, I thought they had more boundary layer levels. Therefore, one would imagine they had fewer.
Yeah, good question. I didn't do. Yeah, that's actually a good point. Let's look at that. Yeah. Oh, you probably know. Yeah.
So the resolution in E3SM is really good through the troposphere, but in a lower stratosphere, it very sharply tapers off really quickly. So we think there's a lot of issues with that. So Walter Hanna has been doing a lot of work. We're trying to make a smoother grid, and even with just minor changes and smoothing out the resolution, he's already getting a better QBO.
But is it coarse or denser than WACM?
Depends which point. So E3SM is finer than WACM, but then it really goes sharply declines, and it's that sharp decline that seems to be the problem.
Okay.
I just have to ask, was there any solution to the huge warm bias?
No.
No explanation.
No.
Okay.
I think they never looked, but this has been around since version 1, so it has been some years, but nobody noticed, or they noticed and they didn't care.
Right.
No.
All right, our final talk of the session here is from Kevin Reed on tropical cyclones.
All right. So yeah, switching topics, I wanted to talk a little bit about tropical cyclones, and I wanted to changes in hurricane rainfall, for example, but just kind of use one of the advantages of CESM over different climate models is this ability to run in very different configurations, and so I hope I'll highlight this. So the motivation, of course, is that every year there's billion-dollar disasters, and then every year there's hurricanes are part of them, and particularly they dump a lot of rainfall, particularly along the Gulf Coast and the East Coast. And it's really through these changes, so we talk a lot about mean climate when we look at biases in the model, but it's really through changes in extreme weather in which humans will actually experience climate change. And so it's important to start to understand, use the models for exploring changes in the extreme events themselves. And as we've talked a little bit over the last day and a half, we're kind of entering this era in which the tools that we have can actually be applied at high resolution. So, that gap between kind of weather scale modeling, which typically looks at day-to-day weather, and climate is kind of narrowing. And so there's been a lot of work, and we've seen some of this even in yesterday's ultra-high resolution breakout, that it's really the advances in these climate modeling can help to really investigate not only extreme weather, but regional impacts of climate change. And so here I'm going to just demonstrate, as I mentioned, kind of the use of the CAM hierarchy to understand some of these changes. So real quick for the methodology, I'm going to be using 10-year-old plus year-old version of the model. So we're using CAM5 for all of our simulations. Mostly going to be focused on what we call high resolution, which is 25 kilometers, but I'll show some results of 100 kilometers, the conventional standard. And everything that I'm showing is atmosphere only, so these are prescribed SST runs. We're going to kind of explore AMIP simulations, so climate scale simulations, and we're going to try to understand some of the changes in rainfall that occur between idealized simulations in which we remove topography, land, and SST gradients. And we're going to try to compare across this pretty wide scale of this idealized to the realistic simulations all the way to observations. And then I'm going to focus on tropical cyclones, TCs, and I'm going to focus on tropical cyclone rainfall. And so just really quick, the way in which we do this is we use tempest extremes to identify storm candidates. We stitch them together in time, we look for their dynamic size. This is taken to be the radius of 8 meters per second of wind, and then we extract all of the rainfall within that radius to be rainfall from the tropical cyclone. And so every plot from here on out will be focused on tropical cyclone rainfall. And this is work by Alyssa Stansfield as part of her PhD thesis. And so some of the early work that we did is we just kind of looked at, okay, if you run the variable resolution version of CAM5, you know, can you look at what's the impact of going to high resolution and how well does the model simulate tropical cyclones? But also we started to look at how does tropical cyclones rainfall change in these kind of VAR-res setups. So I've been showing this slide for almost 10 years now. I think it's just really illuminating that if you take the conventional version of the model and you track all of the hurricanes, this is the number of hurricanes you get in a 26-year run. And if the only thing you adjust in the model is the resolution, right, this is the number of tropical cyclones you get. And of course, there's biases, but the idea is that this model produces a lot of these storms, which means if you're interested, you know, not in getting the regional impacts 100% right, but interested in what changes in the rainfall, that this is a good model for it. And we've shown that if you start to do this with the variable resolution setup that I started with, you can start to look at things like storm impact. And so the top row is the present day. It's a track density, or the simplest way I like to think about it is just the number of hours per year that an individual point experiences a tropical cyclone or is within that radius of 8 meters per second that I mentioned. And the bottom two are just different scenarios. The middle is RCP 4.5 and the bottom is an 8.5 run. And so because we have this ability to extract precipitation, we can look at, you know, how much rainfall is coming from those tropical cyclones only. And so in the present, you see this kind of what you'd expect, that most of tropical cyclone rainfall is near the coast. And then if you look in the future scenarios, you can see that the amount, the annual average or the annual average from RX 5-day, whatever type of metric you want to use is actually decreasing in the future. And it gets a little complicated in some areas. And that's in part because if you start to look at how much rainfall is falling per storm hour, so if you just take the middle row and you divide it by the left row, you can see that actually there's actually significantly increases in the amount of rainfall per hour of impact. And so this is what we're going to start to explore actually in the kind of idealized hierarchy. And so these are, again, some simulations that Alyssa did during her PhD. And so we're going to take a variety, we're going to again use CAM5, we're going to now use global high resolution at 25 kilometers, but we're going to run an aquaplanet mode, but we're going to make a couple additions following the radiative convective equilibrium model intercomparison project, in which we're going to, we have rotation, which RCEMIP doesn't actually, but we've taken out any kind of gradients in sea surface temperature, and we've taken out all gradients in things like ozone, and so it's basically meant to kind of mimic a large domain limited area model. But now we have rotation, and then we're going to run a series of sea surface temperatures in which we fix the global temperature, right, to one value, and we're going to utilize the actual sea surface temperature that's under tropical cyclones from the realistic runs and observations that I just showed. And so here's like just an example of what these worlds kind of look like. These are actually great for looking at tropical cyclone statistics because they're essentially tropical cyclone factories in which you're producing tropical cyclones all the time in about 20 to 30 degrees north or south, and they're propagating towards the pole. There's no baroclinicity in the model because there's no SST gradient, so of course they do weird things at the pole that are actually somewhat interesting. You can do a lot of results to understand how many storms are controlled on the globe because there's a packing density of which you can actually put these things on there. But they're these really idealized environments. But in this area where they develop and move towards the pole, they actually do a lot of similarities to what the actual real-world tropical cyclones do in that space of kind of 10 degrees north and south towards 40. So we can start to look at the tropical cyclone climatology in these runs, and so the colors now are just the different global SSTs, right, going from cool to the yellow colors, which are the warmest. And you can see some interesting things that are consistent with the global scale realistic simulations, particularly as the global temperature warms, you get this pretty significant decrease in the number of tropical cyclones, both in their genesis count, but also kind of just in their track or in their occurrences. You can see, of course, that most of the tropical cyclones are packed at the pole. You can see that there's actually an increase in the wind speed intensity of the storm, but actually in this transition region between, you know, kind of the equator and 40 degrees north, they're actually consistent in size, which is an interesting result. You can start to look at rainfall again using that same methodology, and you can see, of course, that the rainfall increases But what I want to focus on is you can start to do some interesting analysis of the actual characteristics of the rainfall field. So these are a frequency and amount distributions kind of built off some of Angie Pendergrass's work. And you can start to diagnose in this model where are these increases in precipitation coming from that you saw on the last slide. And we can actually start to diagnose that actually about 60 to 80% of that, right, there's some uncertainty there, of that increase in rainfall is actually coming from the SST alone, the thermodynamics. But if you control for the intensity of the storm and you look at changes, you can actually see that that part of the increase in rainfall is actually due to the fact that the storms are stronger. And so you get this kind of additional effect of the dynamic changes in the storms. And so this is what we started to do then to connect across the hierarchy. And so here I'm just showing, again, some of Alyssa's work, more recent work that was recently published in MPJ, that looks at radial profiles of that precipitation, again, using the tempest extremes. You can see that for observations and the colors are now the SSTs under the storm. You see the observations and the AMIP simulations are doing some similar things, but you can also see that the model actually maybe overproduces rainfall in the core of the storm. You can see that in the future, you see these increases in the rainfall as we talked about when we focused regionally on the US, but that the RCE MIP actually has somewhat more similar characteristics to the real world than maybe the idealized storms. But it's important to know that, again, there's a lot of difference in the storms that we're analyzing here. While they're all kind of in the tropical area for the analysis, you can see there's differences in the SSTs that they experience and the count. But what Alyssa kind of did as a final part of her PhD was looking at, can we start to look at changes in precipitation across SSTs, right? So what's the relationship between precipitation and sea surface temperature under tropical cyclones? And can we start to understand, the changes that we've seen, are they consistent in observations? Meaning that if you, take climate change out of it, if you just look at what's the dependence of the sea surface, the tropical cyclone rainfall on sea surface temperature, you can see that all of the model idealized simulations and the realistic simulations, as well as the OBS, are all within kind of the uncertainty range. And that you kind of get this, what we call apparent scaling of 6 to 10% per degree Kelvin. It just means that if you have a storm over a warmer SST, a degree warmer SST, it'll get 6 to 10% more rainfall. Of course, it depends upon the metric. Right here, we're looking at the 99th percentile. You can also look at the mean precipitation within the core of the storm. But the interesting thing is that when you try to diagnose how does the rainfall change in the future run, which is this kind of second AMIP simulation here in the future, you could actually approximate what the rainfall changes would be by just adding a Clausius-Clapeyron 7% to this line here. But what you actually see is that in the in the AMIP future simulations, that you actually get an increase of around 5% per Kelvin. And so this is just, I think, a very important result, that there are study after study every week coming out that is focused on tropical cyclone rainfall changes in trends in the observations. And I think there's a lot of convolution going on between the actual apparent scaling, just the dependence upon SST, and the actual climate change that's impacting these storms. And this just shows that the hierarchy can be really useful to explore that. So I'll just finish with saying that this work kind of suggests that as the surface temperature warms, of course the mean and the extreme precipitation in tropical cyclones is increasing, but the magnitude of that extreme precipitation can actually increase at larger rates. And we're starting to kind of shed some light on what are these extremes are coming from, or where this changes in extreme precipitation is coming from. And one of the things I didn't show is that actually we've also used a different part of the hierarchy in which we kind of run the climate model in weather mode, hindcast mode, and you can actually also do these type of simulations, and you get very similar changes per degree Kelvin. And so this kind of also provides additional confidence that the model it can be used for these purposes. So I'll just thank the funders of this research and stop there.
So we have time for a couple of questions. Well, I just how did you get your observational estimates of the precip distribution in tropical cyclones?
So, yeah, I didn't mention that. That's a great question. So we used a MERGE, right? So the NASA product. So we a data set for precip, and we do the same. We track storms, or we have IB tracks, and then we extract precip within using ERA5 for a dynamic radius to extract the precip in the same way that we do for the model.
Right. All right. Thanks. Any Well, if there are no more questions, I think it's lunchtime. Thanks very much, Kevin. Yeah. So thank everybody. Let's thank all the speakers, and that's it. Thank you.
Okay, we're gonna get started. Don't be too mean to the people filtering in really late. So, welcome to the whole atmosphere working group session. My name's Nick Davis. I'm one of the co-chairs, along with Nick Peditella and Dan Visioni, our external co-chair. So we've got discussion time padded out 15 or 20 minutes at the end of each of these sessions for community discussions or extra discussion on some of the talks. So we've asked our speakers to adhere to 15 minutes, but we've got a little bit of slop in the system if something's particularly provocative for a discussion. And yeah, we will go ahead and get started. So we've shown this timeline a lot, and now we're going to need to start adding another year pretty soon. But we've always shown this because we've got a few functions that the working group does, which is improving community support and existing functionality of the model, more sort of model die-core physics level stuff, and then trying to create these sort of longer timescale advances in modeling capability. And so some of these things were a sort of community push. We have not done something like initialized prediction comp sets yet, but you can tell that because there's an ESPWG parallel with this session, there's obviously a lot of community interest in things like that. I've graded some of these out just to say they're in progress or not. We've actually done quite a few of these, including, thanks to Francis, the TEM and transport diagnostics, a lot of physics updates, and some things we've been thinking about for the current year include, trying to explore updates to the specified dynamics approach, thinking about how to carry gravity wave schemes over to variable resolution grids, and then of course the big one today, which is Wackham's integration with the CAM mid-top workhorse model. So just to briefly summarize some of the things the group's been doing, and I'll point out there's a few talks here today in this session and in the following session with some of these accomplishments, but we finally have a pretty stable spectral element configuration of Wackham at 2-degree nominal horizontal resolution at 135 vertical levels with interactive middle atmosphere chemistry. So this was one of our sort of key model configurations in addition to what we're moving on to soon, which is 1 degree with TSMLT chemistry. Karma will have a slide talking about improvements to the aerosol scheme, especially in regard to sulfate injections. We've done some initial configuration and testing of Wacom X built on top of this sort of vertical grid, and Nick will talk a little bit more about how our different vertical grids transition from Wacom to Wacom X. And then there's a preliminary coupling of Wacom X with Gamera, which Han Lee's going to talk about immediately after this talk. And then a lot of studies looking at solar intervention, or I should say climate intervention strategies. We've also, using this new ad hoc tool, CMRISE, the CCMI 2022 data, and that's being archived right now at CETA. Maybe also going to use that for QBOI. Just continued development priorities are evaluation and tuning of these two versions of the model using the SC die-core, implementing the MPAS vertical extension, again, continued development of Wacom X Gamera, a lightweight Wacom X, and then addressing some regional refinement issues. So this is a sort of schematic view of the vertical level scheme. So you've seen something like this earlier today and throughout the meeting so far, looking at these sort of workhorse configurations. So here I'm showing the vertical grid spacing in terms of log P altitude, in the L58, L93, and then the new L135 Wacom configuration. And I've put the 110 level scheme here. So it's sort of a lot like how L58 spins off from L93 a little lower down. We actually now diverge from the L93 scheme at about 25 kilometers and have a very gentle roll off of the grid spacing through the middle and upper stratosphere, through the mesosphere, and then back to our usual 3-kilometer grid spacing in the lower thermosphere. This sponge layer stuff is actually quite important for stability, as I'll talk about later this session. I think partly because the spectral element model is less diffusive than FV. When we were dealing with things like gravity wave tendencies, it's very important to have this large sponge layer at the top of the model. Through quick thinking by both Rolando and then Hanli's ability to have his own source model ready to go, HB diffusion, so free atmosphere critical Richardson number diffusion, has been put back in to Wacom to help stabilize the middle and upper atmosphere, basically wherever Club's not active. And so we now have this extra turbulent scheme that kicks on above Club. Like I said, we're moving to 1 degree, and then, our core hours right now for NE16 with MA chemistry are 7,000 core hours per simulated year, which is a bit lower than it was earlier this winter when the model was less stable. So this is just a quick snapshot showing you the FV model, so Wacom 6. This is the 70 level model compared to 2 current options from a recent tuning round of the spectral element 2 degree L135 model, and comparing them to MERA 2. So obviously we don't have a lot of coverage over a lot of the domain, but just lower down, what you can see is that we've sort of eroded away some of those biases, like the extra strong, the 2 weak easterlies in the southern hemisphere, in southern hemisphere summer, and then we're also chipping away at that sort of cold vortex bias in the sort of upper stratosphere, and also now essentially have no bias in the lower stratosphere, in the lower part of the vortex. Some of these runs have different flavors, so we still occasionally get this cold vortex bias, but otherwise things are reducing quite a bit. And then just in comparison, this was a sticky issue earlier when we started with the SE model, the mesopause. We had a 50K bias at the mesopause, so we basically just did not have a mesopause when we started running SE. But now we've sort of converged to being a bit better than FV in terms of the actual biases themselves. So now compared to Sabre, for example, in December here, we're only on the order of 10 Kelvin warmer at worst. In terms of the absolute minimum, we're still not quite as cold as FV, but we're sort of fixing this issue where the mesopause region sort of rolls off too quickly towards the mid-latitudes. So SEs, we've actually got some leverage now on kind of beefing up the depth of this region.
Do you want to talk about this? We'll switch off. So I just added this slide that I stole shamelessly from Simone's GMD paper, basically trying to add karma aerosol microphysics to Wacom, and this in particular is trying to figure out whether whether cases like big volcanic eruptions like Pinatubo, whether they look better or worse with MAM4, which is the current scheme. So the model aerosol microphysics, and there's a MAM5, of course, coming up next, but also with KARMA, so the sectional aerosol microphysics, which is a lot more expensive, computationally speaking, but offers up a lot of interesting things at dividing pure and mixed sulfate and so on. And so this is again from Simone's in discussion paper, looking a bit at Pinatubo, and in particular discussing also whether it makes sense to inject all of the SO2 from a case like Pinatubo in one grid box, as is mostly done, or whether it makes sense to get better match with observation to expand more the area of injection, so from a column injection to a regional injection, so assuming that the SO2, the sulfate clouds already spread a bit before we start the simulation. And clearly Simone gets a lot better results. There are a lot of improvements in terms of the size and the burden and the AOD. And there's also a poster, and there's also a poster up from Ilaria, a postdoc from Cornell, that she's looking more at the radiative properties of aerosols in both KARMA and MAM, and so trying to explore this a bit more. That's all I have on this slide. So.
So I'll briefly discuss some of the development for Wacom X. So main development in the past year or so has been using the spectral element dynamical core for Wacom X, and this involved new development for the physics and dynamics. including molecular viscosity and diffusion in horizontal direction, and then this regridding between the physics grid and the geomagnetic grid that we do all the ionosphere processes on. And currently there's two configurations. There's a NE 120 with 0.1 scale height vertical resolution that Han Li discussed a bit yesterday in the high resolution session. And then we have also started testing a more kind of conventional grid that I'll discuss a little bit more. And this is a NE16 horizontal resolution with a quarter scale height vertical, which would be more comparable to what we use for the FE dicore and for longer simulations. So the initial new development of this new vertical grid that Nick previously discussed for WACM-X ends up being 189 levels. And this follows the CAM and WACM grids up to about 10 to minus 1 hectopascal, and then it just stays at a constant quarter scale height vertical resolution throughout the thermosphere. And so this will be likely the new grid that we use for WACM-X. I call it here 7. I don't know what we will call, because we're currently at WACM-X 2.1. Whether we decide to call it 7 or not, I don't know. But this would be the grid that we'll use for a new version of the model built off of CAM 7 and WACM 7. And the initial test we have done use a nominal, this should be a 2-degree simulation for NE16 for January solar minimum. And I'll show a quick comparison here of the different result. And so here is the comparison between the zonal weins for the spectral element dynamical core on the left, and then finite volume on the right. With 130 level, that's the sort of default version now for FV, and then this is for temperature. And generally, the zonal structure is quite similar between the two. Although this is just 1 January, so we can't really say much about the interannual variation. And then we also look at the thermosphere composition and electron density. Main point here is for the in the high latitude thermosphere, there's a slight decrease in the thermosphere composition, which sort of reduces a bias that we know is in the model. So that's a general improvement that we see so far from the initial testing, but more needs to be done once it's sort of a tuned up version of WACM that we can build on for WACM-X. We will start doing that in more detail. And then Han Li will discuss this in more detail, but there's been development in the coupling of WACM-X with the Gamera model, which is a magnetosphere model to provide the forcing of the high latitude during geomagnetic storm. And here is just comparison of the thermosphere neutral density at in the NE120 versus NE30 coupled to Gamera, showing the sort of structure you get when you use a much higher resolution version, and that leads to more Joule heating at the high latitude, and I think Han Li will discuss this in much more detail in the next talk. And so just to summarize the kind of developments that have been ongoing for WACM and WACM-X, mainly it is focusing for WACM on this development using the CAM7 vertical grid and physics, and the tuning, as Nick mentioned, and we'll talk more in a couple talks, is sort of underway and beginning to start some multi-decadal simulations to look more at the interannual variability and sudden warming frequency. For WACM-X, development is mainly this 189 level SE configuration, which will be used going forward. And one thing we are considering, this ends up being a fairly expensive model configuration once we add an additional 50 levels to what was already a somewhat expensive model. We're considering developing a lightweight version of WACM-X, which would maybe have some either a lower boundary at a, not at the surface, but say somewhere in the mesosphere, or some very, simplified representation of troposphere and stratosphere that could just be used for studies focusing on thermosphere or ionosphere, where you don't need a detailed representation of the lower atmosphere physics, but this is still sort of something being considered just to make it easier for community to use WACOM-X. And then, of course, there's Gamera coupling that will be discussed in more detail. And then, of course, there's a number of other science application which will be discussed more in the subsequent talks in the session. So we will conclude there, and I think if anyone has question, comment, feel free, or we can wait till discussion.
Sorry, if anyone has a quick clarification, that's fine, but we can leave sort of broader development discussion to the end discussion if everyone's fine with that. Okay, sounds good. Han Lee's next, yeah.
Thank you. So, yes, the title here is a bit more specific than I submitted. So it's still pretty preliminary, but we're looking specifically at the resolution dependence of a storm time simulation. And so the two models, Nick already tell you quite a bit. I will just give you a quick summary on the WACOM-X and also Gamera. So the WACOM-X uses the new species-dependent dynamical spectral element dynamical core, and it's on the cube sphere. It's one of the CESM components, and also it's the geospace component of CEMA for space weather applications. And here we're using two configurations. One is the NE30, so it's a bit higher than what Nick was talking about, NE16, but the same, this is still using the old vertical level, 130 levels. And then for the high resolution configuration, there's a NE120, 25 kilometer with 1/10 of a scale height vertical resolution, so about 270 levels. And then the high latitude electric potential, and I didn't say here, but also the energy flux, the aurora precipitation is specified by Gamera model. So the Gamera is the new magnetosphere MHD model, and it is part of the MAGE model system, the multi-scale atmosphere geospace environment model developed at, or being developed at CGS, the Center for Geospace Storms. And it was run for this study, it was run with a quite high resolution. They call it octoRes, which mapped down to about half degree in the ionosphere. And it's for a storm on August 24th of 2005. So this is a schematic of the two models and how they are coupled at this point. This is a one-way coupling. Let's see. So here is the CEMA. Mary showed this morning, so we're using the configuration with SE dicore and the ionosphere, ionosphere and the thermosphere component, and it is driven one way by MAGE, and in the future, at some point, hopefully we'll have a feedback interaction to the MAGE model. And so I just throw this last minute, so I forgot a title here. So this is before the storm, trying to look at the base state of the ionosphere from the high resolution model on the side and the low resolution model, regular resolution model. And so this is this is electron density as a function of latitude and height, and starting from the E region. And so the main point here is I copied the contour from the high res to here to compare the two. And this is the so-called EIA structure, equatorial ionization anomaly, basically what also called the fountain effects, because there's a strong upward lift in the equatorial region. So you have this two peaks on both sides of the equator in electron density. One problem we always had in the previous modeling studies is this structure is compared with observations, it's kind of shallow, and then the distance of the peaks are quite narrow. But now with high resolution, it seems it's a good improvement over the previous regular resolution models. So this is right before the storm started. This is August 24th, UT0. And then we look at, here is the Joule heating. Nick already showed this one. So this is the Joule heating in the upper thermosphere as a function of time, UT time. And you can see the storm onset right after UT6 hour. And the solid line here is the global average from the high-res model and the low-res model. So during storm time, you can see in general, the high-resolution model was giving like 30% more Joule heating than the low-res. And the geomagnetic storm, the energy, most of them comes in at high latitude. So this is to look at the northern hemisphere and the southern hemisphere, and a similar kind of relation holds there. And this is statistics looking at the distribution of the Joule heating during storm time. You can see that with high resolution, it shows a much larger dynamical range than the low resolution Joule heating. And so this is a bit more detailed view of the Joule heating. Joule heating is determined by mainly two things. One is the Patterson conductivity, and then the other is the differential of the E cross B drift and the zonal wind, the neutral wind in the perpendicular direction, perpendicular to the field line. So basically, I think of this as proportional to the electric field viewed from the neutral wind framework. So you can see that for Patterson conductivity and for the electric field, for both quantities, the high-resolution model was showing a much larger dynamical range than the regular resolution model. And if we look at the physical space, this is a profile, longitude profile of Joule heating at a specific latitude. This is 60 degrees south. And you see that there are regions where the high-resolution Joule heating can be much, much larger than the regular resolution results, and here too. And if we look at the Patterson conductivity and the electric field, we see that electric field, yes, there are some differences, and some places it is larger, the high-res results are larger, but the main cause of the difference, at least in these two regions we highlighted here, let me see, yes, here and here, the red circle and the yellow circle, the main cause is the differences in the Patterson conductivity. And the reason for that, if we look at the map, it becomes pretty clear. This is, let's see if it looks okay here. Yeah, it's fine. So this is electron density at the height we are just looking at, the upper thermosphere. And this is from high res and low res viewed from the South Pole. And you can see that the big difference is, first of all, there's the plasma density entrained from the low latitude, high latitude. It's much stronger in the high resolution simulation. And this is determined by the ionosphere convection, mainly the electric field. So you can see with the same driving, the transport can be much stronger in this high resolution model. This is so-called time of ionization, TOI. And so you can see it's much more enhanced in the high resolution model, and that's responsible for the very large Patterson conductivity we saw in the previous figure. Another interesting thing is in this region, this corresponds to the yellow circle we saw earlier, and this is this ionization is due to auroral precipitation, And again, even with the same auroral precipitation, we see a much larger response, a stronger ionization in the high-resolution model. And maybe I'll skip this one. This is looking at the density. This is a kind of early in the second part of the storm. And initially, it looks in general similar, but with if washed out a little bit, you see a little bit of the, you can see some mesoscale structures that's not shown up in the regular resolution model. But this becomes more clear in this figure Nick just showed. And there are two things we take notice here. One is that at this same altitude, this is a density viewed from North Pole and South Pole, and this is lower resolution, high resolution, lower resolution. And one of the big differences is that if we look at the peak values of the density perturbation, it becomes much larger in the low resolution model than in the high resolution model. And the other feature, of course, is the more mesoscale structures you see from the high resolution model. And so we look a little bit into this, what's causing this, differences in the density perturbation, which is very important, of course, for satellite drag, things like that. So one thing we've noticed is that the vertical wind response is very different. You can get much bigger vertical wind response in the high resolution models, and this is statistics. So you can see that the dynamical range again is much bigger. And this is really washed, not too bad here. Here it's really washed out. But you can see that by comparing the vertical wind perturbations in the upper thermosphere, the large-scale perturbations, the so-called MSTIDs, they still look quite similar. But in addition, you see a lot of, superposed on that, a lot of mesoscale structures. And also the peak values here is almost 3 times as big in the high-res model than the lower resolution model. So, so you can see that in response to this intense heat from the auroral heating, from the energy input, the high-resolution model shows a much bigger, stronger adjustment, both in terms of vertical wind, which the adiabatic cooling can act to offset the temperature adjustment and therefore reduce the peak values of both the temperature extremes and also the density extremes. And also the mesoscale waves also kind of facilitate a more effective radiation adjustment of the dynamical adjustment in this process. So that may be why we're seeing a much kind of less intense response in the thermosphere density. Okay, so that's our preliminary look. So basically, we're seeing that there's a clear scale or resolution dependence for energetics, dynamics, and transport. And we see all this. For the energetics, we see clear differences in the Joule heating. And for the transport, we see for the ionosphere, the plasma transport, very strong time of ionization in the high-resolution model. And also, we see very strong dynamical adjustment as a result of the storm. And as I mentioned earlier, there's no feedback here. There's no feedback interactions with magnetosphere, and that's something we would like to look in the future with a two-way coupling of the model. And we're mainly Kevin and Francis are working on the two-way coupling. Currently, it's a file-based two-way coupling. Thank you.
We have time for some questions if you have any. Otherwise, we can move on to the next speaker. Thank you. Which is Nick.
Okay. This is something I've been thinking about for the last 6 or so months when I've been trying to get our new vertical grid working with our new die core and trying to do our new everything, because we started with a very rough looking middle and upper atmosphere in Wacom with the SE die core. And when you start from very little, it's very hard to figure out where to go in terms of tuning things like gravity wave parameters in a model. So when you have a really mature model and something minor changes, maybe you kind of have an idea of what to do. But you know, we started with basically with a very primitive stratosphere, mesosphere, lower thermosphere in Wacom 7, and several folks in AMP, in the AMWG, you know, working group suggested, you know, it would be great if we could get some kind of white paper or internal knowledge sort of what the different gravity wave parameterizations do when you modify them in a reasonable range, and what biases they can adjust, and where they may have some unwanted effects that maybe you didn't realize. And so this talks really about trying to unravel some of that nonlinearity. And I will say it gets very complicated, and I don't think I remotely understand some of the stuff going on, but it's a good point of discussion for, I think, the community when we think about maybe even getting to the point of you know, digging into the gravity wave schemes and trying to change some things. So this is just a background on my perspective of the spectral element die core. I was one of these people who heard, you know, years ago that we were going to be moving from a regular Latlon grid to a cube sphere grid, and got very scared. But now I'm not so scared anymore. But I'll try to explain why. So you've heard a lot about the workhorse model. You know, it's intended to be the central configuration of CESM for future intercomparison projects and community use in science, and it's got a lot of good attributes for that. The quasi-uniform grid spacing means, you know, you don't have the grid crunch at the pole that you do with FE, which is nice. It supports all sorts of fun mesh refinements, and then it's got really good computational scaling and throughput, because the finite volume die core, there's a certain step where every core needs to see a full longitude strip. So you've really, that die core is really limited by how many cores you could bring to the task, whereas, I mean, with the SC die core, you can basically go up to a pretty crazy scaling limit of, you know, 1 core per column. I saw it as presenting interesting challenges, because a lot of our, you know, gravity wave schemes were developed on a grid that converges towards the pole, and I sort of thought, is this going to create a problem and change how the gravity wave scheme responds and generates, you know, frontal waves and things at the pole? There were some things actually in the scheme that tried to take care of that, but you never know. And it's a less diffusive model, which when you start getting into the upper atmosphere, like Hanli was just showing, maximum vertical velocities of hundreds of meters per second, right? As you get high up, you get big numbers that have to be, you know, dynamically and chemically damped away. And I will say in the tuning for a while, it was very difficult to get a handle on the spectral element die core in the mesosphere and lower thermosphere. But I think with a lot of Peter's help, it's really stable now. But yeah, I think the configuration presents unique benefits. So there's consistent vertical grid spacing throughout a good chunk of the atmosphere. Wacom now has the same boundary layer in troposphere and lower stratosphere as CAM, which I think is a step in the right direction. So when we're trying to understand differences between the models, we no longer have to scratch our heads and say, well, is it something in the troposphere or something like that? And I think it means that we can really focus on the middle atmosphere parts of tuning. And so I had no idea from a talk earlier today that there was a method already defined for how you can look at how parameters affect a model simulation. My attitude was, the way you do science is you hold everything constant and change one thing at a time. So if I wanted to know how to understand what the gravity wave parameters are doing to Wacom, I just needed to basically do that. And so I've gone through maybe 7 or 8 rounds of gravity wave tuning now, and it's really, really simple, and allows for a really rapid way to go from basically a Wacom with no mesopause and biases on the order of 50 to 60 Kelvin to now biases that are better than maybe the FV model. And so, you know, you start with some guesses of changes that may be needed, and then you do a bunch of runs with all the isolated changes. So maybe you change the convective gravity wave efficiency or the frontal wave efficiency, and then you do them all combined. And I think that this step is important because it lets you realize that a lot of these things are not additive, which I'll talk about. But what it also means is you get to see the individual effects of each of these parameters and understand, you know, them in isolation, and then how you can better create this all changes combined, you know, step in the future. And then you say, well, we have a best simulation, and if I combine that with what I've learned here, I can make a, you know, next guess and move on through. And so it's this sort of feedback loop of iterating through the gravity wave parameterizations. And you know, there's a few things that we change in the model. It's, you know, orographic gravity wave forcing, which is set by a couple different parameters. There's a convective gravity wave efficiency. There's a trigger function for the frontal wave. So when a strong temperature gradient in a weather front kicks off a frontal wave, there's a critical threshold. There's a sort of background wave forcing, and then there's a new thing I've been working on, which is adding a ability to change the spectrum width of the frontal wave. So basically the half width of the gravity wave spectrum in terms of phase speeds. And I'll talk about why this, despite having all these parameters, and there's even more, and why would you want to add this one? I'll talk about why I think, you know, this is actually a really useful parameter, especially for stuff in the MLT. So yeah. We do isolated changes, a combined change, and try to learn something from that. And that's been, you know, what we've been doing. If you've been coming to WACM meetings at all, it's sort of like that every week. And so I just wanted to use this talk to show the really complicated nature of the gravity wave tuning, and also, you know, sort of why it often feels like he takes 2 steps forward, 1 step back, and why these things aren't as simple as, oh, the vortex is strong, so I need to turn up the orographic forcing. And so I will show you this for DJF. So here's our control run. This is one of our spectral element sort of best candidates right now for tuning. And so it, you know, the biases relative to MERA 2, I showed them earlier in the session, but a lot of them are more of a meridional phasing than an absolute value of these jets. So this jet's actually pretty close to where it should be, for example, in the stratosphere and lower mesosphere. And so what I did is a couple simple experiments here where I just increased the orographic forcing, so the FGW, the efficiency, reduced the background frontal forcing, increased the frontal trigger threshold, narrow the spectrum half width, and then reduce the convective forcing. And these are roughly chosen to be equivalent in magnitude. And the way I arrived at that was basically just looking at what values of these parameters taken on during AMWG and whole atmosphere tuning, what parameter values have we used for FV, you know, WACM 4 versus WACM 6, tried to keep everything within that range of reasonable things you might do to the model. So in all of these, I have the gravity, the zonal mean zonal wind in the black lines here, and the shading shows you the response. And the thing that kind of is surprising that pops out really quickly, and I will say this model has a QBO right now that really tries to phase lock a lot with the annual cycle. So there's some of this that may change a bit, but one of the things that jumps out is all of these parameters project onto the tropical winds, and these are, you know, DJF tropical winds. There could be, again, some nonlinearities with the bad QBO that we have right now, which is getting better, but I mean, no one would expect that you change the orographic forcing in this model and you start to rapidly change the zonal wind at the equator at 10 hectopascals. And that's the thing, is when you do a lot of this tuning and you turn too many knobs at once, this is all missed in the fray. And so, yes, you can see, for example, because this is the region where you have a lot of orographic forcing in the northern hemisphere, right? Obviously, you increase the forcing and you start reducing the wind speed in the polar vortex. But it's not always the case, right? You're almost really inducing a shift in the winds, and you're weakening even the easterlies in the tropics, which is interesting, again. Same with the background. Frontal waves, it's a completely different structure, almost out of phase with the orographic forcing. So you can really decrease the whole vertical breadth of the jet speed in the vortex and in the mesosphere stratospheric jet. But again, it's really almost more like a vertical shift if you sort of draw your eye to this region. And so what I'm saying is these are really complicated parameters, and they're even more complicated than I thought. What's interesting is, again, I chose these all to roughly correspond to similar, what do I want to say, similar effects on the jet. I'm really focusing here on the polar vortex. But you can see that changing the frontal trigger is quite a bit different than in changing the background, frontal wave forcing. And then again, the convective changes aren't just limited to the tropics and the QBO. You've actually got, again, if you decrease the convective forcing, you actually also reduce the polar jet speed. And so what's interesting is a lot of these, some of them are out of phase, but some of them are also very much in phase with one another. And part of this is I'm sure that most of the convective forcing is here in the tropics, but if you change the winds in the tropics, you're going to have feedbacks on the meridional circulation that propagate out of the tropics. And the key I want to draw your attention to is the spectrum, because a lot of these have a lot of structure down here, but the spectrum changes have a lot of structure up here near the mesopause. And I'm just going to skip this for time because it's a similar story. It's something we can talk about when we talk about the biases in the southern hemisphere, but it's a little bit more complicated. I just want to show the temperature from all these runs in December versus SABRE. So SABRE's got coverage in the MLT. And what you can see is that variations in the gravity wave spectrum really project quickly onto variations in the mesopause. And if I show you before, again, in terms of the zonal mean zonal wind, it's much more targeted. This is a big blob. And so you can see that most of the spectrum changes really, really happen in the MLT, especially near the mesopause. And so I think adding this as a new tunable parameter is really useful because it gives us more target control of the mesopause without having to, muck up the rest of the atmosphere. And so just to conclude, I didn't show it, but adjusting gravity wave parameters is rarely additive because when you change the winds, you change the wave filtering for all other waves too, not just the other gravity waves, but also the resolved waves. And so there's not just issues with wave filtering, but there's also issues with, how that feeds back on the meridional circulation, how it moves momentum around because you change the background, angular momentum of the atmosphere, and then how that can feed back on chemistry and change your zonal mean climate. One of the important things with SE was making sure we had free atmosphere diffusion above club to really stabilize when we get regimes with really strong shear and we need to dissipate that quickly. What it's really doing is it's not a numerical technique, it really is modeling a lot of the turbulence you would see at finer scales in the middle and upper atmosphere. I think we've had a lunchtime discussion about this, but there's been a lot of talk about our vortex biases in the southern hemisphere and how it's too fast in the upper stratosphere. And I think some of that may be associated with horizontal propagation and how, I don't know how we tackle that. But I do think, again, the frontal wave spectrum half width is a really, really important tuning knob, especially for WACM and WACM-X to really try to nail the mesopause without having undue impacts lower down. Again, targeting that we'll have this in a white paper shortly to sort of explain, here's the effects of the parameters in different seasons and on chemistry even, so that it's very easy to say, I have this bias, let me match it to what parameter I need to think about. That also makes me think that there's probably some interesting way to go from this categorical state with all these maps of changes and back engineer from your biases to try to optimize your gravity wave schemes. Because if I go back just briefly, looking at this and trying to figure out how to adjust the northern hemisphere or southern hemisphere vortex, it's very tricky, but I think optimization routines would be a logical way to get there and how to combine changes in these parameters into something that reduces your biases. That's all I had.
Thank you, Nick. Any questions for Nick? Yep.
I know you've. Is this on?
I know you have started to think about chemistry. Have you looked at all at the polar chemistry in this tuning? Is it anywhere near?
No, I've looked at the polar temperatures, and I mean, yeah, it's kind of like it's a so part of my goal with those longer runs is to get a better handle on the chemistry and whether those small vortex biases are still causing problems or not. Haven't looked at ozone yet. The temperature's looking a lot better. Our best case has a temperature bias at most of like 1 Kelvin during the seasonal cycle in the lower stratosphere.
That's great if it's in the spring season anyway. So
we'll have to talk.
Any other question? Yeah. We have time, or then we can move the other to the discussion. But yeah.
Real quick, is that spectrum width parameter checked in? I mean, is it something we can?
I'll submit an issue. Yeah, but it should be a quick addition. Yeah.
Okay. Thanks again, Nick. And now we have Lin. She should be online. Is that correct?
Yeah.
Okay.
Can you
Go ahead,
confirm they
Lin.
can hear me all right and see my screen all right?
Mm-hmm.
Very cool. Okay, let's get started. Hello, everyone. My name is Ling Ling, and I'm a graduate student working with Professor Xiaohong Liu at Texas A&M University. I mean, thank you very much for having me. I'm so excited to present to you some of our most recent work. All right. On the right-hand side, a cartoon shows the climate impact of volcanic eruptions, and so the persistent stratospheric volcanic aerosol layers can cool the Earth's surface by scattering sunlight back to space and can warm the stratosphere by absorbing infrared radiation. And these are all better understood and are all associated with the deep red radiative effect. What is less explored and less understood is the indirect radiative effect of volcanic aerosols. So volcanic eruptions can produce volcanic ash particles and sulfur aerosols to the upper troposphere and lower stratosphere where cirrus cloud resides. And both aerosol types can trigger ice nucleation and might affect cirrus cloud microphysical property, as well as their optical properties. But so far, we just don't know to what extent these volcanic aerosols impact cirrus clouds. So to narrow our knowledge gap, we examine the response of cirrus cloud microphysics to volcanic aerosol emissions using both satellite observations and CESM2. So the objectives of this study are investigate how volcanic aerosols change the microphysical properties of cirrus cloud using satellite observations. And second, evaluate climate model simulations of volcanic aerosol effect on cirrus cloud against the satellite observations. So before we go into the result, a very quick overview of cirrus cloud formation mechanisms and the fundamentals of ice nucleation theory. So cirrus clouds are the ice clouds that reside in the upper troposphere and lower stratosphere. And there are two pathways for cirrus cloud formation, the homogeneous freezing and the heterogeneous freezing. So in the absence of ice nucleating particles or INPs, abundant soluble aerosol particles, such as liquid sulfate aerosols, can pick up water and freeze homogeneously to make a dense ice cloud. And this is homogeneous freezing. And on the other hand, in the presence of ice nucleating particles, ice crystals can form heterogeneously. But due to the INP scarcity, but only a few ice crystals can preferentially nucleate on the INPs. But I have to mention to you that volcanic ash particles are actually potent INPs according to laboratory measurements. And cirrus clouds forming through these two different pathways actually display very different microphysical properties. Due to homogeneous freezing, actually cirrus clouds contain numerous small ice crystals, but due to heterogeneous freezing, cirrus clouds actually contain fewer but larger ice crystals for a given amount of water vapor. And heterogeneous freezing usually occur at much lower supersaturation of water vapor with respect to ice, and homogeneous freezing usually require much higher supersaturation of water vapor. That means in the presence of IMPs, actually heterogeneous freezing usually occur preferentially and precedes homogeneous freezing, and homogeneous freezing might be suppressed by the preceding heterogeneous freezing. And cirrus clouds, the very different microphysical properties of cirrus clouds of two different origins might provide a critical clue for us to infer the dominant freezing mechanisms later. So with this knowledge, we started to investigate how volcanic aerosols impact cirrus cloud microphysics from a few more recent eruptions using satellite observations. So this slide, I show you the aerosol extinction profiles during the volcanic and the unperturbed period over northern hemisphere mid-latitude and the southern hemisphere mid-latitude. And there are three eruptions that substantially perturb the aerosol load in the upper troposphere and lower stratosphere. And they are the 2008 Kazatoshi eruption, 2009 Saratov eruption all over the northern hemisphere, and the 2015 Calco eruption over the southern hemisphere. And aerosol extinction in regions above 12 kilometers actually return to background levels without eruption and represent the pristine environment. Then we define the volcanic period versus the unperturbed period, between which we can contrast cirrus cloud microphysics. So the 2008 and 2009 volcanic periods are compared to the unperturbed baseline reference period from 2012 to 2016, and the study area for the 2008 Kazatoshi eruption is the latitude band of 50 to 60 degree north, and for 2009 Saratov eruption, the latitude band is 40 to 60 degree north. And for the 2015 case, it's compared to the 2007 to 2014 baseline period, and the study area is 40 to 60 degree south latitude bands. And there's one piece of important information for us to take care of before we look into the cirrus cloud microphysics, and that's the volcanic aerosol subtyping. So here, this slide, I show you the stratospheric aerosol subtyping occurrence. So we use the Calypso level 2 vertical feature mask, and I show you the occurrence frequencies of volcanic ash in panel A and sulfate in panel B during the volcanic versus the unperturbed period. So in panel A, immediately after eruptions of the 2008 Kazatoshi and 2009 Saratov in blue and red, the ash occurrences increase substantially when compared to the unperturbed background level. So based on these high ash occurrences, these two volcanic eruptions are classified as the ash-rich cases. On the other hand, for the 2015 Calco eruption, actually the ash occurrences are after the eruption are quite comparable to the background level. So it's the ash pool case. For the interest of time, I'm going to skip the discussion for the sulfate occurrence, but we can come back later. And finally, I show you the observed changes in the ice microphysics. So we use the data and ice retrievals to study the ice crystal number concentrations in cirrus cloud over the unperturbed and the volcanic period. So for all three cases. So the first, the left column, I show you the ice crystal number in log 10 scale as a function of month relative to the eruption month. So 0 is the eruption month, and the black and red line represent results from the unperturbed and the volcanic period. Solid and dashed lines are the mean and median, and the shading areas are the 1 standard deviation. And the right column, I show you the ice crystal number probability density function. So for the ash-rich scenario, actually we observe a quite substantial decrease in the ice crystal number by about 60 to 80% immediately after the eruption, and the decrease lasts for a few months after the eruption. And also we observe a clear shift of the NIPDF toward smaller values. And even though I don't show you the effective size of the ice crystal, but I want to let you know that the effective size increased from about 17 to 20 micrometers. So it's about 12% increase. All these results indicate the heterogeneous freezing on volcanic ash particles, suppressing homogeneous freezing. And this is the so-called negative to me effect, because we have a stronger aerosol load, but we have the decrease in ice crystal number concentration. On the other hand, for the ash pool scenario, actually we don't observe the same result as the ash rich scenario, but instead we find a slight increase in the ice crystal number by about 26%, but all the changes are within the 1 standard deviation, and the effective size remains largely unchanged. And this indicates the homogeneous freezing on the enhanced sulfate aerosols produced by the eruption. And based on our observational findings, we next examine the response of cirrus cloud microphysics to volcanic aerosol emissions in CSM2 WACOM 6. So we conduct 4 experiments for the 2 different eruptions. With and without volcanic forcing. So the first experiment, the 09 assay experiment, we used the historical emission file to account for the 2009 Sarah Trough volcanic SO2 emission. And the second experiment, the same as the first one, but we exclude the 2009 Sarah Trough volcanic SO2 emission. And the third experiment is the 15 CA experiment. So we use the SSP 245 emission. And the last experiment, I mean, the same as the third one, but we exclude the 2015 Calbuco volcanic SO2 emission. And note that now all the model simulations, we do not consider the volcanic ash emission. The only volcanic emission is the SO2 gas. And in the coming slides, I'm going to show you some preliminary results of our model simulations. So this slide, I show you the simulated meridional stratospheric aerosol optical depth as time and compared to the Calypso level 3 stratospheric aerosol profile observations. So in the lower left, the 09 SA experiment simulate an immediate increase in the SAOD. But compared to the observation, the 09 SA experiment actually simulate 2 strong AOD, and the SAOD peak lasts longer than observations show. But compared to the 09 SA of experiment, I think the 09 SA experiment actually at least capture the volcanic signature. Then we can wait to study the cloud signature after the 2009 Sarah Trough eruption. I record that this is the ash-rich case. So in the top 2 panel, I show you the time height cross-section of the simulated ice crystal number from 2 experiments with and without the volcanic forcing. In the bottom, I show you the difference between the 2 experiments, and we see an immediate increase in the ice crystal number, temporarily consistent with the SAOD increase, and it's about 20 to 120% increase. But note that for the ash-rich cases, actually observations show a decrease in the ice crystal number due to the heterogeneous freezing on volcanic ash particles suppressing homogeneous freezing. So we speculate that without considering volcanic ash particles, the models actually cannot reproduce what observations show. So it's imperative for us to incorporate volcanic ash particles into the model to simulate the impacts of the ash-rich eruptions on meteorological cloud properties. And next, for the 2015 Calbuco eruption, in the lower left, the 15 CA case actually, reproduce the SAOD distributions reasonably well when compared to observation regarding the location, the timing, and the magnitude of the SAOD peak, as well as the transport toward higher latitude. And finally, the ice crystal number changes after the 2015 Calbuco eruption. And record that this is the ash pool case. So in the bottom the differences panel actually show we see a increase in the ice crystal number a few months after the eruption, and that's quite temporally consistent with the SOD change, and it's about 20 to 50% increase. And observations show about 26% increase in the ice crystal number after the ash pool case. So, I mean, for the ash pool eruptions, probably the absence of the volcanic ash emissions might be okay, and the model results are just quite comparable with the observation. And finally, a quick summary and discussion. And satellite observations actually show a substantial decrease in the ice crystal number for the ash-rich case, and that's because heterogeneous ice nucleation of volcanic ash particles can suppress the homogeneous freezing and of sulfate to reduce the total number of ice crystals. And this is the so-called negative 2-me effect. And for the ash pool case, instead we find a slight increase in the ice crystal number. And that's because the enhanced homogeneous freezing of sulfate aerosols, but with very weak sensitivity to the sulfate aerosol number concentration and size. And our model simulated the volcanic aerosol indirect effect from the 2015 case, the ash pool case, I mean, collectively well agree with the observations. But for the ash-rich cases, the model results just disagree with the observations due to the absence of the volcanic ash particles. And that motivates us to incorporate volcanic ash particles into global climate models as INPs, I mean, ice nucleating particles, to account for the mixing ice nucleation mechanisms and estimate the cloud-related forcing changes in response to the ash-rich eruptions. And thank you very much for attention.
Thank you, Lynn. I actually have a question. Are you using here MEM4? Is this WACAM 6 with MEM4, the model aerosol microphysics? Yeah.
Yes.
So we do have some studies that we published last year showing that since these are all internally mixed, the aerosols, basically the reason why you see this increase is just because the sulfate that is coming down from the stratosphere to the troposphere is changing the size of aerosols in the troposphere. So it's not a physical effect, the one you see in CSM if you're using MEM4. If you reach out, I can point you out to the research, and this is probably why you're observing such a big increase from the moment that from a moment that you have more aerosol optical depth in the stratosphere. But yeah.
Yeah, thank you.
Okay, sorry. If anyone has questions that are not actually observations like mine.
Great talk. Maybe it's just a minor detail. I noticed there is a time gap between the eruption and the onset of the peaks of the change of Ni. Could you explain or comment on this?
You mean
time gap? Yeah, between the time of the eruption of the volcanic and the really onset of the peak value from the cloud signature over there.
Yeah, I think here the increase of ice crystal number, actually we see that it's quite consistent with the increase of the SAOD. So we can come back to see actually the AOD peak actually also lag a few months after the eruption. So this is one thing we don't know for sure currently, but we are speculating that probably is associated with the timing of the eruption. So it erupts in April in the southern hemisphere. So it's almost entering the winter time of the southern hemisphere. So we're thinking about if it is lacking some hydroxyl radical in the southern hemisphere winter time, that can make the oxidation of the SO2, slower. But right, this is the good question, but we don't know for sure right now.
Okay, any other questions, or we can also open up the floor for discussions. We have 20 minutes before the break, if anybody has any observations about any of the talks or anything. Or we can just have a very long break.
Yeah, I mean, it's discussion time. there's all sorts of groups in the room. There's people from AMWG and CZWG. We've got 3 different vertical level scheme models, and this could be an app research and development needs. It's sort of the floor is open to the community. We don't have anything prepared today.
Mon?
Your talk, you mentioned that you do the next step is the TSM at was 1 degree for webcam, 132 levels. And I wonder if you had already figured out, tested it in terms of timing, how much it costs. Because the 2 degree, I think, did you say it was 17 or 70?
7 conservatively. I've had a number of configurations that are down more towards like 6,000.
Okay, so that's quite reasonable to run. And you're thinking that the 2 degree is a reasonable model for stratospheric processes to be used, since we had a paper on that it showed that the climate is reasonable. So going up, I mean, what's the maximum cost that we can expect for webcam when it's fully TSMLT 1 degree?
I mean, I think you do 4 times NE16 and then another 1.5 times for TSMLT. So we're talking somewhere in the 36 to 40,000 core hours range for 1 degree TSMLT. But I think, yeah, I mean, like you said, so the folks here that don't know, there's a paper still in review at James looking at some Wacom 6 configurations at, there's the TSMLT runs at 1 degree that were done for CMIP, and then there was a series of runs done with the MA middle atmosphere chemistry for, at 1 degree, and then also some 2 degree middle atmosphere runs. And so we had the ability to look at what's the effect of going to simplified chemistry, and then what's the effect of going to coarser resolution. And the upshot for the troposphere and climate sensitivity and stuff like that is there's basically no changes across those model simulations that are material. There are differences, especially in I think the tuning between 2 degree and 1 degree in those runs. But I think the intention here is based on the workhorse configuration, trying to, basically integrate that higher boundary layer and troposphere resolution to the model. We sort of said we know we're going to go we're going to maintain a slightly higher resolution through the stratosphere and mesosphere, so we want to always carry at least some kind of economical configuration. And going to 2 degrees seemed reasonable with MA because, like you said, for a lot of things, especially in the stratosphere, you may not necessarily need 1 degree to get that may, the trade-off of almost a factor of 10 increase in core hours may not be needed. And so, I think we'll take a look at 1 degree. I have not touched it since this whole HP diffusion thing. I think that was important to get figured out because the model was almost like maybe unworkable before that for a lot of the tuning cases we had. So, yeah.
And sorry, Doug, I just wanted to add as a tiny thing from the point of view of the community, a factor of 10 really matters a lot if you have computational proposals that are not as big as what Anchor can do. And so having a version that is usable and quite fast is actually quite important.
Yeah, I just wanted to speak too, for the 2 degree, 130 some levels, you have a pretty nice QBO in that, right?
We did. We wrecked it? We wrecked it recently. But because we had it, it should be no problem getting it back. It looked really good a month ago, and then, I won't use the royal we anymore. I wrecked it. No, I think it's the HP diffusion. Well, okay. Yeah. You can tell a lot of those gravity wave parameters oddly project into the tropics. and I don't, it sounds like maybe this was not a thing with FV. I don't know what that means necessarily or not, but that has presented some issues. So every time I've tried to fix the mesopause, I screw up the QBO basically. So that was part of the spectrum motivation. But yeah, we're definitely going to have to go with very different parameters than the mid-top model for the QBO. And I think that maybe because we are continuing, we have that slower roll off of the vertical spacing with height sort of through the initiation region of the QBO. And I just have a feeling that that is playing around with the parameter settings we use. So I think we thought maybe we'd be able to copy a lot of the stuff that the mid-top model had for stuff like the QBO, and I think it's just turning out that's not the case. So it's complicated, but it should be easy to fix.
Promise?
No.
Anybody else?
That on the QBO tuning. Quite a while ago, maybe almost 10 years ago, we had a visitor working on inertial gravity wave parameterization. I remember at that time when we tuned it, it seems to made a difference with whether it's an F case or a B case. With a B case, with F case, it seems that at least in his case, in his parameterization, it always tend to show a phase lock at 2 years. But with a B case, you don't have a phase lock. I'm not sure if in your tuning, have you ever tried B case tuning?
Yeah, not yet. And I know Yaga's been talking about this because, yeah, there's differences when you also do like the future climate simulations, whether you use F or B case, what happens to the QBO and when. Yeah, no, this is only with F case right now. And that's a good point to think about for these longer simulations. I think from what I took from the stuff she's been involved with, yeah, you kind of maybe have to go to an even different parameter set sometimes when you go to a B case, actually, for stuff like the QBO. So that's something to keep in mind here, that this is all F case stuff, yeah.
I guess we can just all go for coffee and reconvene at 3:30.
Thanks, everyone.
And there is this weird pointer that basically,
I see that,
I
yeah.
don't know how it works. Like, I'm trying to figure out technologically how it works, but it does a bit. And it's not point, you don't have to point there.
Yeah.
You can point magically at the screen and it works.
Okay. All right. Sounds good.
Yeah, how does it do that? Did you? But that's fine. We have plenty of time and proceed the discussion.
All right, everyone, welcome to the second session of the whole atmosphere working group. This has some more applied talks, and our first speaker is Dan, who's going to talk about CESM and solar radiation modification experiments.
Yep, thank you, Nick. So yeah, my talk is actually not going to have that many results after mine, but I wanted to offer more like of a reflection in needs and also where are we going with CSM in particular and climate modeling in general and climate intervention or solar radiation modification or whatever you want to call it. So I'll give a little bit of a background. I'm sorry if you've heard this before already, but it's always useful for everyone. Well, the remote was supposed to work. Okay, now it does. So the first thing that I want to say is that if you know of anyone that is interested in a grad program or PhD students looking for a postdoc, I'm building my new lab at Cornell as an assistant professor, so send them my way. Woo, yes. So why do we talk about climate intervention? And what do we use climate modeling for, right? So you're all familiar with this figure. You see on the left, the IPCC results for the SSP scenario, so how much warming there's gonna be, for how much, amounts of CO2 emissions, and then on the right, that's not nice, and then on the right you can see the global mean temperature change and the amber diagrams that basically say how much risk is connected to how much further warming. Now, this is mostly modeling result. These are results from a lot of different models, and they tell us not just how much risk there is, and so they don't just inform climate policy, but in a sense, climate models are also used right now for adaptation purposes. So what are we expecting with future climate change levels? And this is why we heard yesterday a lot in the ultra high res. There is a bit of adaptation that is starting to creep in, and what do we need to expect with future warming? These in a way is where climate intervention comes in. This slide is from the National Academy of Science report. solar radiation modification or climate intervention or climate engineering defined as a way to deliberately modify the Earth's climate through reflecting a bit of the incoming solar radiation, cool the planet a little bit, and perhaps mitigate or ameliorate some of the damages from climate change. These would just be a temporary thing, just because the CO2 would still be there. Eventually, it would be too much to cover up all the warming, so it can be considered in a way as a temporary measure. This morning in the atmospheric session, you've heard a bit about marine cloud branding. I'm only going to focus today, since we're at the welcome session, on stratospheric aerosol injection. So basically, the idea coming from volcanic eruptions, what if you added some sulfate to the stratosphere artificially to reflect some of the incoming solar radiation? We know from Pinatubo that we would cool the planet, but what about the surface impact and what about all the other impacts? So again, the main idea is you have SO2. Once you put it in the stratosphere, just like it happens for the troposphere, except the lifetime is much higher, it would oxidize, it would react, it would form H2SO4. And finally, from H2SO4, you would get aerosols through coagulation, nucleation, and condensations. Those are the processes that determine, and sedimentation, those are the processes that determine the size of these aerosols. Why does the size matter? For two main reasons. First of all, these aerosols scatter solar radiation. Here you can see some, on the right, you can see some tests that were done in a paper by John Dijkma et al., basically showing in blue the top of atmosphere solar spectrum, and in yellow the shortwave real part of the reflective index. So basically saying how much these sulfate particles of a certain size distribution, they can scatter solar radiation. The smaller they are, if they are around the optical window, around 0.2, 0.4, the more they can scatter solar radiation. That's not the only thing that the aerosols do. For every real part, almost always there's an imaginary part, which indicates the absorption of solar radiation and of planetary radiation in a way. Here you can see for small particles, this absorption is small, which means that the connected stratospheric heating can be small. If this size distribution is too big, these particles then are not just inefficient scatterer, but they also absorb more. And of course, the other thing is that they also affect chemistry, in particularly ozone chemistry in the stratosphere. So these are the main thing. And again, the thing that I want to remark is that all kind of studies that are done thinking about climate interventions are never assuming that you can just continue emitting business as usual and cover up all the warming with climate intervention, but that together with cutting emissions and perhaps CDR, if we are overshooting targets like the Paris Agreement one might eventually want to consider some other forms that might help us stay at 1.5 or 2 degrees or whatever we decide is a safe threshold. But we need to do an assessment for this. Basically, we need to figure out whether it would be preferable to maybe overshoot. We don't know. The Paris Agreement is legally binding, but the 1.5 threshold is just, it doesn't mean, in the Ember diagram figure that I showed before, it's pretty clear. It doesn't mean that at 1.6, we're going to have the apocalypse or the turning back. Risks might increase, but it would be completely up to the world to decide whether we want to overshoot or whether it might make sense to have a little bit of solar geoengineering, reducing some of the worst impacts. And this, in a way, it's what an assessment would look like, right? It's in a way the same thing as for climate change, trying to figure out what these uncertainty bars are. So are the climate impacts going to be less or more with climate intervention than without it? And when we talk about assessments, we're not talking about things that haven't happened yet. We are, as a scientific community, we've already been asked to do some form of SAI assessment. In particular, the WMO assessment that just came out at the beginning of this year, the parties to the Montreal Protocol explicitly asked the scientific community to talk about what would be the potential impact of stratospheric aerosol intervention on the ozone layer. This figure is from a paper that we published in 2021, and it was also in the WMO assessment with Simone, looking at one of the parameters that I talked to you about. This is about stratospheric processes because it's about the WMO report, so we're looking at stratospheric heating. And these are 6 models, well, 7 considering 2 versions of CSM, that were asked to that performed climate intervention simulations, except that the main purpose was these are for the IPCC report, that was for part of scenario MIP. So the main purpose, in a way, was these models are tuned in a way to get the best match to the surface climate and what happens for future climate change in terms of CO2. So these models might not be, in a way, fit for purpose for stratospheric aerosol intervention studies, and this is one of the ways in we can see that. If we look at how much stratospheric heating in the lower stratosphere, in the lower tropical stratosphere, these models observe, it varies a lot between models because the size distribution of the aerosols is much different because some models have interactive chemistry, some models have interactive aerosols, some models don't. So for a similar amount of optical depth, so if we look just at 0.1 micron, it would already, a global AOD, would already be a bit alpha degree probably of cooling. You can see that some models like CSM, they see a relatively moderate amount of warming. Some models like the MPI model see over 6. And when we go to even higher AODs, we can see that these increases a lot, which means that then the chemical changes would be higher, the dynamical changes would be higher. But the point that I was making before is that these models were mainly, they were asked to do these SAI experiments, mainly looking at global mean temperature. So if we look at this figure, we can see what happens to the global mean temperatures, right? So the green line is the underlying higher emission scenario, SSP 585. The purple line is SSP 245, and the red one is the SAI experiment. So if one just looked at this one, at this figure, they could say, well, it looks like SAI is doing a great job, right? It's cooling the planet exactly as we want it to be, and that's it. Of course, that's not what it means to do an SAI assessment, and in particular, the thing that this figure is hiding is that most of the uncertainties, here you can see that the uncertainties related to the climate sensitivity are gone, right? Different models see different amount of warming from SSP 585 and 245, but this is hidden in a way by deciding, we can determine how much SO2 to inject, and so in a way, this climate sensitivity part is hidden. And this is what in a way, the part that is hidden from that figure, that the part where the models really differ in if we inject the SO2 in all the models in the same way, the size the distribution, the latitudinal distribution, the amount of SO2 that we need for that distribution, they differ a lot between models. Mainly, again, part of the reason why that is really because these models, not all models have a very well-developed stratosphere, not all models have interactive chemistry or interactive aerosols, so these are all things that matter. At Anchor, with CSM and with WACAM in particular, we've done a lot of stuff. Yesterday, you heard Yaga talk about ARISE. There's going to be more talks later this afternoon about it. In general, trying to approach this problem also looking at a model that has pretty good stratospheric aerosols, pretty good stratospheric chemistry and surface climate, and looking at larger ensemble and trying to, and the community has been using these a lot. Now, what I want to get at now is, well, and my point is that we should really stop a second and think, what questions is SAI supposed to answer, and what questions are we supposed to answer, SAI research supposed to answer, I guess, and what questions should we answer as a community? And in a way, what I'm arguing is that, unlike for climate change, where the problem is you have a CO2, you warm the planet, and then you look at the impacts, not that simple, but for the sake of argument, with something like SAI, the problem can really be separated into like at least 3 stages. So the first one is asking if we put SO2 or other precursors in the stratosphere, whatever you inject, what happens to the size distribution, what happens to the mixing, to the latitudinal transport. So something that, these are all stratospheric processes. And then we have a second problem. Once we have an aerosol layer, whatever the size distribution is, whatever the distribution latitudinally is, this will have some radiative response. Top of atmosphere radiative forcing, long wave absorption, dynamical changes because of the long wave absorptions. And finally, we have the third part of the problem. Once you have a certain radiative forcing, this would produce a certain amount of cooling. But in a way, and unlike climate change, maybe, we should start thinking of the fact that these 3 processes can be a bit more clearly separated. And so maybe that we need to think about them a bit more separately. So the 3 questions are, what are the specific changes that we can have to stratospheric composition and dynamics if we add this aerosol layer? And for something like that, we would need a model like WACAM, like what we use now, right? High top, so good representation of stratospheric aerosols. Maybe for something like this, it would be incredibly important to have better aerosol representation. So maybe MAM, the model aerosol approach, is not enough, and maybe we would need to have something like KARMA. We need good chemistry, good representation of things like QBO and polar vortex. And maybe this is important if the entity that asks us to do an assessment as a scientific community is something like the WMO that cares about stratospheric ozone. Maybe we want to do something like what Scenario MIP does. So basically explore future scenarios and how many different scenarios can we have. This is what, again, the SSP framework for climate change does. In that case, maybe we don't need that much complexity in a lot of stuff. Maybe we need a fast, and I say fast because really the community cannot afford to run incredibly expensive models, not all the time. So maybe we need a fast but reliable model that can allow us to explore a space of potential policy relevant scenarios. So where are we injecting, what time of the year, because that impacts something like the WMO report for CFCs. And in a way, it's a space that is much larger. We've talked, Yaga showed this figure yesterday. Here, we're not just talking about how much CO2 we put, but also how much we decide to cool. Do we cool to 1.5, to 1, to 0.5? Do we start in 2035, 2045? Different injection strategies, potential termination, interruptions, volcanic. So there's a lot of space to explore. And maybe a model with the full complexity of WACAM maybe is not needed. I'm not saying I have the answer, but just that I think we should actually be thinking about a bit more. And finally, eventually, for something like the IPCC report, you need to be more explicit about specific surface changes, even if it cools globally. We don't really have a doubt that SAI would cool globally, but we are large uncertainties over the specific changes to climatic features, like the monsoon season. And that's what eventually people want to know. People are a lot more interested about that. For this, we might need a higher resolution model, something like the discussion we had yesterday about ultra high resolution. That might be what we need. We might need incredibly large ensembles to capture a certain signal. Maybe we can start thinking about potential S2S setups that allow us to understand the detectability of someone actually doing this and intervening in the climate. And this so might be targeted more to IPCC purposes. So, just to conclude, and then I'll be done. There is no doubt that up to now, CSM WACAM has done a lot of this work that I talked about. What we showed with the WMO report was actually the problem that we had was that most of the results were done with just 1 or 2 models. That's not good. That's not good for a lot of reasons, for robustness and for trust. But CSM WACAM has done a lot of this work, and it should continue doing this. Also, it's in the anchor strategic plan to study more climate intervention, so just keeping it out there. And definitely we need more people to look at this. And the point with all of this is that for me, as part of the community needs WACAM. We're always going to need something like WACAM. If, as I was saying to Nick before, if WACAM tomorrow disappeared, I would have a lot of problem getting tenure eventually because I would have to figure out how to do my research in other ways, and it would be a big problem. And I really like WACAM. It's a really good model. And again, this is in the strategic plan from Anchor, so really, this is not something we're just doing for the fun of it, but because actually we're starting to be asked to do these kind of assessments. But we should really think more of whether we actually need a model that does it all. And can one model do it all? Should one model do it all? Do we need to, do we need to maybe go back? For now, we've all appreciated the ability of WACAM to do both surface climate and stratospheric aerosols, but do we need to do everything at the same time? I don't think we have the answer yet, but I think we should really be having this discussion. And if not, what should we focus on more? What should maybe WACAM be focused more on this? And if yes, if someone says, yes, we must have a model that does everything from the land carbon cycle to stratospheric chemistry, we need to do it all in one large ensemble. Cool, then what resources does Anchor need to make sure that WACAM is up to the task? And what can we do also as a community to make sure that we can all support this? So this is it for me. Thank you.
So if there were one thing that you would want to see in WACAM that's not there, what would it be?
What? Sorry, I didn't get the last
If there were one thing or two things that you would like to see in WACAM, what would it be? What kind of improvement?
So this is a great question. And again, I really think that we should stop a second and think what are the biggest priorities, right? And so I definitely think that on one hand, a faster version of the model that allows us to explore reliably the space of possible injection strategies that would be useful for a lot of reasons. On the other hand, one of the, in a way, main criticisms of when Simone was leading the WMO chapter report on SAI was about, for instance, we haven't looked at all about what would happen. We haven't looked that much over what would happen over the Arctic ozone depletion, right? And so I think we should start doing that a lot more. And so being sure that we can have reliable a much more robust answer when we ask, like, can we trust the model when it comes to stratospheric aerosol or polar ozone depletion? So I think, and I would prioritize that over maybe going ultra high resolution. I'll just.
Please turn on your mic.
How? And do I just change this? Okay. Okay, hi everyone. I'm Eva, I'm a research scientist at NOAA, and I'm going to talk about, follow on with the topic of stratospheric aerosol injection research. Okay, so Dan already gave a great intro to what stratospheric aerosol injection is and some of the issues surrounding modeling it, so I'm just basically going to pick off where he left off and go straight to the point of my presentation. So two of the specific changes in stratospheric composition and dynamics that Dan mentioned that recently received a lot of attention in this SAI context has been the potential impacts of SAI on stratospheric ozone depletion, on evolution of stratospheric ozone, and also on the extratropical modes of variability and surface climate. So does the thing work? No, it doesn't. My screen? No. Whoa, that's so cool. Okay, so many studies by now pointed out that because the aerosols are not inert, they absorb solar and terrestrial radiation. That leads to strengthening of stratospheric jets on both hemispheres. And the reason why it matters that in the northern hemisphere during dynamically active seasons, so DJF, this stratospheric response can propagate down to the surface and lead to what we call the positive phase of the North Atlantic oscillation. So this pattern of changes in sea level pressure consisting of decreasing sea level pressure in the Arctic and increasing sea level pressure in the mid-latitudes. And this is in turn important for determining winter temperature and precipitation patterns in Europe and North America. Okay, so most of the SAI studies that look at some of these changes use by far only a single, usually high-end greenhouse gas emission scenario, and as such, they needed for a large amount of SO2 to offset the strong greenhouse gas-induced warming. And also, many of those studies, or by far most of the previous studies, used only a single location or a single set of location for SO2 injection. And it is still not very well understood how would this side effect differ, if at all, if a different SAI strategy was considered instead. Okay, so as we heard from Yaga on Monday, and also Dan mentioned it in his presentation, NCAR has recently produced a large ensemble of SAI simulations called ARISE SAI. And the simulation used CESM2 in its coupled to WACAM 6 in its workhorse TSMLT chemistry version, so the comprehensive tropospheric, stratospheric, mesospheric, and lower thermospheric chemistry. And in this case, also coupled to interactive aerosols and ocean models. And in these simulations, SO2 is injected at 4 of equatorial locations in the lowest stratosphere. And there's a feedback algorithm that injects magnitudes in order to maintain global mean surface temperature. And also these large-scale horizontal temperature gradients at the quasi at the levels corresponding to quasi 1.5 Kelvin above pre-industrial conditions. So what I want to talk about, today are the CSM2 simulations that we carried out recently at Cornell using versions that are very similar, to the NCAR's ARISE simulations, but that use the middle atmosphere configuration of CSM2 WACAM. So the middle atmosphere version is very similar to TSMLT, but it omits most of the species and reactions that are mainly matter in the troposphere. And as such, it does produce a very similar climatology and variability to the full chemistry version. This is shown in the plot here. There are some differences, mainly in the background tropospheric aerosols, but I'm not going to talk about it here. What I do want to point out is, as many of you know, running tropospheric chemistry is expensive. And so not including tropospheric chemistry saves us around 35% of computational costs compared to the full TSMLT chemistry version. And the saving of the computational cost allow us to explore some of the uncertainty space of SAI responses that Dan mentioned in his previous talk. Okay, so first I want to focus on the role of SAI scenario, so loosely how much SO2 do we inject and how much cooling is to be achieved. So we've got 3 SAI simulations that are very similar to the ARISE simulation that I mentioned before, but that differ in terms of how much global mean cooling those simulations achieve. So first we've got the simulation that is almost identical to the ARISE simulation in that we get the stabilization of the global mean, wrong. So that we've got the stabilization of the global mean surface temperature at around 1.5 Kelvin above pre-industrial conditions. And then we've got two additional simulations that achieve further cooling. So we've got a simulation that maintains global mean surface temperature at 1 Kelvin above pre-industrial, and a simulation that maintains global mean surface temperature and half a Kelvin above pre-industrial conditions. Okay, so some of the questions, scientific questions that we managed to explore with this sort of like free temperature target setup is we started thinking of what the SAI response actually is. So one of the common questions people ask is, once you have your SAI simulations, what exactly do you compare that against? So, and what we figure out is that the answer really depends on the question, the particular question that is being asked. So the plot here shows the matrix of changes in surface temperature, and the rows are for the 4 simulations. So we've got the SSP2 simulation without the SAI, and then we've got the free SAI simulations, and then the columns are the different baseline wow, this is so weird. And the columns are different baseline periods for comparison against. So first we can compare the results of SAI simulations against the same future period of the corresponding greenhouse gas simulation without SAI. So this is shown in the first column. And what we're looking at is basically this direct cooling response from SAI that is important to illustrate what kind of force change, global mean response, is being mitigated. We can also compare against the quasi-present day baseline period. So this is shown in the second column. And in this case, we are looking at basically the impacts of SAI compared to present day. And this is in turn important for policy perspective. And we can also look at the, compare the SAI responses against the each of the SAI responses against a period in the past that has the same global mean surface temperature, and this is shown in the diagonal panels here. And in this case, we are looking at basically the response of SAI that results from this imperfect compensation of the greenhouse gas effect. So you can also think of it as some kind of like a side effect of stratospheric aerosol injection. So the point I'm trying to make with all of that is that really the choice of the baseline period can really strongly influence the message that one wants to put across, and therefore needs to be considered accordingly. Okay, so another aspect that the use of the simulations, So the other aspect that the use of this set of simulations with 3 different temperature targets allow us to explore in detail is the linearity of the response. So it shouldn't come as a surprise that many of these direct surface responses, direct radiative surface responses can be expected to be roughly proportional to the magnitude of SAI. However, an interesting question is what happens to the extratropical modes of variability and dynamics in general, which are more complex. And what we found out in this case, in these simulations, in the high latitude dynamical responses are, however, not linear. So this is shown on the plot here, which shows DJF changes in zonal winds and northern hemisphere sea level pressure in those 3 sets of SAI simulations. So first, in the stratosphere, you see strengthening of the In the stratosphere, we see strengthening of the jets in both hemispheres that become stronger as we go from the low SAI case to the high SAI case on the right-hand side. But really, the important thing is that in the northern hemisphere, the stratospheric westerly response only manages to propagate down to the surface in this larger SAI simulation on the right-hand side. And this gives us this pattern of changes in sea level pressure that is basically a positive phase of the North Atlantic Oscillation. Remember, that has impacts for winter temperature and precipitation in Europe and America. And so basically that indicates a much stronger coupling in the between the stratosphere and the troposphere in this larger SAI case. And this is also shown on the plot on the right-hand side, where I've got the change in the NAO index correlated versus the change in the stratospheric jet in the northern hemisphere. And I'm doing it for each of the ensemble member and each of the in each of the simulation. And you see that this sort of the relationship, the linear relationship between the NAO index and the stratospheric jet response really emerges for the strongest SAI simulation, indicating nonlinear effects on the stratosphere to troposphere coupling that needs to be explored in more detail. Okay, so another bit of the puzzle, another bit of the puzzle that we managed to explore with the use of the middle atmosphere chemistry scheme is the role of the SAI strategy. So loosely, where and when do we inject sulfate aerosol precursors? So in this case, we've got 4 SAI simulations, each with different SAI strategy, but all achieving the same global mean surface temperature. So we've got an We've got an equatorial strategy that ejects SO2 at the equator in the lowest stratosphere year round. We've got 2 pairs of simulations that inject SO2 symmetrically at either 50 degrees north and south and 30 degrees north and south, again year-round in the tropical lower stratosphere. And then we've got what I'm going to be referring as the polar injection strategy, where we inject SO2 only in the high latitudes and only in the spring in each hemisphere. So March, April, May for the 60 degrees north, and September, October, November for 60 degrees south. Okay, so one interesting result that came out of it is that despite achieving the same global mean surface temperature in those 4 SAI strategies, those SAI strategies give rise to contrastingly different impacts on stratospheric temperature circulation. So this is shown on the plot on the top. We've got yearly mean changes in temperature for the equatorial strategy and the polar strategy, so those 2 extreme ends of the strategy space. And on the right-hand side, I've got the measure of changes in tropical lower stratospheric temperatures across the 4 strategies. We see a very strong dependence of the simulated warming in the tropical lower stratosphere in each of the strategy. And then this in turn significantly impact the simulated stratospheric dynamical response. So at the bottom, we've got yearly mean changes in zonal winds, again for the equatorial strategy, the polar strategy, and then on the right-hand side, I've got the measure of changes in the strength of the northern hemisphere and southern hemisphere polar vortex in the stratosphere. Again, we see the strong dependence, very strong dependence of the simulated strengthening of the jet on the SAI strategy. Now, the reason why this matters is that differences in stratospheric circulation responses will give rise to different impacts on the surface climate. So here I've got DJF changes in sea level pressure, again for the equatorial strategy and the polar strategy, and on the right-hand side, I've got the changes in the NAO index. So basically for the equatorial strategy, again, we've got these changes in sea level pressure that corresponds to the positive phase of the North Atlantic Oscillation. And remember, this is this NAO, the positive NAO response is the response that's been previously pointed out frequently in literature as a kind of like unavoidable side effect of geoengineering using absorptive sulfate aerosols. However, what we find that really this response is really strongly strategy dependent. So like if you go to the 50 north and 50 south injection, the positive NAO response becomes much weaker. And then if you go to the higher latitude injections, the positive NAO response basically goes away. And all of that really highlights that some of the side effects of SAI might be potentially reduced upon the design of an optimal SAI strategy. And I don't want to talk into details because I don't really have time, and also it's not that it's beyond the scope of this talk, but really the differences in the distribution of stratospheric aerosols in those different SAI strategies and the difference in the resulting temperature and circulation responses across those strategies, they will give rise to different impacts on stratospheric ozone. And this is both for the stratospheric ozone concentration locally, again, this is the changes in ozone in the equatorial and the polar strategy, and this is also going to be the case when we integrate the ozone responses across the depth of the atmosphere. So on the right-hand side, I've got the changes in total ozone columns in the 4 strategies, and we see large differences in the ozone columns in most of the globe. And really the point I'm trying to make is that this another aspect of the SAI impacts that receives lots of attention, the potential impacts of SAI on stratospheric ozone recovery, it really does strongly depend on the SAI strategy and therefore needs to be studied in a broader SAI strategy dimension. Okay, so I talk about stratospheric ozone injection, how it alters stratospheric and tropospheric temperatures with implications for stratospheric ozone, large-scale circulation, and ultimately surface climate. If you remember nothing else from my talk, do remember that the response is strongly dependent on the magnitude of SAI and also on the location and season of SAI. And really more research is needed to understand the atmospheric and climate response to SAI and its dependence on the SAI scenario, on the SAI strategy and scenario. And really, I demonstrated how the use of cheaper middle atmosphere configuration of CESM2 has allowed us to explore some of the uncertainty space of potential SAI responses. And just to say, we have a few papers with some of those results if you're interested. And with that, I just want to thank you for your attention.
Lot to digest there, but
sorry.
On slide
I do that, I'm sorry.
On slide 6, bottom right, it looked to me that there was a ENSO response.
Yes, ENSO and AMOC
response. To the stratospheric change in heating.
Yes.
That's robust?
I mean, ENSO response has been studied in the SAI context. The problem is you need long simulations, but like, yes, it does seem like you get a positive ENSO response from SAI, presumably through the impacts of Walker circulation. It could also be like partially because you don't compensate. Well, you get the ENSO response under climate change. So it's the question, does your SAI mitigates fully the answer response due to climate change alone? So it's presumably the combination both of the SAI impacts on the worker circulation and also the fact that the climate change response is not mitigated.
Okay, thank you, Eva. There's, again, going to be time for discussion. So the next talk is going to be online and also is a recorded video, so no questions.
Hi, I'm Matthew Henry. I'll be sharing some research on stratospheric aerosol injection modeling. So this is work I'm doing at the University of Exeter. I'm funded jointly by NERC and Silver Lining. And these are all my collaborators, both from Exeter and the US. I'm very thankful to them for the help in doing this research. So we are looking at stratospheric aerosol injection modeling because our projected emissions aren't in line to avoid 1.5 or 2 degree of warming. So we are looking at different ways we could voluntarily, intentionally cool the climate. So there are different ways that people are looking at doing this. One of them is marine cloud brightening, where we brighten clouds that hang above the ocean. The other is thinning clouds, high clouds that act mainly on the long wave side of things, and that would allow more heat to escape to space. But the way that I will be focusing on in this work is stratospheric aerosol injection, where we add, for example, sulfates in the stratosphere, and that would create aerosols which reflect a bit of sunlight and cool the planet. So there have been some previous model intercomparisons of doing stratospheric aerosol injection, but they mainly used equatorial injection, so they injected either at the equator or between 10 north and 10 south. And they used so they went from a high forcing scenario, a high greenhouse gas forcing scenario, and used stratospheric aerosols to bring it down to medium. So it was then later shown that if instead of injecting at the equator, we inject at 4 different locations, we can then use an algorithm that decides each year how much to inject at each location in order to not only maintain the global mean temperature, but also we can seek to maintain the equator to pole and interhemispheric temperature differences by using these 4 different locations. So as an example, here on the right is the surface temperature change from RCP 8.5 for different latitudes and different years. And then on the bottom is the same simulation, but where we injected at 4 different locations, and using the algorithm in order to maintain the same pattern of surface temperature. So just to talk about the benefits of injecting at 4 different locations and off the equator, I will show some work from Alice Wells, where it's the same scenario, so going from SSP 585, which is a black line here, to SSP 245, which is set to 0 here. And they did it in 2 ways. So one is the blue one, which is injection at the equator, and one is the pink one, which is the G6 sulfur controller, and that is injecting at these 4 different locations shown here, and the total injection shown in pink here. And so you can compare for the same scenario the relative benefits of injecting off the equator. So on the left here, I'm showing the stratospheric aerosol optical depth, which shows that the aerosols tend to get trapped in the tropical pipe in the stratosphere. Whereas for the injection at the 4 different locations, you can do a better job and you can maintain the equator to pole temperature difference, which is the pink line here, which is near the 0 line, whereas the black line is the SSB 585 change in pole to equator ratio temperature, and the blue is when you do the injection at the equator. And so, as you would expect from this plot, you get in the case where you inject at the equator, you get an overcooling of the tropics and an undercooling of the poles. So that's the sort of residual temperature change you get in the geoengineered climate. In the case where you inject at the 4 different locations, You still get a bit of undercooling at the poles, but it looks a lot better than in the case where you inject at the equator. And finally, so it is known that doing stratospheric aerosol injection with SO2, you get some stratospheric warming, but the stratospheric warming is a lot stronger if you inject at the equator than if you inject off the equator. And that stratospheric warming has some surface impact. So it's good to know that you could reduce these effects by injecting off the equator. And so this talk is mostly about this new simulation ensemble, where we use that controller with the 4 different locations, and we use a different background scenario, which is arguably more policy relevant. So in this case, the baseline scenario will be SSP 245, and the goal will be to maintain the global mean temperature at 1.5 above pre-industrial, but also to maintain the hemispheric difference and the equator pole difference in surface temperature. So we have 2 Earth system models that have done these experiments, so CESM2 and UKSM1. And the objective of this talk will be to compare the climate impacts and performance of the algorithm. So first off, looking at the global mean temperature. So on the left, we have UKSM, on the right, CESM. And the red is the background scenario, so SSP 245. And then in blue is the geoengineered climate, where we inject aerosols in the stratosphere to maintain temperature at 1.5 degrees above pre-industrial. So the target is shown here in the dashed lines. So both models achieve the required target. Then looking at the second temperature target, which was to maintain the interhemispheric temperature difference. In CESM, there's not much of a change in the interhemispheric temperature gradient. So the controller doesn't have much work to do, so the target is achieved. In UKSM, it's a different story. There's a strong Arctic amplification. So there is a need for the controller to change the injections in order to maintain the interhemispheric temperature gradient. But it looks like it manages to do that. So we do hit the target more or less. And finally, for the equator to pole temperature gradient, it's more or less the same story for CESM, where in the background, there isn't much of a change in the equator to pole temperature gradient. But in UKSM, where there's a lot of Arctic amplification, there is a large change in the gradient, and the geoengineered climate does not reach its target. And we'll talk a bit more about that later. And then we can look at the injection rates and the locations. So on the left is for UKSM, on the right for CESM. In black is the total injection rate. And then the different colors show you where the algorithm chose to inject. So it's at 30 and 15 north and south. So in CESM, there's a linear increase in injection for the 4 different locations, and basically most of it is injected at 15 south. In UKSM, it's not so linear, it's a bit more messy, and after 2050, it seems like there's a huge increase in injection at 15 north, and that is basically because the target for the equator pole temperature gradient was not reached, and because of how the algorithm works, it chose to sort of increase the injection at 15 north. And finally, just to give you an idea of what these different numbers mean, I just gave as a reference the Pinatubo eruption in 1991, between 14 and 23 teragrams of SO2 in the stratosphere. And the current tropospheric emissions of SO2 is about 100 teragrams per year. And then we can look at the surface temperature change. So on the left, I will be showing the UKSM, and on the right, the CESM. And this is for the background warming scenario, SSP 245. And then for the geoengineered climate. So you see for CESM, there's a large North Atlantic warming hole. And so because the algorithms are optimizing for the global mean temperature, it means that the rest of the planet is warming a bit, but not a lot. And in UKSM, because of the large Arctic warming, there's a strong residual Arctic warming, and so the rest of the planet is cooling a bit, but again, not that much. And then you can look at the zonal mean temperature difference. So the solid lines here show the SSP245 for the two different models in green and purple. And the dashed lines show the ARISE, so the geoengineered climate. So there is a strong disagreement between both models in the SSP245 because of the different rates of warming and the different rates of Arctic amplification. But in the geoengineered climate, the disagreement is still there, but it's a lot smaller. And that is basically because the total temperature change is a lot smaller, the effect of the feedbacks is a lot smaller. So the disagreement between the models is smaller. And then, so the story for precipitation is a bit more complicated. So I'm focusing here on the zonal mean precipitation over land. And I'll be separating out the seasons because that is quite important for tropical precipitation. So on the left, I'll be showing the DJF, December, January, February, and on the right, June, July, August. And the top row here is the SSP245, so the warming scenario. So even then, so the change in land precipitation and the SSP245, the two models disagree on the sign of the change in the tropics. So even without stratospheric aerosols. But then if you look in the geoengineered climate, so in June, July, August, the change in the tropics, there's less of a disagreement in the change in the tropics, but in December, January, February, there's more of a disagreement. So the story around precipitation is, I guess, a bit more complicated than the story around temperature change. Okay, so these results are out in the preprint that's out for discussion. So if you have any comments, you're welcome to contribute. And as a side note, I wanted to verify that if I moved the injection further towards the poles, I could reach the targets in terms of inducing enough Arctic cooling to reach the temperature targets that I showed at the beginning. So these are the injection rates I've just shown, where we inject at 30 and 15 north and south. And then this is the sort of a different simulation where I just changed the 30 north and south to 60 north and south. And so in this case, the algorithm just decides to inject everything at 60 north and south, with a bit more at 60 north. So in red is the previous simulations, and then in blue are the so-called like polar simulations corresponding to these. So obviously the aerosol optical depth change is a lot more polar amplified in the case where I inject at 60 north and south. But as you can see, the surface temperature change is not that different between the two cases. And the same is true for precipitation. So I even looked at the different seasons, and the story is more or less the same. So I find it surprising that despite the large differences in the aerosol optical depth, you don't get that much of a big difference in the surface temperature change or the precipitation change. And also just add the blue line here means that you do satisfy the targets as depicted in this plot. So this one in the polar simulations does reach the T2 target. So conclusions, so the adding stratospheric aerosol injection tends to reduce the disagreement between models, at least for the surface temperature change. It's more ambiguous for precipitation changes. And so in order to reduce the uncertainties around stratospheric aerosol injection, it'd be good to have more models performing the same kind of experiments. The algorithm that we used is somewhat complicated to implement. So we're looking at sort of simpler injection strategies that would keep the benefits of injecting off the equator, as I explained at the beginning. Finally, injecting at high latitudes does not seem to change the climate much, so that suggests that at least for UKSM, the number of degrees of freedom around SAI is relatively small, potentially. And so there's a lot yet to be explored using the existing climate simulation ensembles. So something I've been thinking about is the impact on monsoons. So if you want to collaborate on that, please reach out. And if you have any questions or comments, I'd be very happy to respond. And sorry that I couldn't be there either in person or virtually. So thank you very much.
I'll tell him you clapped. I guess we can move on to the next talk.
Today I'm going to talk a little bit about the chemistry in Wacom, and it might affect some of those talks that were just mentioned. We've always had a little bit of trouble getting good Northern Hemisphere ozone depletion, especially in the interactive version of the model. And hopefully the improved denitrification choices will get us there. I want to acknowledge the collaboration we have with the Solomon Group. I'm going to present two papers today briefly, and one is by Catherine Wilke, who is now at Stanford, and the other is Michael, and she was a graduate student for Susan, and Michael Weimer, who was a postdoc and is now at the University of Bremen, and then of course Susan. Lots of satellite data, and we're actually going to talk about some chemistry today, and I'll move on here if I can do that. Okay, so a little background. Why do we care about denitrification? And if you look at the yellow line here, everything above the yellow line is the unreactive chemistry. My glasses on. And so you have reservoir species, chlorine, nitrate, and HCl. Okay, so if the temperatures are cold enough, what's going to happen? You're going to have heterogeneous reactions on surfaces of PSCs, and you're going to convert these reactive gases into the activated chlorine, and as long as the activated chlorine is going on, you're going to get ozone depletion. So the question is, what role does denitrification play? Well, in the late spring, as temperatures get a little warmer, if you have a little nitric acid around and you photolize to NO2, it can move more of the CLO back to chlorine nitrate and shut off the whole heterogeneous chemistry. Also, denitrification on NAP particles can take nitric acid out of the atmosphere, and if it takes too much out of the atmosphere, you're not going to have enough nitric acid or to be uptake by the supercooled ternary solutions, which are the main solutions that actually destroy ozone, at least in the Wacom model, and I think probably in the atmosphere too. So there's a fine balance between getting nitric acid right or NOY right in these models. Too much or too little can put you in a place you don't want to be. Okay, so today I'm going to show some satellite data, and I just want to highlight the data. It's we're going to use some nitric acid data from the microwave limb sounder. It's got roughly 4 kilometers vertical resolution, 0.6 parts per billion precision, and we're only going to look in 2020 the year for that. It's a cold northern hemisphere winter. Most of our work with the nitric acid is going to be done with the MEPAS data, a little bit better vertical resolution and better precision, which is important for this study. I'll also show some total column data from OMI on the Aura satellite and one ozone sonde. We're using the 2-degree version of Wacom that goes from 0 to 140 kilometers, and we're nudging it to MERA-2 data. And the good thing about that is you get the dynamics about right, but you get the temperatures right. And the previous slide, and I didn't mention it, but temperature is really important. You have to get this to plus or minus 1 to maybe 1.5 degrees to get the right ozone depletion. So why did we start thinking about denitrification? Well, it was this study that Catherine started with Susan and myself. We were looking at the Arctic ozone hole in 2020, and we had this study that we wanted to look at it. What would happen if we didn't have a Montreal Protocol? And you can see in the line here the regular equivalent effective chlorine would drop off in 2020 to be somewhere a little under 4, but if you had no Montreal Protocol, it would be over 10 in 2020. So the example here is the March 13th total column ozone for real-world Wacom. specify dynamics, compared to the OMI satellite. And this is actually a really good comparison. And there's no real, there's ozone depletion here, but nothing like what you would see in the southern hemisphere. In fact, if you look at what it would look like in the southern hemisphere, you would get this large ozone hole in 2020 if you did not have the Montreal Protocol. In fact, this depletion, right there is the United States, Canada, large population areas, so this would have been a real catastrophe. The ozone hole area is around 19 million kilometers. That's similar to what you kind of see in the Antarctic, and we would have had like 130 Dobson units of depletion for that year. So this was a really cold year, but with that kind of chlorine and bromine in the atmosphere, you would have really had a problem. But we had to work really hard to get the Northern Hemisphere real world to look good. And the way we finally got it there was to work on the denitrification. And so the way we do denitrification in WACM is for every time step, we calculate the condensed phase nitric acid and assume a supersaturation of 10. So it's based on laboratory data. And we assume a log normal size distribution, we give it a width of the distribution, and then we specify the total number of particles per centimeter cubed. Out of that, we can derive the radius, effective radius of the NAP particle and the surface area density. The radius is for denitrification, the surface area density is for chemistry. And we tried various different choices for the size distribution. And what happens is when you have a few particles, for that given amount of condensed phase, then you have a larger radius and more will fall out of the atmosphere. If you have a lot of particles, then it'll fall out slower. And so our reference case was this blue line here, 0.01 particles per centimeter cubed. So we didn't have small enough particles or small enough number of particles per centimeter cubed to get really significant denitrification. And we know from aircraft data in 1999-2000 that Fahey saw these NAT rocks where nitric acid was just coming out of the atmosphere really rapidly on NAT. Okay. So the next step is we want to do a more quantitative approach to deriving what number we should use for the NAT particle density in WACM. So we needed basically to get a better representation of nitric acid gas, again to the chemistry slide I started with, and the amount of nitric acid that would be available for STS or important for ozone depletion. And we decided to go with MePass data based on its vertical resolution and precision. We also looked at other species from MePass, but I won't go into that today, ozone and chlorine nitrate. So what did we do? Well, we started out and we looked at 3 different NAT particle densities. The red, which is 1e to the minus 5, so a small number. The green, which is 5e to the minus 4, somewhere in the middle. And then 1e to the 2 was where we started from. And we know that 1e to the minus 2 wasn't good. The way we did the analysis, so instead of looking at monthly means or things like that, we used the output tool in WACM where you can, if you give the model the coordinates of your satellite, the latitude, longitude, and time, you can output a profile. So we outputted profiles for every location of the MePass data between 2002 and 2012. And then we binned it up into the polar region using the Nash criteria. It's a common thing people do. And we only looked in spring. And I'm going to show you just briefly some scatter plots of observations versus model for the 3 different cases. I'll show you some vortex average time series, and I'll also show you some PDFs. I won't show you another form of analysis we did in the paper. You'll have to go to the Weimer et al. Paper to see that, where essentially it's an integration of the PDF. It's called the cumulative density functions. And what you can do is you can compare these functions and you can look at the maximum difference from them, and you can use that to say which function basically most matches the observations. But you'll have to go to the paper for that. Okay. So here's one of the take-home plots. This is vortex average for 2002 to 2012. There's something like 200,000 profiles that are in each one of these plots here. And This is the three different colors. Again, 1e to the minus 5, so small number for the gnat particle density. 5e to the 4, medium, and then 1e to the minus 2, which is where we started. And if you look in the northern hemisphere, you know, pretty much it's a 1-to-1 correspondence, you know, with some variability there, that the 5e to the minus 4 is really the best choice to get the right amount of nitric acid in the model. And this is over all these different years. If you look in the southern hemisphere, it's a little bit over denitrifying, but not too bad. We probably could have used a little smaller number there, but it's not bad. But you can see that there's cases here for the blue case, which 1e to the minus 2, that Wacom would have had significantly more nitric acid available and around than what the MEPAS data would suggest. Okay, so that's that. If you want to look at, another way to look at it is to look at integrated, to look at the vortex average time series, and this is between 150 and 30 hectopascals for just 1 year, 2011. Now, 2011 is an interesting year because it was also a very cold year and there was ozone depletion going on. And you notice in the MEPAS data, if you can see that dashed line, that's from March 1st. And yeah, you can kind of see that there is some depletion. The green kind of washes out there. But when we had previously, we had just the 1e to the minus 2, which was our reference case. We weren't getting hardly any ozone depletion, just a small amount. And we had way too much nitric acid around. If you look at the 5e to the minus 4, it looks a lot like the MEPAS data. So the nitric acid is looking consistent. If you go to, you know, even a smaller gnat density, unfortunately you over-denitrify, and you see that clearly in this picture. The southern hemisphere looks pretty good for all cases, but it's much better overall for the 5e to the minus 4. Again, and if you have the 1e to the minus 5, you're over-denitrifying, and the 1e to the minus 2 gnat density, you're not denitrifying quite enough. And this was actually shown in a talk by Michael Schwartz of MLS Group for the QoS, and he was saying, you guys should really work a little bit more on your nitric acid in the southern hemisphere because MLS was showing more, and so that's another reason why we wanted to get on this study. Okay, and finally, I'm just going to show you some PDFs here. This is northern hemisphere. Again, the same colors for particle density, the 1e to the 5, 5e to the 4, and 1e to the 2. And let's just go to the middle panel here for year 2003. You can see the data is in the black, and the dark green here is the 5e to the 4, and then you can see the shift of the PDF to lower values for the 1e to the minus 5, and the shift to the right for higher values. And so you can really stare at these things. We looked at every year and all, and in general, we do a very good job of kind of representing the PDF structure. Now, it's not perfect by any means, but I think it's good enough for the way we're using this simple approach to denitrify. And I did put in the max D here, which is the difference between the distributions, and the smaller number is always aligned with a 5e to the minus 4, which is what you want to see when you're comparing the distributions. And again, you'll have to go to the paper to understand that more. And then finally, I guess this is Southern Hemisphere too. Again, when you have too small of a gnat particle density, you over-denitrify, the PDF gets shifted all the way to the left. But if you use the value that we consider the best, the 5e to the 4, it's right over the peak of the observations. So it's kind of we're beating the same drum over and over again, but we're looking at it in 3 or 4 different ways, and we're coming up with the same conclusion. And so finally, we're going to go with this number density for a gnat in all the future versions. In fact, if you're checking out CSM2 more recent, it's already in there. I think Louisa put it in with Francis. And we hope that'll give us a better opportunity to get ozone depletion correct in the northern hemisphere. And, number one thing always in these models is temperature, and that's why they pay the gravity wave people all the money to get this stuff done. But the second thing is you gotta get denitrification right, and have the right heterogeneous chemistry in there. So thank you for your attention, and that's all I have. Do you have any questions? Anybody?
Hi, so that was all pretty cool. So like for when you show the comparison with MIPAS, that's for the HNO3, right? Or our
Yeah, it's for the nitric acid, yes.
Yeah, have you done, so what, I'm just wondering, have you quantified what is the impact on ozone? Obviously, if you don't denitrify enough, you're gonna reduce.
Yeah, you know, we did put that in the paper. We did PDFs of ozone, and we
Okay.
did it also of chlorine nitrate, because MIPAS measures those. And so because of that, again, ozone looks better when you have the 5e, the -4 number in there.
Okay.
So yeah, it is consistent.
All right. Thanks, Doug. Let's move on to our final speaker, June.
Apologies, I need to download your presentation again.
Oh, it's here. Oh, hi, I'm Jun Zhen. I'm an ASP postdoc working at ACOM. Thanks for the opportunity to present here. And today I'm doing simulation to study the effects of Tonga eruption on stratospheric ozone. First, I would like to thank all my co-authors for their tremendous help and support. And on January 14th, Tonga Hapa volcano erupted in Tonga, a country near Australia in the southern hemisphere. This eruption was one of the most explosive volcanic events in the 21st century. It erupted it bring up the volcanic materials all the way up to 58 kilometers, break through into the mesosphere. And this eruption injected 0.42 teragrams of sulfur dioxide into the stratosphere, which is actually very small compared to the Pinatubo, which put about 20 teragram of SO2 into the atmosphere. However, Tonga is unique because it's a submarine volcano which injected a significant amount of water vapor along with SO2 injection, and which is something we have never seen in the modern satellite era before. And this additional source of water vapor can increase the hydroxyl radical in the atmosphere and then enhance the Hawkes ozone loss cycle and eventually deplete stratospheric ozone. On the other hand, SO2 injection forms sulfur aerosols and enhance the aerosol surface area density and facilitate heterogeneous chemistry, can also end up on the stratospheric ozone depletion. Here I'm showing the observed aura microwave limb sounder satellite data. This movie here shows the evolution of ozone anomaly throughout 2022 in the stratosphere. It's calculated by 2022 minus 2007 to 2021, 15 years climatology. And the hatched region here shows the 2020 anomaly are outside the range of all variability during the climatology period. And we see that there is a southern hemisphere middle latitudes anomaly developed in here, and we also see there's a large anomaly over the Antarctic polar region during October to December. So I'm curious how our model is representing this ozone anomaly in 2022. I'm using Wacom 6 110 level with a horizontal resolution of 1 degree and a vertical resolution of 500 meters in the upper troposphere and lower stratosphere. It includes 4 interactive troposphere and stratosphere chemistry, and the simulation here is notched all the way from 2007 to 2022 towards MERA-2 reanalysis fields. And starting from January 2022, 2 simulations were performed. One is a full forcing, which include both water vapor and SO2 injection. Another one is no volcano emission case, which we use as a control case. Okay, now I'm bringing back the ozone anomaly figure I showed before from MMS. This time I have Wacom results on the right for comparison. You can see that Wacom shows very good agreement with MLS throughout the whole year of 2022, and it fully represents ozone anomaly over the southern hemisphere, mid-latitudes, and the Antarctic region. One thing I want to point out is that anomaly here we see is not just due to the Hunga Tonga eruption. The stratosphere internal variability also plays a role here. And the question I'm particularly interested in is that the relative role of chemistry and dynamics impact on this ozone anomaly. So in the following, I will try to quantify the chemical impact on this ozone anomaly. First, we are looking at the evolution of water plume and aerosol surface area density. It's calculated by the full forcing case minus the control case. And both of cases are notched to the same dynamics. The red contour and blue contour lines are for water vapor and surface area density perturbations. We see that the water plume propagates from the southern hemisphere middle latitudes, southern hemisphere subtropics to the high latitudes in 2022, but it stayed out of the polar vortex last year, which is consistent to what we see from the satellite data. And for the surface area density, I highlighted the region that is more than doubled relative to the background level. And we see that the small amount of aerosols gets into the Antarctic region underneath the polar vortex. And both of the perturbation can directly impact on the ozone chemistry. Now I'm trying to quantify the chemistry-induced ozone change. So on the left panel here, we see that the ozone change due to the combination of the stratosphere internal variability and the Tonga-Hunga-induced ozone change. And we call it full impact. On the right is the ozone change only from the pure chemistry, which is calculated by the forcing minus control case. We call it pure chemistry because the two cases are notched to the same dynamics. So it does not include the dynamics feedback on the chemistry. For example, the stratospheric water could cool the water in the stratosphere could cool the stratosphere and further enhance the heterogeneous reactions and further impact on the ozone chemistry. But the notch simulation does not allow the temperature to adjust. So the changes we see here are purely due to the chemical impact from the water vapor and SAD perturbation we saw from last slide. So we see that the chemistry contribution to the ozone depletion occurs at both mid-latitudes and polar region, and they are contributing to about 20 and 42% to the total ozone anomaly. To understand this better, I further looked at the ozone loss chemistry cycles. So the left figure here shows the ozone loss from all the cycles, and the right 4 cycles shows the individual loss cycles. Those cycles interfere with affecting each other and changes repartitioning from each other. The red shows more ozone loss from each cycle. And the the ox cycle here is not important, but I included here for completeness. We see that the Hawks and Clark's and Brock's cycles are playing major roles in the ozone depletion in the middle latitudes and the polar regions. We also see that the ozone loss from NOx cycle is suppressed, and what's going on here? Then we further looked at the NOx anomaly from OSIRIS in the top panel, overlay with OMP's aerosol extinction in the contour line. And the bottom panel shows the Wacom-derived NOx anomaly. We see that the Wacom can reproduce the NOx anomaly very well. It captures the dipole structure of the NOx anomaly. The positive anomaly above is mainly due to the QBO internal variability. And you may notice that the negative anomaly is co-located with Hunga Tonga aerosol plume, which reveals that the N2O5 hydrolysis in aerosols is the major chemical process that's controlling the NOx reduction here. Okay, in summary, Wacom 6 notch simulation shows a very good agreement with MLS ozone anomaly and also reproduced NOx anomaly in 2022 very well compared to OSIRIS. And notch simulations can be used to quantify the chemistry contribution to the ozone anomaly. The chemistry contribution to ozone depletion occurs at both middle latitudes and polar region, accounting for about 20 and 42% respectively to the total negative anomaly. We have also done a set of free-running ensemble simulations from 2022 to 2025. If you are interested, please check out this preprint paper done by Xingyue Wang, which has a very nice discussion about how the Hunga Tonga eruption impact on the dynamics. Okay, thank you for your attention, and contact me for any questions and comments.
Time for a question. Dang.
Okay, all understood.
Doug, you're volunteering. Okay. Yeah. If you can use the mic, yeah, thanks.
Talk, June. Volcanoes are known also to emit bromine. So does your simulation include the additional bromine that would have been injected to the stratosphere?
Chlorine are very short-lived. So we are working on a paper that look at the initial evolution of the plume that has the chlorine injection. But for the longer term, I'm looking at the whole 2022 year, so I didn't include chlorine and bromine injection. But that's a good point.
All right, thank you, June. So we've got time here before our break for the evening, before the evening sessions for further discussion. For those in the community that don't know, I will be leaving NCAR for industry at the end of July. So part of the discussion that leadership's been having NCAR for industry at the end of July. So part of the discussion that leadership's been having is hiring needs and transitions for the Wacom group. That is fair game if people want to talk about that here, but also just know multiple lab directors are involved and expressing care about that. So I don't think Wacom itself is in immediate danger as far as I understand. But yeah, if there's anything else folks want to talk about in terms of Wacom 7 development or other development or science priorities, feel free. This is the time to have that discussion.
Just a little plug for tomorrow's chemistry climate working group is that there's some great talks that will influence both not only the troposphere but also the stratosphere. And specifically, we're getting the VSL chlorine, bromine, and iodine into CSM2, and Rafa is going to talk about that. And so that's kind of an exciting new thing for chemistry.
Well, Nick, I would say for what you just said, do you expect that Wacom 7 and in general will it be able to stay on time when it? Well, I know that it's complicated because scenario map is also like delaying their own things, but do you considering that Wacom doesn't even have a liaison right now, right? Which should be another one of the priorities.
Yeah, I don't have a lot of visibility on what the future plan is right now. I know, like, I've been trying to work hard to the end to get at least these couple of configurations tuned up in a sort of F-case situation. But yeah, someone needs to do someone needs to basically be handling coupled model simulations and evaluation. So I think, last week at the Wacom group meeting, we talked about people do that, but no, I don't have any easy answer there.
Well, I guess my point more in general was that I feel like the community outside of NCAR should maybe make it clearer how important Wacom is for them and for their research, and if that is any way it could help, making sure. I mean, they know at NCAR, but it's always helpful if the community steps up and says, we need Wacom, so you need to pay attention to Wacom. And thank you, Nick, for all you're doing in your last. You're great. We'll miss you. And on that note, if anybody else wants to show their affection to Nick, otherwise we can, I guess, break.
I will miss you too. You can always keep bothering me. I will not completely turn my shoulder. I may be more of a weekend kind of guy in the future. I'm entering a more operational kind of role, so yeah. But if there's folks who want to keep discussions going that we've already had about things like resolution and priorities, I don't know, a few of us will still be sticking around, so if you want to have a smaller discussion on that, we're good. So otherwise, thanks everyone for coming. Please give a final round of applause to all of our speakers. Thank you, everyone. And we will see you around tomorrow.
I'll say more about our.
Okay, I think we're ready to
Okay.
start. I don't
So
see a
let's
remote
just go
presenter.
with Mike then. He's going to be the first one in any case. If we are ready, Mike, can you hear us?
Mike, if you're on Zoom, please raise your digital hand and we'll make you a co-host to share. We don't see that remote presenter here. We can move on to the next and we'll keep an
Is he
eye.
in the other one, I wonder?
Maybe, that's a possibility. Yes, there was a switch in links.
So, oh, he wants a reminder of the Zoom link. He just sent me an email.
Forward that to Daniel Senna, please.
Okay, Daniel, could you send
We'll take care of
the
it.
Zoom link?
Mhm.
Okay. Yeah, he needs, yeah, he's panic mode. He sent me his phone number now.
We're working on it, yes.
Josh,
Not going to use the pointer. Okay, I guess I need to stand here, don't I? Better at walking around. Okay, I said a little bit about what our company is sort of based on and what we're trying to do. I want to talk a little bit about how we go about how we view the world. Really, a lot of it's going to be familiar to a lot of people in this room, and then I'll provide a couple of high-level methodological views and why we take that approach. Hopefully, it makes sense, and then I'll leave you with a couple of thoughts on what I think could be important going forward from a CESM community. So this is a marketing slide, a sales slide, right? Our marketing team built this for the sales team. They use this in conversations. One of our strengths as a company is our breadth, right? There's companies out there that focus on flooding only, or maybe flooding plus wind. And what we spent a lot of time doing, in fact, the way we built our company from the beginning was we want to build physical hazard platform based on defensible science, right? And there's a lot of choices you have to make when you do that. Everybody knows, right? But one of the core things is, for example, how do you downscale, right? Which I'll get into in a little bit. But I think the key thing here, one of the messages is that just going from downscale climate information, which we know is fraught with perils, not a pun, but it has to be used very thoughtfully. But to get from there to something that's consumable at scale, there's a big step there, right? There's a lot to do there. And our focus was really to build out our platform in a way that makes that doable at scale. We can serve a lot of information in a short amount of time for a lot of use cases that are emerging in business at various well. So we've built out a breadth and we've adopted the insurance industry terminology, perils. Underneath these perils, there's a lot of different metrics. So for example, for wind speed, we have a dozen different kinds of metrics: return periods, winds above thresholds, monthly averages, annual averages, annual maxima, those kinds of things. And we compute uncertainty for everything, right? Every number we give comes with uncertainty, presented pretty simply in our case with a 5th and a 95th percentile of that metric. So 100-year return period wind speed, you also get a 5th and a 95th percentile. So that's how you get to 11,700 numbers per location, right? We don't do downscaling to 90 meters for every peril or every peril metric, but we serve everything on a 90-meter grid, right? That makes it really easy, really scalable. Some things we downscale. People ask us how we choose what we downscale. Okay, what do we have good information to downscale with? Do we have, is there a reason to downscale, right? What's the length of the physical system, for example, that matters. And then just have we gotten there yet, right? Or is the science there? So those are all considerations for how to do it. in this pipeline here, and then we end with business impact. And what you find, and I'll say this in a different way here in a second, there's a lot of different kinds of customers out there in the world. Going from left to right, it's sort of, what do we do with climate? We're told we have to pay attention to this. And on the right is, we're trying to gain business advantages from this, right? And we encounter customers all through this. And their needs are very, very different, right? Even customers further to the right, maybe they're at 4, but not yet 5. There's a big difference between two banks, for example, who some banks, they know what to do with this data, or they know how to try to run it into their business units. And other banks, even the same size banks, they don't even know how to calculate loss on their portfolio, right? I mean, there's a huge disparity of customers in this. And so it makes a massive space. And what that means is there's lots of room for lots of organizations. All the way from everybody in here, all along this value chain until you get all the way on the right. And so what we're trying to do as a company is move people along this curve, right? So that they're learning how to make decisions and then making better decisions and understanding the limitations of the models, right? What they can do with them, what they can't do with them, how they should treat uncertainty and all those kinds of things. Okay, so just in a nutshell, one way we view our downscaling, our bread and butter, a lot of it is extreme events, right? So you might do downscaling, but to get to good extreme event estimation is another big step, right? We calculate all over the planet, so many of these things. And we often get asked, how do we choose our GCM? This is where we start waving our hands, right? And saying things like, well, it has to have the output variable we want. Great, check, that's an easy one. We like to use ensembles. Why do we like to use ensembles? Because we can treat now, we have enough samples in some time period that we can start to do reasonable extreme value estimation, assuming stationarity over a limited window, right? So if I have an ensemble with 50 members and I care about a year in the future and I'm okay taking plus or minus 5 years around that, 50 times 10, sample of 500 to do something on extreme value distribution. Now I can layer in, if I do that by itself and I've bias corrected it all, and I go ahead and fit all these distributions 1,000 times to get that part of the uncertainty, and then I can combine the ensemble at the end, or combine all the different ensembles at the end, and I'm using ensemble very specifically as a single model. Combine that at the end in a way that preserves the tails of distribution, and I get uncertainty from internal variability, model variability, and the fitting, the statistical estimation part of it. So all that's wrapped up in our basic downscaling. And this is, something that we do routinely, right? It's kind of a basic part of our processing pipeline. There's a lot of variations around it. We choose different extreme value distributions for different variables. We might choose different time windows or different baselines or things like that. But the general process, this applies in a lot of what we do. You can see that even in this case, we use different versions of the CESM and different ensembles because it beefs up our sample. We often make the choice of adding more is useful as long as we treat them in a fair way so that we're equally weighted. I should say, I didn't introduce, there's a little bit of terminology here that I realized I just went right over. This would be, I would call this like a phase 1, right? So our truth in this, to do the downscaling, is ERA 5, right? Sort of standard approach. It looks like a bias correction spatial disaggregation. We do it in distribution space rather than the time series, right? And there's several advantages, which it's much, much faster than trying to do time series all over the globe, possible GCM. These things are a little bit out. I'm going to do this first. This is phase 1. This will look familiar to many here, right? So this is taking one GCM ensemble, and this is how it looks. I'm not going to spend a lot of time on this because most of you probably know how it works. But the key thing is that, again, instead of doing it time series, we do this to distribution parameters. I'm showing a Gaussian here because it's easy to look at, right? So this might be a temperature, daily maximum temperature distribution. We have the orange or red, which is a reanalysis or ERA 5. I've got the green, which is baseline, historical run, and the blue, which is the GCM future run. Future to the downscaled and calibrated. ERA 5, right? So this is like step 1 of our downscaling everywhere. And then, right order, step 2 is where it gets more complicated, right? And this is where Currently, we're bringing in new information, land cover. I know it's probably pretty small. Land cover information to modulate heat, for example, so we can really see the urban heat islands and the coastal. Friction for wind speed, all these things come in at this time. Local observations to build out the tails of the precipitation distribution. All things, and now it's a real big data problem. Okay, and so simple. Let's try a regression model and go with that. Let's try the next more complicated thing, maybe a random forest, right, or a more complicated linear regression, or a regression in a transform space. Well, let's see if we can do something more. Now we'll try a neural network. And along the way, we're always evaluating cost to benefit. So there's a bunch of boxes here. Maybe you got through some of them, but in a nutshell, next level downscaling that we apply when it makes sense to do it. Well, it's a different beast, right? The digital train model or digital elevation model is order one control on this. We're right now finishing up a brand new flood model that's globally at 90 meters. Why 90 meters? There's a hydro-conditioned digital rain model that comes built from the shuttle radiative transfer mission, and that actually defines sort of how we serve all our data. So this new model, all three kinds of flooding, right? And we're building hazard maps, right? We're not doing or days or whatever, although we could with this system if we wanted to. So we have pluvial, coastal, fluvial. There's several different features here that I don't really have time to go through. Happy to be talking to anybody about it later, but coastal, for example, accounts for storm surge, wave setup, layer in our tropical cyclone stresses to add to that, and calibrated with sort of a common approach to capture the peaks of the surge. So all these things happen, so they're very complicated processing pipelines. I should mention, I didn't really put a slide in on this, but the team we have in the company we're scientists, right? A lot of us have academic backgrounds. We spent a lot of time looking at our data and understanding what we have and what we don't have. We've also built up a lot of automated quantitative validation based on external independent data sets. We spent a lot of time looking at the literature that you all produce about how well things are doing, right? Checking ourselves. And we're open to communicating this to our customers, right? They ask, we show them, okay? We show them work. We have customers that care more about the edge effects than the overall skill, right? The probably not well thought out list of my ask is what Alicia said, but what's the ask? There's a long list. I think at the end of the day, we're fans of what you do, right? Keep building good models, right? Keep advancing the science, because that's not something we can do. We're in another part of the value chain. But I think that all the work coming on in interannual and decadal prediction is super exciting. Right? We get questions about this from our customers, and we just say, well, science is coming along, but it's not quite there yet. But this may open new uses once we get a little further along. And just, model fidelity, right? I'll give you an example. The hot model problem is I get these questions all the time now, right? So as these customers move along to the right of that maturity, they're going to ask more harder questions, right? And we want to answer these questions accurately, and we want to make the best decisions in building our products too, right? So keep those things going. And somebody I didn't know but gave a talk there in a session, Monica Morrison or something. I haven't met her, but she made some really nice comments, I thought, about sort of responsible use of this stuff. And it led me, and somebody asked a question, I couldn't see who it was, but about this may apply to the broader CESM or broader community, but it's idea of, 1 minute, okay, this idea of what do you have and what do you not have in your model, right? I don't think you need a 40-hour survey to get this in a way that's useful to users, right? That might be useful to you all to some extent. So for us, it's like, oh, these 6 models have problems in the Great Lakes. Like, we probably knew that through our own diagnostics. We know the issues with the runoff, right? That's easy to see, right? But these sorts of things at that level is super useful, right? Because then we can do a better job choosing which models we use, but also explaining to our customers, who at the end of the day are making money decisions, right, with this stuff. Shouldn't look at stuff where they should, how they should use it, how they should think.
Yeah, we'll take questions at the end. So in the interest of time, Mike has to leave pretty soon. So Mike, you are next, but we need your presentation.
Is that coming through?
Yes, it is coming through, so please go ahead.
Okay, great. Yeah, thank you so much. I'm sorry I couldn't be there in person. I'd hoped to be, but I appreciate you enjoying a remote presentation here. Yeah, so you might be wondering what's NVIDIA doing in a session like this. To me, the deep roots of that go to supercomputing. So of course, NVIDIA builds supercomputers, and this is the latest one. This is the ALPS machine that's being installed at the Swiss Supercomputing Center using the new Grace Hopper super chip. And I know people that are interested in next generation global cloud resolving modeling are excited to use it because it's really powerful. So it's part of the story. And there's a few of these exascale AI capable machines around the country now that are being actively used for Earth system science. So that's part of NVIDIA's connection to climate prediction. That has also deep roots in the code. So this slide's meant to be overwhelming. These are the many atmospheric simulation codes that NVIDIA has invested engineering cycles in trying to refactoring to prove the concept of how fast they could run if re-engineered for speed of light performance on GPU. And then lately, I guess I would point to AI because the same GPUs that are great for certain highly threaded calculations have also proven to be great for AI, and some of the clusters that are being built are going to be primarily used for ambitious machine learning. And so the big question that's interested me for a long time, as someone who's tried to be explorative of algorithms with breakthrough potential to solve the resolution dilemma in climate simulation, is whether we don't have to wait for Moore's law to get to the sorts of cloud resolving resolutions that we know we need to answer questions about stratocumulus cloud feedback and other things that regulate future climate hazard. But whether AI offers an opportunity to sidestep Moore's law. And so I'm an academic and have been for a decade at the University of California, Irvine. And my life changed a bit after the CEO of NVIDIA dropped a blog post that you can read expressing interest in some of these same issues about outsourcing high resolution calculations to AI emulators and trying to do the impossible in climate simulation. And also very resonant with the mission in Destination Earth in Europe to make climate prediction operational. So I should say my first encounter of NVIDIA's technology had been as someone who used the DOE supercomputers, where it turned out through an effort called the Exascale Computing Project, a certain category of multi-scale climate simulation algorithm had been successfully refactored to a large GPU supercomputer, and that's sort of changed my life. But I've since found out, in terms of being able to run more ambitious simulations, but I've since found out that they're much more than a GPU cluster company, and that the company's full of, and it's 27,000 people, it's full of AI experts and deep learning engineers who can optimize ambitious machine learning and high performance computing workflows. So they both build the hardware, scale it to ambitious limits, and innovate on the latest AI algorithms that also try to scale those out. And so because the business model involves a lot of hardware as well, much of the science can be open and in the open domain to prove concepts that, if authentically appealing, organically drive some of the business. So I want to mention some breakthroughs in AI weather prediction that are relevant to the interface between NVIDIA and CESM. So we'll get to climate in a moment, but start with weather here. So this is NVIDIA's fully AI weather prediction model called ForecastNet. It's different than physics-based weather simulation, solving PDEs on a large cluster, which is slow and expensive. This is completely data-driven. It's trying to predict videos using the next frame, but instead of red, green, and blue pixel channels, we have temperatures, winds at various altitudes of the atmosphere. And so it's trained using the entire Era 5 reanalysis library at its native 25-kilometer resolution, which is sort of an active, ambitious machine learning using transformer architectures with Fourier operators in the middle of them to make it easier to scale. But the big point is in green here. Once trained, this model is 10,000 times faster to inference than a classical simulator of weather. And so it can achieve a 2-week simulation on one GPU in just a quarter of a second. And so that's the really exciting thing here, is that this sort of speed is game changing. provided there's skill that's relevant here. This graph shows you in yellow the baseline IFS, the European models weather skill. So, skill decays as you lose memory of your initial condition. The name of the game in weather prediction is try to predict curves, move curves like this as far to the right as you can. About a year ago, we were at this purple line, and just a few months later, we're at this blue line. The main point here is that the rate of change, the rate of improvement in these pure AI weather predictors is phenomenal compared to the rate of progress in classical weather prediction. And last year you may have noticed that a few tech companies, Huawei, DeepMind, and a couple of others are claiming that the AI weather prediction is now better than classical deterministic weather prediction. So very, very exciting time, very exciting year. These are clearly physics emulators to an extent if they can pass skill scores like this. And the game-changing part about that is just the speed up, the order of magnitude of the speed up. This opens the door to 10,000 member weather ensembles. If you want to build counterfactuals of historical climate risk, there's a new tech to do that. We quite valuable, I think, for sampling tail risk. And meanwhile, if we want to train emulators like this on other forms of data other than the historical record, it's a way to offer very low latency, very nimble access to the same sorts of results that we get from actual PD solvers. So on the tail risk aspect, of course, there are high impact, low likelihood extremes that we desperately need better climatologies of for the historical climate, let alone the future. This year's California wet season is an example of one. But I could spend an hour on weather. I don't want to. Let's move to climate because we're here to talk about CESM. This is part of the vision of Destination Earth that is resonant with our CEO's interest, which is that we need a paradigm shifting moment in our appreciation of people's place in the planet and in changing climate. There have been such paradigm shifting moments in the past. Flew up in air balloons and airplanes and satellites, and especially satellites. How much innovation was spurred by curious people just flipping through banks of global imagery they'd never seen before. But the problem is nobody knows how to flip nimbly through banks of climate predictions. You all know how impenetrable the archives are and how much niche expertise is needed to really make use of them and visualize them. And these archives are somewhat impenetrable to non-experts. They need people to hold their hands. And that's where, there we go. There we go. So that's where ideas like ForecastNet could be quite relevant. Models like ForecastNet could be trained on the existing library of climate predictions, including CSM's climate projections. And once trained, they offer a way to tether, to allow you to not have to store as much data, not have to move as much data around. If you're interested in the high frequency details of a climate simulation's future predictions, you may only need to checkpoint every week or two if you trust these AI generators to develop reliable realizations of internal variability in between them. And so that's a really exciting idea that I think in the next year or two, we'll see the same sorts of architectures that have proven capable in weather prediction be trained on future climate projections. And once trained, you could imagine them easily allowing a back end that doesn't involve inferencing actual data stores, but just involves inferencing local generated AI predictions to fill in the gaps. And so Destination Earth, as well as NVIDIA, envisions these sorts of systems connected together to impacts models. So to the extent that CESM might be interested in making bespoke output to train bespoke digital twins of itself, I think this is an exciting vision. And so the Earth 2 initiative is something our CEO has built. It's not meant to do this inside a company on its own, but just given that it's a tech company, to think hard about whether some of the assets we have, like these ultra-fast AI surrogate models, some of the lessons we've learned and how the pipelines for how to train them well at scale, and some of our visualization assets might be relevant to the world's efforts to build these sorts of digital twins. So these are some of the tools. I haven't talked much about them. The top left one is an omniverse environment. It's a place where designers, architects, people who build factories are now investigating and optimizing before they break ground using digital twins of physics emulators to optimize systems. You might imagine similar experiences with climate system optimization in the future. Nucleus is a place for interoperability for AI physics models to interconnect with each other and with the visualization experience. Modulus, I want to emphasize on the top right, is now open source and is the vehicle with which we're releasing openly our new AI weather algorithms. If you want to play with them and test the limits of AI weather predictability or investigate the properties of large ensembles that can be generated from AI weather predictions. Bottom left is the new super chip I mentioned that should open the door to another step change in resolution and global cloud resolving modeling. So yeah, I want to emphasize that again, that this is a complementary effort. It's finding its positioning. More about its positioning will be revealed in a month or so. And you know, but the idea is that we think we have some complementary assets compared to other efforts going on in industry and government, and our CEO definitely wants to help. And so I'll end with a slide that I've been starting to put together on my academic half. I still maintain a half-time or part-time appointment at UC Irvine, and I'm thinking about my graduate students who are expressing increasing interest in becoming competitive for these sorts of climate tech jobs. Reflecting on my last year off with NVIDIA, I think any user of CSM, your climate and weather domain expertise is definitely already valuable. I overheard Josh speaking to some of that. This niche knowledge of what's working well and what's not is valuable. Having it alongside some AI algorithm expertise that helps you become conversant with the deep learning professionals in a company like NVIDIA is, I think, a double threat. Having students gaining experience in team development operations, whether it's through contributing pushes to open source repos and the friction that comes there, the understanding of how to build performant ML pipelines, and having sensible software versioning control. I sense these as sort of core competencies in most of the employees in NVIDIA. And I think also leaning into the data set formats of the future, the cloud-friendly formats, and the issues going on there in modern analytics, all helpful things to be doing, and communication skills. I think there's a lot of team dynamics I'm witnessing for the first time across product and marketing and engineering and basic research, and you know, just being able to communicate nimbly, but also you know, being nimble in your technical depth and your social breadth. So I hope some of this is useful, and I'll try to connect later on for questions by audio, and I hope we kept to time here, and thank you for your time.
Thank you very much, Mike. So our next speaker is Polly.
Great. So this is going to be a little different topic from the others, I guess. We all have pretty different applications. So I'd like to talk about how we're using CLM fates in the voluntary carbon credit market. And just to give a little background on really how this all came about, you know, achieving net zero emissions equal removals, it balances out. And so I'm going to use Microsoft as an example of how a company is proposing to do this. This is their plan for achieving net zero by 2030. And the blue, these are the reductions in emissions, and the green are the increases in removals. And those increases in removals, that's where the voluntary carbon credit market comes in. It's not regular, it's not mandatory. They're doing it because they want to do it. So there's a lot of ways that you can get carbon credits in the voluntary carbon credit market. And what I'm focused on, whoops, is the forestry and land use sector, which, you know, blue carbon gets stuck in there. Yeah, so the natural climate solutions, which I'm sure you've heard a lot about the potential for natural climate solutions. Really, I'd like to focus on two ways of doing that. One is preservation, the reducing emissions through avoided deforestation and degradation, or the RED Plus program. And the other is through reforestation. Afforestation is definitely in there, but I'm not thinking about afforestation. In our work, we're only looking at reforestation. And so the volume of this market is really drastically increasing recently. This is the number or the volume of retired carbon credits. It means they've been sold to count against someone's emissions. They can't be resold, they can't be traded. This has been said, this is balancing out emissions that are existing. And circled in blue are the natural climate solutions, what was in that other, the blue carbon and the land sector. Sure, you've heard a lot about, there's some real problems in this market. And these are just a couple high-profile examples of things that have come out recently that, they're worthless. These credits, they don't provide any additional carbon sequestration. They would have happened without the project anyway. There was no deforestation risk in this area, and so those credits weren't additional. Or they're not permanent. They don't last 100 years. They are susceptible to natural risk, fire or hurricanes or volcanoes or could be anything. And that's true. There's a lot of that going on. It's a market-driven commodity, and there are plenty of people willing to make money in this new emerging market. So the company that I work for now, Earthshot, our solution to that is, well, first we need to provide reliable carbon projections. So we have to, if it's a reforestation project, you have to, when you're presenting the project to be certified, you have to give some estimate of how much carbon is going to be sequestered from this project. And right now, the methodology that is accepted for doing that is really broad. It's really loose. You can come up with those numbers in many different ways. So we want to do that in a more robust, more scientifically robust way. We also want to account for natural risk. What's the chance if you have a project in California that it might burn from wildfire? Or what's the chance that if you have a project in the tropics that there's going to be a change in the precipitation seasonality, and those trees that you planted that you think are adapted to the historical climate don't survive because things are changing. And there's also the need, a really strong need, to promote projects that actually provide both social and biodiversity co-benefits. And this has been one of the most egregious places where these projects are being misused, misrepresented, and actually causing harm. So our mission is to address all of these components. And so we're doing this, most of it, not the social part, but the other parts, with using CLM fates. And just to give a brief, because I'm sure most everyone here knows basically what it is, but it's using the land surface model in CESM that understands different sizes and ages of trees, cohorts of trees. And so we're modeling, it's a process-based model. So we're saying it's our best understanding of how forests actually grow. We're not using growth and yield tables based on historical information where things are changing. We're using our best understanding of how do forests grow. And what we can do with fates is we can say, well, what if we plant this mix of pioneer species and late successional species? What will that do for the carbon projections in the early period when it's really important that a project has a significant return carbon investment so that people will actually, investors will invest in the project? The first 7-ish years can make or break it from being able to happen in the first place. So how can we define the mix of PFTs, plant functional types, that will allow both robust carbon sequestration, but also lead towards a natural forest? It's not about doing plantations. It's about, in the end, recovering as close to the native forest as possible. And we can also then assess things like, what's the local temperature change? What's the local cooling effect? Are there changes in water availability? There are a lot of different ways that fates really, or CLM fates, enables us to look at, in a very robust way, what are the multiple co-benefits of these projects. And our ask, which I think actually I just need to talk to Josh, is high-resolution climate forcing data. So if you think about, these projects happen anywhere in the world. They're mostly in the tropics because that's where trees grow best, and that's where investors are willing to invest. And so the goal is to bring people like Microsoft who want to offset to people who live there who want to do reforestation because their land is degraded. And so the investors need to see a high rate of return. And so that's the tropics right now is where it's the biggest market. So this is just looking at half-degree temperature anomaly over South America. But what we really need is this is from analysis from Walker et al. In 2002, looking at what's the maximum potential biomass. We really need to get down to a much finer resolution because it matters, because these projects aren't happening over a half degree. They're happening over maybe tens of thousands of hectares if we're lucky. But maybe that can be handled outside of the CESM community. And the other thing that's really great is working mostly with Brian Dobbins to run CLM in the cloud. And that's going to be really, really important to have access. That a user doesn't have to have access to a supercomputer. They don't have to know how to set up the model and do all these things. We can create a containerized version that's easily accessible. Thanks.
And our last speaker will be JF.
I mean, this is actually super helpful to have those presentations before me, because they're all relevant, and they're very relevant to the basic way that we work. So McKinsey, in and of itself, the group I'm in, Climate Analytics, we actually try to do our downscaling by ourselves, because a big part of what clients are interested in is provenance. You really want to know that they're going to make decisions. A lot of them are going to make decisions that are relevant for the next 10, 15, 20 years for their business when it comes to climate adaptation, risks, resilience. So they really want to make sure that whatever we're providing them is of as good quality as we can get. And so one of the ways that McKinsey has decided is that, at least for parts of it, is to really do the work inside, because that gives us the full also flexibility of making sure that we can then answer the question with all the tools that we need, including, as I mentioned earlier, really trying to understand what are their needs and how can we adapt what we have, which is very limited. We're starting from CMIP6 simulations, from a variety of models, very similar to what was discussed before, and then understanding of what are the, whether it's super high resolution and going to very large scale. What is going to be the impact of company? They want to know what do they have to do, investment on really care about. And actually, I'm not going to go through my presentation because it's just too many words. I don't have that much time left, but I'm going to really jump to what I think is the most relevant for this group here. I mean, everything that was said before about the role of CESM as a climate model is absolutely true. The need for high resolution is definitely there. Have this building. And we have to come up with ways to express what can or cannot be done, and people do understand. So there is that communication with the client, which is also super interesting as a scientist, to really try to educate people on what can or cannot be done. yes, we can ask for higher resolution. At the same time, it's always going to be too little. But what we can generate for simulations here will only take us part of the way there. And I think that's fine, because what I've seen in the few months that I've been there is that there is then people like Jupyter Intelligence or additional groups. There's quite a few out there doing that, who will take the data and downscale it. Some of it is really good, some of it is really bad. And so I think there is a need maybe also for the community in general to maybe voice concerns when they start seeing data that are being bad, because people are going to use it. So, and that's where McKinsey is really trying to ensure that there is quality behind what we do, because we don't want our name associated with something that looks terrible. So on the CESM side, and I think more generally on the climate research side, I think the key aspect that I've come up with is that if this group doesn't do the fundamental science, no one will. And it is critical to have the fundamental science, because in some of the engagements that I've been on, clients come and ask a question. I don't have 2 years to answer the question. I don't have the capability of running CESM to do a simulation. I might have CLM, maybe some people out there, we're using other models, but we don't have the time. So we rely on published literature. And for very broad questions, I mean, one of them that I had was about weathering, right? Enhanced weathering over land in the ocean. So if people like this group don't provide those answers, don't research and do the work diligently, then we don't have the capability of providing those answers. My plea is actually, and maybe more so than before I left, that I think there is a place for fundamental science, and there is a place to explore fundamental science, and it can be done under the general view of how applicable it can be. But I don't think there is any, I think there's a huge need for this. And then there is a downstream dozens, if not hundreds of businesses out there who will take that information and then push it all the way to what is needed to answer specific questions. The second part is, with all the bashing that I've heard over the several years about CMIP and how useless it is, I can tell you that no one out there uses anything but CMIP 6. And they're expecting CMIP 7 to provide additional answers. There is no other source of information that is with a stamp of approval through the IPCC process, through scientific evaluations, through the whole community assessment of what those simulations are. And so that is the stamp of approval that really makes that data absolutely critical. So if people stop making those, then maybe we're good. Maybe we don't need maybe we don't need CMIP 7. But then there are all those questions for which we don't have answers. And so my plea is really focus on the science and doing as good a science as we can, and develop the best models that we can. Definitely agree with Mike on that. But that should be done in such a way that we can really use that information for real world questions that are going to come to people now like me and thousands and many other groups doing that. That is the only standard that will be provided, is the quality of the science that you guys do. So sorry I didn't go through my presentation, but it was boring anyway.
Okay,
So one of the doubts about this session that I had before organizing this thing, I mean, this is advertisement for the private sector, and I'm worried that many other people will leave NCAR for private sector. Hopefully that won't happen. So since we started 5 minutes or so late, so I'll spend about 10 minutes for, and you can answer.
Yeah, thank you for those really interesting perspectives on how climate models and climate data is being used. I guess maybe this question is most directed at Jean-Francois based on some of what he said about the importance of basic science and understanding. There seems to be this kind of assumption that there's a dichotomy between basic science and using modeling for process understanding and then actionable science purposes. And I think that's something that maybe we've struggled to really understand the interconnectedness of those two things as opposed to seeing them as dichotomous and conflicting. And so I'm just curious, like, in your experience, like, what have you learned that can help us to better articulate and leverage the connections that I guess the private sector and the end users see between the value of basic science and actionability, to draw those closer together in the way that we conceptualize CSM and future science? Does that make sense? Sorry, that was a lot, but...
There was a lot. But, and I can try to answer, and in a fairly succinct fashion. In my mind, the main portion of the additional information that will be the most useful to the client is, I think the way Josh presented it, that value chain, right? And I think there is no reason for people in CESM community to try to go all the way from 1 to 5. I think having an understanding on how the data will be used, where maybe we should stop and have collaboration and discussion, and having people say, who are well-versed in the language of climate modeling, like the team that I work with is like 10 people with PhDs in environment. So it's that is the connection, because after a while, it's going to be just a universe of opportunities. So there's no way you can go all the way. And I think they would disperse the strength of the effort to try to go too far. Maybe that answered your question.
Do you want to add more to that, Josh?
Just real quick, I think, yeah, we used to have a joke among some of our weather prediction colleagues that the metric depends on the user, right? There's an infinite number of uses you can imagine, so trying to design a system for that, it's like an unsolvable problem, right? I mean, I think I can pick apart whether Cortex is useful for some of my use cases, for example. It is. It's also very not useful for some of my use cases. But for CESM and the IPCC, you know, the CMIP stuff, it is what we have. It's a vast source of information. If it's used in a good way, it's the best you can do, right? And I don't think I have a specific ask around how you're going to build CMIP that's going to change that, right? So,
thank you. Let's take one question from here.
My question is, this increasing avenue of private sector really wanting science from us, wanting CMIP models, kind of data, using this data, profiting off of this data. How do you see reinvestment in the basic science happening? Your companies or across the private sector?
Yeah, I mean, that's a great question. I think, and it's a challenging one. Then there is no one answer, right? Because it depends on a lot of different things, right? I think everybody here can agree universities and a lot of stuff that goes on here operates on a different time scale than we have to operate on, for example, right? There's just fundamental disconnects. They're hard to break down. On the other hand, what things we can do is go to Capitol Hill and advocate for basic science, and we do that, okay? So, you know, we can do those kinds of things. When we're a bigger company, can we fund 3-year projects? Probably, you know what I mean? Whether that's a fit is a one-off question to answer, I think. So there's no magic bullet here, if you will. I mean, I think I'm with JF. I believe in the need for it, and I take every opportunity to tell somebody who has control of money that this needs to happen, right? And for the time being, it's just, I don't want to be a downer, but it's probably like the best we can do until the market gets really big. Oh, well, we're funding this basic science that's needed to generate $10 billion in value, right? I mean, and we're just not there yet.
Follow up later because we have quite a few questions. Sarah Manon?
So it's to the whole panel. I know you communicate the mean and the standard deviation, but there's uncertainty about the standard deviation itself. There's uncertainty about the uncertainty. IPCC revised its remaining carbon budget. And the tail for heat waves is more certain than the tail for tropical cyclones. And it can't.
We don't actually communicate, and it's done very differently for a lot of different things and different use cases. There might be a good reason to do the mean and the standard deviation. We're calculating the uncertainty of any point on that distribution, which accounts for exactly what you're saying.
Oh, but there are things that are not quantifiable, right?
In what sense?
Uncertainty you compute from the ensemble is not, it's just a model uncertainty. We don't know the true uncertainty.
We could talk about it later. I mean, the way we accumulate our distributions to do the fitting, and then the way we do the fitting accounts for internal variability and the uncertainty in the statistical estimation as well.
Tropical cyclones, we really don't know what the tail of the tropical cyclone distribution is.
Yeah, we use stochastic systems for that, but yeah, you're right.
But that's just what you do, right?
Discuss it over a beer or something.
Yeah.
And
I mean, we can all agree there's no truth here, right? So.
And one of the things is that decision makers are accustomed to making decisions with uncertainty, right? So they're not completely afraid of uncertainty. Matter of communicating the uncertainty.
How do you do that?
Well, you try.
Next, please. Yeah, go ahead.
Hi. So I'm going to move a little bit further down the value chain away from models, actually. In terms of you're valuing assets in various companies, I'm assuming that some of that asset valuation is turning into large-scale climate indices. Create derivatives. That kind of a derivatives market can potentially lead to something 2008, 2009 derivatives crisis. How much responsibility do companies bear in that, and more importantly, what do you do about the fact that a lot of the valuation is happening inside of a black box? I mean, both on the financial side and also on the risk side for things like fires and droughts.
Chris?
I mean, that's a great question. I think no matter what the information, people will try to make money. So I'm always personally, this is maybe a personal view more than something that would be relevant to my work. But I think information, we should never limit the amount of information that we provide. And yes, if now the market realizes that real estate is not the best place to invest, that might have very significant impact on people, or as in California right now, their ability to get insured. And and maybe I did not quite understand. I'm sorry, you were breaking up.
Yeah,
so it was
sorry
hard
about
to
that.
follow.
I think that what I was thinking about in particular was when pointing out the mortgage derivatives crisis, is that a lot of risk got actually pushed off towards people who were too poor to afford it. So the second it turns into a financial market is as soon as that all of those various cases turn into one index, that's something where it can be hedged. So I guess, if you're worrying about fires and droughts, what happens when it turns into an index and all of that gets washed out? It's a very similar kind of problem.
And I'm not close enough to the financial businesses. Nick.
Judith?
Interesting that we can't get the microphones to work in this room. My comment goes to Mike Pritchard, who might or might not be online at this point. I do understand that NVIDIA is main effort is not to provide NWP, but I really would like to see some probabilistic metrics, especially with the speed up that AI can do on NWP. I would like to see probabilistic metrics. I would like to see statistics about extreme events and go out to 3 weeks. And I think we need to see those metrics before we even start to consider AI trained on NWP for downscaling climate models. So this is a comment on climate, weather interactions, and AI, and we need to go probabilistic if we want to start to look at some of the uncertainties.
Mike, are you there?
Microphone worked.
Yeah. Are you there, Mike? No, he's gone, I think. He's picking up his kids, so that's the thing. Please go ahead.
Question is for Jean-Francois, which is around 2 years ago, McKinsey settled for $600 million for their role in exacerbating the crisis. Seen as an employee at McKinsey since 2015, adding structural safeguards against our data being used by McKinsey to disaster ends.
And I'm glad I wasn't part of McKinsey at that point.
Yes.
So I think what they're trying to do in the space of climate, they have put other safeguards. I think they're evaluating risks a lot more than they used to. For anything, any proposal that goes out has to be. Basically, they're hiring people like me. So they're putting us in charge of making those safeguards such that when analysis goes out, they try as much as possible to have people like me to be at least looking at it. It's a huge firm. It's 40,000 people. So it's I think that's the way they're trying to maybe regain some of and other things.
Thank you. We'll take 2 last questions, one from there. Neil and Lee.
I'll try to articulate if I can get the answer.
Hello?
Can you
This is Mike.
closer to the mic?
What I understand from your conversation, map 6 IPCC report, in return, what you are giving it to us? In return, can you take some of the actionable science model you produce? Can you make at least result available to the because these models, my model, this is NCAR model, this is their funded model. Everyday people, that's how this basic research is being done. Why the benefit only goes to the corporate, some wealthy people. Some of those basic.
We do open source some of our data, but the reality is we can't have a business that services other parts of the economy without keeping some of it private, because we won't have anybody pay us for it if we do that, right? Just the value proposition. It's the world we live in. But we open source data. Look at open source climate. Our data's in there. We also provide data to academics and NGOs who want to do things for underserved communities, for example. We can't open the book all the way, right? I mean, it's just that we wouldn't have a business. So.
For example, simply if I want to buy a house, I want to know. I do not want to go through the for them to get that estimate. Should have those reliable estimate available.
Yeah, well, I mean, there is open data for that question right now, right? First Street Foundation provides that for now. May not always be free, but that's what it is for now. And I think as the market matures, what you're going to see is more data being pushed to the public, because the companies like us will be able to make viable businesses elsewhere, right, as things grow. That's my expectation. In fact, even with lower price individual consumer level data, I think it's coming at some point. Again, the market's, it's early days on this stuff, so everybody's trying to figure it out.
I think my question relates to some degree to the other one. In the, you know, we're moving into an ecosystem where we have the climate scientists, the CMIP class models to make the projections, right, out 10, 15 years is what Jean-Francois said. And then you all are selling a product to well, what if we're wrong, right? What if we're wrong, and what if the carbon doesn't stay in the trees? What if the drought is actually worse than CMIP 6 projected? How do we take on the risk profile of that? Y'all are going to blame us, right? Because CMIP 6 wasn't right? Or the fundamental climate scientists, because that's the product, that's what we have. How do we avoid that? And because the timescales are long, right? The timescales are a lot longer than the return than the investment decisions, right? I think there's some fundamental back and forth here that also goes back to the question of how do we fund the fundamental science to do better? What if we find out that the global carbon budget really hasn't been affected by all the CDR stuff, right? All these kinds of pieces. So how do we work together is the question.
Yeah. I think your point is actually right. We have to work together, and to me it's an optimization issue. We have this much information now, and we have to make decisions. So what's the alternative? Wait 15 years to see if we're really going to hit 2 degrees? So I think there has to be feedback loops between what we need and what private sector decision makers in general, and what people can offer, and how that picture might change. But again, I think people are taking those decisions knowing that there is a risk that this may not be true, which is why some people decide not to do anything, and then they will be just living with the consequences of those decisions. I haven't heard at this point, but I've only been that if projections are correct, we'll go after the CESM2 chief scientist, for example.
That I think it ties into, Monica, what you asked about. What's the tie between actionable science and basic science, and also the understanding of what does the model do? From just the simple carbon perspective, you can't ask a model to have any sort of robustness to drought if you're not modeling trees that are sensitive to drought. And so I think having, we've all worked with the models before going to the private sector. And so I think that, keeping the interaction and communication across all of us is really important, because then it's our job to communicate to the people that we're working with where the model is applicable, and really do our best effort to categorize the risk. And it's, what Sanjeev was saying, that, or maybe it was someone else, the uncertainty just compounds, because is everywhere, and you have to do your best to represent that accurately, and then it's up to the person that you're working with to decide if that's a level of risk they can accept. And that's something I feel like the financial, that industry they're all about assessing what level of risk they're comfortable with, if we can do a good job of characterizing that risk.
I just had something that ties back into a couple of the comments already made. There's a lot to your question, and there's a lot of things we need to do. Some of it is just being responsible human beings, right? And being open about what things can and can't do. And the private sector is not just for companies like us, but from our customers, they're looking for people with climate expertise so that they can understand what they can and can't do, right? This is a growing area of employment. How fast anybody can predict. But I will say, if anybody who's paying attention knows that these recent heat waves, like in the Northwest and Southern Europe and all that, none of us could have predicted this, right? Under any circumstance in the next 15 years, right? So has that stopped them from using the data? No. On the other hand, you get some companies will say, well, we're not going to look at anything related to 5.85 or 8.5 because that's not realistic anymore, right? And my response to that is, well, we may not reach that temperature, but the impacts that you might find from that can easily happen under another scenario. So you really should be paying attention to this. You shouldn't think of yourself on a curve. So a lot of it's education, moving along the maturity and making sure we're responsible and keep the communication going. I mean, it's a huge thing we're trying to do here, right?
Well, let's thank our speakers one more time. Thank you, everybody. Thank you. And thank you, Mike, if you are still online.
I'm here. I'd love to respond to the question if there's time.
Okay, go ahead, please.
Okay. Yeah, no, thanks. I really appreciated it. I basically just fully agree. Long rollouts, probabilistic assessment, it's exactly what we're working on. And I invite anybody who's interested to join the analysis. We have 2 atmospheric scientists in the company. I'm sure you know what's actually required for proper probabilistic assessment. Our models are open source, and if you'd like to contact me, if you're interested in the probabilistic properties of these AI models, we know a bit, be happy to share it, and I'd be especially delighted to collaborate. Thanks.
Thank you very much, Mike. So there should be a reception outside in celebration of the RISE project that's actually happening next door. And it's funded by Silver Lining. 7:30, so please enjoy. Thank you again. And we'll start at 8:30 tomorrow, and then you are supposed to take your posters down at lunchtime tomorrow.